In today's video, we're going to discuss carbon and its compounds. In the early history of chemistry, chemists had discovered that molecules derived from living sources, so from plants and animals, tended to behave and react differently than molecules that were derived from the natural world, so ores and minerals and that type of thing. And this was the first distinction of what they called organic chemistry, which they associated with living things, and inorganic chemistry, which was derived from basically everything else, the non-living world, so to speak. They also noticed that these quote unquote organic compounds via analysis tended to have always a very small subset of elements that made up these compounds. Notably carbon, hydrogen, nitrogen, oxygen, sometimes the halogens, and maybe just a few more handful of elements. And so this is where we begin when we are talking, when we're just first talking about organic compounds. The definition of organic chemistry today is the study of carbon and its compounds, and because carbon is at the center of all organic compounds. And so the other thing they recognized was that these particular different elements, these organic elements, tended to form a certain number of bonds, and this was fairly regular. So for example, they noticed that carbon typically formed 4 bonds. As you can see here, depicted by these various different molecules here. They might be multiple bonds, they might just be single bonds, but if you count the number of lines to each carbon atom, they always amounted to 4. If we go over to another organic element, such as nitrogen, they found that nitrogen tended to form 3 bonds. Again, you'll notice here that the 3 bonds can be made up of single, double, or even triple bonds. And then continuing along, they found that oxygen tended to form 2 bonds, and then hydrogen and the halogens tended to form 1 bond. And this was the start of their basis of being able to piece together what these particular organic compounds look like, based on what we call these valencies or valence rules. And this is referring to the number of bonds that these different elements typically formed. And so basing this on the valencies of these different elements, then we can now develop what we call Lewis structures for these organic compounds. This should be hopefully a review from your first year chemistry. Here is sort of a list of different, I'll say, instructions or steps to follow in order to develop Lewis structures. But what's important here is that you have a good handle on being able to draw Lewis structures quickly and obviously correctly. This is where we start. So we'll do an example here. If you look at this first compound, the connectivity is implied here. So we've got 3 carbon atoms. So we'll look at this first structure here. And when we draw a Lewis structure, typically what we do is we draw all the bonds and all the lone pairs on the atom. So everything is shown explicitly. So I'll start off with my first carbon atom, and we'll develop from there. Actually, first thing we should do is actually calculate the number of valence electrons we have at our disposal in order to develop this particular Lewis structure. So we start off here with carbon, and we ask ourselves basically how many valence electrons can this element bring to this structure. The valence electrons are essentially tied with the group number of the different elements, and so carbon is in group, this is older nomenclature, but carbon is part of group 4, and so carbon brings 4 valence electrons per carbon. So we have 3 here, so we have 4 electrons for each carbon times 3, and therefore this brings us 12 electrons. Hydrogen is in group 1, and therefore it has 1 valence electron, and we have 3, 5, 6 hydrogen atoms here. And then finally, we have one oxygen atom. Oxygen is in group 6, well, it's actually 16, but the older nomenclature is group 6, and so therefore it has 6 valence electrons. 1 is equal to 6. So if we add this up, we have a total of 24 valence electrons in order to distribute to develop this first Lewis structure. So typically what we do is we just start with the carbon skeleton. And so I know I have a carbon here. I know it has 3 hydrogen atoms attached to it. That's the CH3. And then now I have a CH2 group. So this carbon is attached to the next carbon. And there are the 2 hydrogens attached to it. And then I finish off by saying this carbon, it has a hydrogen and an oxygen atom attached to it. And so we start off by just drawing basically the skeleton of this particular structure as it's been given to us. And we just include single bonds at this particular moment. What we want to do now is count the number of electrons that we've used of the available 24 electrons that we can use. So we recognize that a bond, any one of these lines, represents 2 electrons. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18. So I've used up 18 electrons forming these single bonds. And so I can subtract that from my total here. And this leaves me with a total of 6 valence electrons still that I have yet to distribute on this molecule. If you just go back to our steps here, and if we look at, step 2B here, so we subtract the number of bonding electrons from the number that we had originally calculated. We just did that. So we now have 6 electrons left. So it says any electrons that are unpaired are added to atoms that lack a full octet, typically heteroatoms. So we do have a heteroatom here, oxygen. Recall a heteroatom is anything other than carbon and hydrogen. And I have 6 electrons yet to distribute. I'll notice that oxygen is only taking part into 1 bond so far, and therefore it only has 2 electrons around it. So if I put 8 or 6 more electrons around it, it will now have a complete octet. Okay, so I've now added the last 6 electrons, and I have no more electrons to distribute. But we're not done now. Now what we need to do is assess our Lewis structure, and we need to determine whether or not this is the best Lewis structure. All the hydrogen atoms should only have 1 bond or 2 electrons around it. They all meet that requirement, so they are good. If you look at the left-hand carbon atom and the central carbon atom, you'll see that both of those are forming 4 single bonds and therefore have 8 electrons around it. So it's met its valence requirement, which is 4, and it's following an octet of electrons, which again is something that carbon would like to do. The carbon attached to oxygen, however, you'll notice that it's only involved right now in 3 bonds. They happen to be 3 single bonds. So therefore, there's only 6 valence electrons around that particular carbon atom. So that carbon atom right now is electron deficient. And then if we look at the point 2C here, it says atoms still lacking an octet are satisfied by using lone pairs from adjacent atoms to form multiple bonds. So this is the situation we're at right now. We have an atom, this carbon atom here, which is lacking an octet. It does have an atom directly adjacent to it, which does have a lone pair. So what we're going to do is we're going to take one of these lone pairs. It does not matter which one. And now what I'm going to do is instead of leaving it as a lone pair onto oxygen, I'm actually going to put it in between the oxygen and carbon atom to form a bond. Now, because there's already a bond there between carbon and oxygen, this will now form a double bond. So I will just redraw this here. So nothing has changed over here. And now what I've formed here is a carbon-oxygen double bond. So now you'll notice that if we look at the number of electrons around all our atoms, they'll all satisfy the octet or the 2 electrons that we need around hydrogen. That carbon, which was electron deficient, notice now that it is taking part in 4 bonds, so a double bond and then 2 single. It does now have 8 electrons around it, and therefore and is happy, and that oxygen still has 8 electrons around it. And again, oxygen typically likes to form 2 bonds, and you can see that we have 2 bonds here to oxygen. So this is our final Lewis structure. And before you finish off, you should always make sure that your Lewis structures, that you actually calculate the formal charges of all the different atoms. Just because the molecule is neutral overall does not necessarily mean that there's no formal charges. In this particular case, what you'll find is that all the formal charges for all the atoms are equal to 0. But this is an exercise that you should go through to make sure that all these atoms have a formal charge of 0, as they do in this particular case. So that's one example. The others we'll look at during one of our live meetings. Okay, let's talk a little bit about bonding in organic compounds. So these lines that we draw in between these different atoms, these single, these double, these triple bonds that we draw them, these are known as covalent bonds. And the covalent bonds are essentially a sharing of electrons in between 2 different atoms. And so we can show you this particular type of bonding and how this arises from the overlap of the different orbitals that are involved. This should be a review from your first year chemistry. And just recall that, because we're dealing with organic elements, carbon, hydrogen, nitrogen, oxygen, we're typically only generally going to talk about s orbitals and p orbitals. And so all we need to do is remember how these particular orbitals can overlap with each other. So just recall that in a sigma bond, so we use this Greek symbol here of sigma, we have essentially a head-on overlap between either 2 s orbitals, 2 p orbitals, or an s and a p orbital, okay? Now, in this particular example, they've actually gone ahead and used the hybrid orbitals, which we're going to talk about a little bit later. It essentially looks like a p orbital, however. And so what we're saying is we have this s orbital here, and then we have this lobe of so this lobe here of essentially this sp3 hybrid. And if you overlap the end of the s orbital with the end here of the p orbital, as long as they have the same phase, then you will get constructive interference, i.e. you'll get an actual chemical bond. And that's what they're trying to show you here in this picture here. So what they've shown you here in this sort of pink or purple sort of color is the net, what the orbitals look like after they've overlapped, after they've had this constructive interference. Okay, you can see essentially that the lobe has kind of gotten bigger. So now you've got one lobe because the S and P have kind of mixed together, creating this larger lobe. Okay, now the thing to really look for here is I want you to look at the areas in between the nuclei of these particular different orbitals. So the s orbital, the nuclei here is given as a small green circle. Same thing here for this sp hybrid or the sp3 hybrid or the p orbital. And if you look in where they actually have the bond here and in between these 2 nuclei, you have an area of overlap with the orbitals, and that means a bond. Okay, there's no node there. And by a node, we mean a 0 probability of finding the electron. Remember, these orbitals, what they describe, an orbital is nothing more than a mathematical model that describes the likelihood of finding an electron in that area of space. So in this particular sigma bond, we've got this now lobe in between these 2 different nuclei, and it's telling us then that we have, the probability of finding the electron is in between those 2 different nuclei. We can get the same type of bond, a sigma bond, by having either 2 p orbitals or 2 sp3 hybrids overlapping. So again, you can see you've got a shaded lobe here and a shaded lobe here, and they're coming together to overlap. And then when they add together, you get constructive interference. So you get something that looks sort of like this. Again, these are more like computer graphics of this. This is just a way for us to visualize. But what's important here again is if you look the area between the two nuclei, that there is an actual overlap there, which meaning that there's a bond. If we were to look at, for example, the overlap of, if we look at an anti-bonding combination here. So if you had a p orbital and another p orbital, but now the phases don't match. So if you add this like this, then typically what we get is something that looks like this. And here I'm going to shade in the nuclei of each of those two different atoms. And you'll notice now that there's an area right here that I'm putting a line through where there's no actually overlap of the orbitals. This is called a node. And this is important to recognize those areas in between the nuclei, because if there is overlap, then that means there's a bond. And if there's no overlap, i.e. a node here, means that it's not a bond, i.e. it's an anti-bonding interaction between these orbitals. So we can have two s orbitals overlap to form a sigma bond. We can have an s and a p orbital that overlap to give you a sigma bond. You can have two p orbitals, or even these sp3 hybrids, which look very similar to p orbitals, and they can all overlap in a head-to-head fashion to give us sigma bonds. How do we get pi bonds? Well, this is when these orbitals interact, instead of a head-to-head fashion, they interact in a side-to-side fashion. And of course, this can only happen with p orbitals or d orbitals and so on and so forth. We can't have side-on overlap with the spherical s orbitals. So here they're showing you two p orbitals. It's unfortunate that they've got the shading, the two colors of the shading being very close. So on top here, they have more of a purple color, and on the bottom, they have a blue color. The point is, when you have overlap with these two orbitals, notice that they're coming together a side-to-side fashion, right? So these two purple lobes will interact, or they will have constructive interference, and these two blue lobes of the other phase will come together in a side-to-side fashion to have overlap. And this gives here now, so you can see there's this region here. So now we've got this constructive interference here on top and on bottom, and this is known as a pi bond because of the orientation of the two different bonds, or I should say the two different orbitals, how they came together. Again, you can see they've got the node defined here, and they still have them here in the pi bond picture. And p orbitals inherently have a node. So there's a node here in this p orbital, and there's a node here and here in the second p orbital. So that means there'll always be a node in pi overlap. That's just inherent because of the p orbitals. But what I want you to look at is this area on top here, where I'm drawing a line, and you'll notice that there's no area there where there's no overlap. There is overlap here, and i.e. this is a pi bond, an actual bond. If we had these two p orbitals come together in an anti-bonding fashion, so now what I'm going to do is I'm just going to flip the phases of one of these p orbitals. If we have something like this, then what we have is they kind of bend away from each other. So there's our node. So we still have this nodal plane here, but that's again inherent from the p orbitals. But what I'm more interested here is seeing that now there's a node in between those two different lobes, and that's an area of zero probability of finding an electron, and therefore this is not a bond. This is an anti-bond. We're going to get back to these orbital pictures a little bit later on when we start talking more about pi bonding. Another concept to look at here is this idea of dipoles, and dipoles are nothing more than electronegativity difference between different atoms, bonded atoms essentially. So what we have here is a very small number of elements. These are like typical organic elements, And we've included here, this is from the periodic table, and they've included here the Pauling's electronegativity values for them. And basically, the greater the difference between these two atoms, those values, the bigger the the bigger the electronegativity difference, and therefore the stronger the bond dipole. So what we have here in this picture is what's known as an electron density map, so to speak. And so you've got, it could be different colors, but in this particular case, they're kind of shading a green. And they're trying to give you an idea of how the electrons are distributed over this carbon-hydrogen bond, okay? Carbon is more electronegative than hydrogen, not by much, but if you look at the values 2.2 versus 2.5, there is a small electronegativity difference between these two atoms. So it would make more sense that there would be a little bit more electron density around carbon than there would be around hydrogen. And this is why that sort of green sphere or blob, if you will, on top of the carbon atom is slightly bigger. If these would have had the exact same electronegativity, then this green cloud above these atoms would have been symmetrically distributed, and it's not. So it's one way of visualizing this bond dipole. Another way is to just write in these partial charges here. So they're using the small Greek letter of delta. And so whenever you see a delta, we mean a partial. So this means that there's a partial positive charge on hydrogen, a partial negative charge on carbon. And yet another way of doing this is just to draw sort of a vector or a dipole, in this case, showing you the direction of, where the electrons are pointing. And in this case, they're pointing in the direction of carbon. They are all showing you the same thing. Now, even though there's an electronegativity difference between carbon and hydrogen, typically for most organic compounds, we kind of consider carbon-hydrogen bonds to be essentially non-polar. They are very slightly polar, but for all intents and purposes, we consider them to be non-polar. If we look at a more extreme example of this, so let's just look at an oxygen-hydrogen bond. So again, if you go back here, you can see here that there's a much bigger electronegativity difference between oxygen and hydrogen versus carbon and hydrogen. And so if you look at this electron density map, notice that there's a much bigger green cloud around oxygen than there was around the carbon when it was a carbon-hydrogen bond. And this is reflecting that greater electronegativity of oxygen. So again, we could represent this bond as, delta plus, delta minus, or as this vector. Again, you'll notice that this vector that they've drawn here towards oxygen, notice that the line, the arrowhead itself is just bigger. Like this line is just generally bigger in this example than this one. And that's to try and show the magnitude of that dipole. So oxygen-hydrogen bonds are definitely considered to be, polar bonds. The reason why we're interested in whether bonds are polar or very polar or non-polar is because understanding this allows us to predict the structure, the properties, and even the reactivity of these organic molecules. So having an understanding of this, again, we're basically talking about, where are the electrons distributed along this molecule? Having that knowledge gives us a better understanding of their physical properties and reactivity. Okay, so we've talked about how the typical valencies of these atoms. So we typically say, in organic chemistry that if you can count to 4, you're good. So 4 bonds to carbon, 3 to nitrogen, 2 to oxygen, 1 to hydrogen and the halogens. We can also use Vesper theory in order to explain basically 3, there's only 3 here, general shapes that we typically see for these organic elements. And so basically the 3 shapes are linear, trigonal planar, and the big one here is tetrahedral. So in a linear geometry, this is typically when we have triple bonds involved. So a great example of this would be this acetylene molecule here. So you can see that both carbon atoms, they're part of a triple bond. They still have 4 bonds, but they're not part of a triple bond. And this bond angle here is typically about each carbon atom is about 180 degrees, making the molecule linear. If we have carbon, which is involved in a double bond and two single bonds, then we typically get what's called a trigonoplanar geometry. So again, it's like three electron groups, so to speak. So in this particular case, an oxygen and two hydrogen atoms pointed at about 120 degrees away from each other in the same plane. And that's where the name planar comes from in this geometry. And then finally, when carbon is involved with four single bonds, the easiest way of getting those electron groups about that central carbon atom would be to put them into a tetrahedral geometry. And so those are the three typical geometries that we explore in organic molecules. So again, you can see here, they're just highlighting the linear aspect of carbon when it's involved in these triple bonds. And you can see here, they're highlighting the bond angle of 180 degrees. So again, we're just using simple Vesper theory here. We're saying, look, there's two electron groups. So if you look at, say, for example, this carbon atom, we have two electron groups about that carbon atom, a hydrogen atom and a carbon. And how can we get them as far apart as possible? When there's two electron groups, the easiest way of doing that is putting them 180 degrees apart from each other. And this is typically what we see. And the bond angles for these triple bonds are 180 degrees, and that portion of the molecule anyways is typically linear. Same thing here when we have trigonoplanar. So when we have carbon involved in a double bond with two single bonds, again, how do we get these three electron groups distributed as far apart from each other around that central carbon? Well, we keep everything in the same plane and we put them at about 120 degree bond angle. It forms this triangle, and so this is where the term trigonal planar comes from. So it forms this triangle sort of shape, and it's all in a plane, and they're trying to highlight the planarity of that carbon atom in this picture here. And then finally, when we get to four single bonds around the carbon, it likes to form this tetrahedral geometry. This one's a little bit more, perhaps a little more difficult to visualize because this molecule is no longer planar. It is actually, it does have some three-dimensionality to it. So the way they're showing you this particular structure here, you're going to have a couple bonds that are in the plane of the screen or the paper. So in this particular case, from the drawing above, this bond here and this bond here are in the plane of the screen, and then the wedge. So this particular group here is coming towards you, and this one here is slightly pointing away from you. The fact here, though, is that understand that because we have four groups and this molecule is not planar, we have bond angles of 109.5, and this is the best way we can do that to avoid any electron-electron repulsions. Now, one of the things we need to do, and this is what we're going to finish with, is that when we deal with tetrahedral carbon atoms, and we're going to see this a lot, we want to try and show as best we can the three-dimensionality of that carbon atom. And so this is why we do use this, for example, this wedge here and this dash, and that's to show that the group is either coming towards you or pointed away from you in the plane of the paper or screen. And it's just important that you get a feel for how to use these dashes and wedges. So again, what you need to remember is that when you're looking at a tetrahedral carbon atom, typically the way we orient the carbon atom or the rest of the molecule is that two bonds are in the plane of the screen or paper. And so in this example above here, it's these two upper bonds. They're just drawn as simple lines. So I know that they're in the plane of the screen. And then the other two bonds will be a dash and a wedge. The other thing to notice is that if you look at the two bonds that are in the plane in this example, they kind of form a V. And this will typically be what we see. And then what you want is that V is essentially kind of pointing up right now. And so your dash and your wedge in this case should be pointing in the opposite direction. And that's what this note here is trying to show you. So the dash and wedge should also be in a V, but they should be basically, pointing in the opposite direction as the other V of the two bonds that are in the plane. And typically we have the dash and wedge a little bit closer towards each other than normal bonds. So it should look something similar to this. If ever you have all your hydrogen atoms pointed in the same direction, then you're going to run into problems because this is not depicting a tetrahedron. It's depicting some highly strained sort of geometry around carbon atom. The thing to remember is that you can rotate these different tetrahedral carbon atoms. So there's no rule, so to speak, that says that the two bonds that are in the plane have to be pointing in a particular direction. So pay attention to these four tetrahedral carbon atoms that have been drawn here, and just look at, where the dashes and wedges are placed, and in relation to where the two bonds are that are in the plane of the paper, and how they're placed. So, like, for example, here, the two bonds in the plane could be pointing down, and therefore your dash and wedge will be pointing up, or that can be reversed, as in this case here. But again, they don't have to be either pointing up or pointing down. They can be kind of pointing to the side, as shown in these two examples. So just understand that all four of these are completely correct. All we've really done is just rotate the different orientation of that tetrahedral carbon atom. In today's video, we're going to continue talking about some fundamental aspects of carbon and its compounds. We now want to just introduce a few bonding models that are typically used to describe the bonding in especially these organic molecules. The first that we're going to look at is known as the valence bond theory, or VB theory. And the defining aspect of valence bond theory is that, of course, bonds involve the sharing of two electrons, so spin paired electrons, and they do this via the overlap of atomic orbitals between atoms, just as we looked earlier in the previous video on how these atomic orbitals will overlap with each other. So we say that these are what we call localized bonds, and that the electrons are confined to that region in between the two participating atoms. Highlighting this now because this will be in a little bit of a difference from the other bonding model that we look at in a few minutes. In order to use valence bond theory, we use what's called hybrid orbitals, and we'll explain this in a minute. And this is to help us explain the geometry, the observed geometry of organic molecules. This idea of hybrid orbitals, or hybridization, you have to understand is not an actual physical process, but is nothing more than a mathematical one. The two bonding models that we'll be looking at, they both have their pros and cons, so to speak. One of the nice things about valence bond theory is that it really helps us explain the geometry of these different organic molecules. However, it does have some shortfalls when it comes to the reactivity of these molecules, which is why we look at the other bonding model, which we'll talk about in a moment. Okay, so in order to look at valence bond theory, first what we need to do is build what we call these hybrid orbitals. And the reason why we build these hybrid orbitals is because if you just look at carbon, and if we look at the simplest organic molecule, in fact, we'll go back here, and if you look at the simplest organic molecule, which is methane, and if you look at its valence electrons, there are 4 valence electrons. Those 4 valence electrons are found in the 2s orbital. There's 2 electrons found in that 2s orbital, and there are 2 other electrons found in 2 different 2p orbitals. So if you look strictly at the valence electrons on carbon and where they're located in terms of what orbitals they're located in, so 2 electrons in a 2s, and then 2 other electrons found in 2 separate 2p orbitals, it becomes hard to rationalize how come, for example, this simple organic molecule here, which is methane, and we know that methane is in a tetrahedral geometry, it becomes very difficult for us to rationalize how this geometry comes about strictly using a 2s and 2 2p orbitals. We have a hard time trying to explain the geometry via this. So this is where we've come up with this mathematical model, and it's used, in fact, to describe the observed geometry of this particular molecule. And the concept of these hybrid orbitals is not difficult. All we're doing is we're going to take some atomic orbitals, and I want you to imagine that we're kind of sticking them in a blender, and we're going to mix them together, or as we say, we're going to hybridize them into new orbitals that have different sort of shape. And so when you're dealing with the tetrahedral geometry, you're going to use the 2s orbital of the carbon atom, and you're going to use 3, and there are only 3 of its 2p orbitals. So what you're doing is you're mixing 4 atomic orbitals, a 2s and 3 2p's, and you're sticking them in a blender, and you're blending them together, and what's going to come out of that are 4 identical hybrid orbitals. And we call these hybrid orbitals sp3, okay? And this name is not really that clever. It's called sp3 because we've literally mixed an s orbital and 3 p orbitals, right? So the 2s and the 3 2p orbitals. And this is where the term sp3 comes from. The point is that these sp3, these 4 sp3 or hybrid orbitals, they're all shaped identically, okay? And they have this kind of shape here. They kind of have a modified p orbital shape. So if we imagine a p orbital is typically drawn in our little cartoonish thing like this, the hybrid orbitals have sort of a bigger lobe, and then the shading is like that. And that's what they've represented here. So this green circle here represents the nuclei, and you can see that you've got this dark green and lighter green shape for the 2 lobes of this sp3 hybrid. The other 4 look identical to this hybrid, and the only difference is the spatial direction that it's pointing. And when we have these 4 identical sp3 hybrids, we can now arrange them in space so that they actually point to the corners of a tetrahedron, okay? And that's what they're trying to show you here. So what they've done here is they've actually omitted in this picture, they've omitted these little small lobes here, just to make the picture a little bit clearer. And you can just see the large greener lobes. And now they're pointed at the 4 corners of a tetrahedron, which would be at 109.5 degrees from each other. And so we do this, again, I want to reiterate, we make these hybrid orbitals so that we can have them be equivalent, so that we can point them in the 4 directions to help us explain the tetrahedral geometry of methane. And it's simple as that. All we do is we take a certain number of atomic orbitals and we mix them or hybridize them into these new, what we call hybrid orbitals, okay? So if you mix a 2s and 3 2p's, you're gonna form, so the number of atomic orbitals you start with is the number of hybrid orbitals you form. And in this case, we form 4 equivalent sp3 hybrid orbitals. So what they've done here in this little picture, so they're showing you methane again. Here are the 4 hybrid orbitals in a tetrahedral geometry. And in this case here, they've actually included those little small lighter green lobes. They're kind of pointing in the opposite direction of their larger green lobe. And so they're the 4 hybrid orbitals pointing in the tetrahedron. And then those larger green lobes are going to overlap now with the 1s orbital, and that's the only orbital available for these hydrogen atoms. And so you get here overlap between this s and this sp3 here, and here, and here, and here. And they're basically showing you how this molecule of methane is coming together. So that's what they're trying to show you here, is they've overlapped now the sp3 hybrids on carbon with the 1s orbitals on hydrogen to form these new, these 4 new carbon hydrogen covalent bonds. Now, strictly speaking, we have the same sort of effect that's happening with nitrogen. So we know that nitrogen typically likes to form 3 bonds, not 4. But remember that although nitrogen only has 3 bonds, it also typically has a lone pair on it. And so, and again, if you go back to Vesper theory, you'll see that the, I think it's called the molecular geometry is still tetrahedral for this NH3 molecule, except its actual geometry is slightly altered because we know that the lone pairs take up more space than a bond, so we would call this trigonal pyramidal. But it's still based off of the tetrahedral molecular geometry. Same thing happens here. The nitrogen would use its 2s orbital and its three 2p orbitals. Those 4 atomic orbitals will get mixed to form 4 hybrid orbitals, and they are sp3 hybrids. And again, they're showing you those 4 sp3 hybrids here. Okay. Now you can see that in this NH3 molecule, you have 3 hydrogens now that are forming a bond to the nitrogen atom, and they've shown you those 3 hydrogen atoms in gray, and they're going to overlap to form these 3 covalent bonds down here. Now you'll notice that one of those sp3 hybrids never overlapped with a hydrogen atom. Well, that orbital contains 2 electrons. That's why they've got these 2 little dots here. And this is the lone pair. So this is a pair of electrons, unpaired electrons, found essentially in an sp3 hybrid that just never overlapped to form a bond. But it's still there, and it contains 2 electrons, which is where we would find the lone pair on nitrogen. Now, if you look at, and you'll see that when we go through these different hybrids, we're basically going through the 3 typical geometries for these organic molecules. We're just kind of doing them in a reverse order here. So we started with tetrahedral. Now let's look at trigonal planar geometry. And again, the reason behind this is because we are using valence bond theory is actually very good at helping us describe the geometry of these different organic molecules. So when you're dealing with trigonal planar geometry, all we're going to do different now is instead of using the 2s orbital, atomic orbital, and 3 2p orbitals of carbon, what we're going to do is we're going to use the 2s, and we're only going to use 2 of the 2p orbitals of carbon. So now we're using 3 orbitals, an s and 2 p's. And yes, as you guessed it, this particular hybrid, when you mix those 3 atomic orbitals together, form an sp2. And again, it's because we're using 1 s, and 2 p's, so p2. Again, I want you to see here that this hybrid orbital, this sp2, if we go back to the sp3, it's identical to the sp3s in terms of shape. Okay. Again, you've got that larger, darker green lobe with a smaller, lighter green lobe. In this case, is the color coding they're using. Okay. The only real difference here is the number of these sp2 hybrids that we're forming. Because we mixed 3 atomic orbitals, now we're only forming 3 sp2 hybrids, right? And so we have 1 here, 1 here, and 1 here. Now recall, carbon does have 3 2p atomic orbitals. We took 2 of them to mix with the 2s orbital to form these 3 sp2 hybrids. That third 2p orbital, we didn't do anything with it. So we say it's an unhybridized orbital. It's just a normal 2p orbital, and that's what that is right there, okay? So now, if you take those 3 sp2 hybrids and were to arrange them so that they're, again, as far apart as possible, they would be arranged in this trigonal planar fashion, okay? And that's what they're trying to show you here. Again, they've omitted the smaller green lobes, lighter green lobes for clarity, but you can see that here they're arranged in this trigonal planar fashion. So we've got that triangle and they're all in the same plane. Now, what we're going to do is we're going to tilt that plane a little bit, and then we're still going to include, and that's what they're doing in this picture here, that unhybridized 2p orbital, the 2p orbital that wasn't used to mix to form these hybrids. And it's perpendicular, that 2p orbital, and this is a really important concept to understand, but that 2p orbital that was not hybridized, the one in purple and blue there, is perpendicular to the plane of those 3 sp2 hybrids. Okay, and it's that unhybridized p orbital that allows us to see these multiple bonds, these pi bonds. So as an example of that, if you look here, this is the molecule, this particular molecule here that they've shown. This was the molecule here. And so if you focus on the carbon atom is trigonal planar with bond angles of approximately 120 degrees. And so at that carbon atom, this is the skeletal structure that you have, okay? And this double bond here between the carbon and oxygen, again, you have to understand, what does that double bond mean? A double bond is a component of, it's an addition of two components, a sigma component and a pi component. And that pi component is from side to side overlap of atomic orbitals. And so what we're going to have here is one unhybridized p orbital on the carbon, as we see here, overlapping with an unhybridized p orbital on the oxygen atom in a side-to-side fashion, and that's giving us that pi bond. Okay, and then finally, basically as we go from sp3 to sp2, and now we're going to be looking at sp hybrid orbitals, basically what we're doing is every time is we're just mixing one less p orbital of carbon into our little blender, so to speak. So the linear geometry, what we're doing is we're taking the carbon 2s orbital, and now we're only taking one of the three carbon 2p orbitals. And so we're mixing two atomic orbitals, a 2s and a 2p, and therefore we're going to get two sp, in this case, hybrid orbitals, okay? And again, sp because we're only mixing an s and one p in this case. And again, I'll point out here that the hybrid orbitals look just like they did before, except the difference really now is that there's only two of them, okay? And the best way of getting those two orbitals as far apart as possible is in a linear fashion. And again, in this particular picture, they've omitted the lighter green orbitals. Now, just because we didn't use those two p atomic orbitals to mix in this case, they're still there. We can't forget about them. And so that's why they still have them drawn here. They look like normal p orbitals, and they just haven't been hybridized. So if you take this carbon atom here and add the two hybrids, as they've done here, now what they're going to do is they're just going to superimpose on top of that the two unhybridized p orbitals. And they're perpendicular to each other. So one of them is going straight up and down, the other one's coming along in and out of the plane of the paper here on the z-axis, so to speak. And again, this helps us understand where triple bonds come from, because triple bonds are made up of two pi components. And those two pi components are coming from those two unhybridized p orbitals overlapping with whatever other atom it's overlapping with, the unhybridized p orbitals of that other atom, giving us 2p or 2 pi components. And of course, the geometry here is 180 degrees between these sp hybrids. And again, this is so we can get them as far apart as possible. So these hybrids all look the same, and really the difference is the number of these hybrid orbitals, depending on how many atomic orbitals we mix. And again, we use this in order to help us explain the different geometries of these organic compounds. Okay, so let's review another topic that I'm sure you've seen in your first year of chemistry, and this is this idea of resonance structures. The important thing to understand with resonance structures is that, well, first of all, Lewis structures are limiting in how they can describe the bonding in a molecule, especially when we're involving pi electrons or pi bonds. So what we do is, in order to give a better picture, if you will, of these different, the delocalization, if you will, of these pi electrons in the pi component of the molecule, we use what's called resonance structures. Okay, and so this molecule here is an allyl-cation, and you can see here there are 3 carbon atoms, and these 3 carbon atoms have 2 of the carbon atoms are involved in a pi bond, and one of them is not involved in a pi bond. The problem is, if you just look at that picture, and if we understood if that picture was 100% accurate to what the structure of the molecule would be, we would have an inaccurate picture of what the molecule looks like, because the 2 carbon atoms that are forming a pi bond, we'd expect that bond to be shorter than the 2 carbon atoms that are involved in the carbon-carbon single bond. It turns out in this molecule that all the carbon-carbon bonds have all the same lengths. And they happen to fall directly in between the length of a carbon-carbon single bond and a carbon-carbon double bond. So clearly this Lewis structure that we're drawing is not accurate. It's not giving us the true picture of what this molecule is. And this is why we look at these different resonance structures. If you look at the, say, the left-hand carbon atom and the central carbon atom, notice there's a pi bond there. And so the sigma framework, so all the single bonds in this, they're all formed from this overlap of these sp3 hybrids, right? Now, these two carbon atoms, as they're drawn here, they are involved in a trigonal planar geometry. So they would actually be involved with sp2 hybrids. And again, we'll just point out that when you're dealing with sp2 hybrids, you have your 3 sp2 hybrids, and of course you have this unhybridized p orbital. That is the orbital that they're showing you in these pictures here to the right. So these little p orbitals that they're showing here on all 3 carbon atoms are those unhybridized p orbitals on those carbon atoms. Okay, and you can see here that these 2 carbon atoms, those 2 p orbitals, can overlap in a side-to-side fashion. And this is why we draw this as a pi bond here, because we have this side-to-side overlap between those p orbitals. But what's important to understand is that this carbon here, which is drawn as a carbocation, okay, is also trigonal planar. It also has an sp2 hybrid, and therefore it also has a p orbital that is unhybridized, and that's what they're showing you here. The only difference with this particular orbital is that it's empty. There are no electrons on it. This is why it has a positive charge. Okay, so they've kind of drawn that here with a positive charge. But what's really important to understand is notice that that p orbital, that empty p orbital, has the exact same side-to-side overlap with the central carbon's unhybridized p orbital. And so there's nothing to say that you couldn't form a pi bond here as well. And this is what resonance structures are trying to depict. And so in this picture C here, what they're really trying to show you is that all 3 of those carbon atoms have p orbitals that can overlap in a pi fashion. And this is why we use these resonance structures to describe the pi bonding in these molecules. At the end of the day, what you end up by forming is you can draw 2 different pictures for this allocation that are identical. And in the one picture we'll call A, you can see that the carbon-carbon pi bond is between the left hand and the central carbon atom. And in what I'll call molecule B here, the pi bond is now between the central carbon atom and the right-hand carbon atom. So which is it? Well, it turns out neither of them are true. It's just that each one of these pictures gives you one particular look at what the overall structure of the molecule looks like. So this is what resonance structures try to do. We try and give you little snapshots of what the overall structure looks like, because it's impossible for us to depict, for example, a bond and a half on a piece of paper. So the first thing to realize is that these different resonance structures that I'm drawing here, so in this particular case, A and B, these resonance structures do not exist. Okay, it's just a way for us to show you what, give you a better picture of what this overall structure of the molecule looks like. And because these 2 pictures don't exist, the molecule does not flip-flop in between A and B, okay? The actual structure of the molecule is what we say is a weighted average of all the different resonance structures. In this particular case, these 2 resonance structures are identical, and so they represent the structure 50% of the time. Because they have the same energy and they're identical, we say that they are degenerate. The best way that I can describe this is that, again, so here's resonance structure A and resonance structure B. I like to use a color analogy. And if resonance structure A was blue and resonance structure B was yellow, again, these 2 resonance structures do not exist. What we have is an amalgamation of all the different resonance structures. Now, the ones that represent the structure more, have a higher percentage, will give you a better look at what the actual structure looks like. In this particular case, we're saying it's 50-50. And so if you were looking at this molecule, this allocation, you wouldn't see it be blue and then yellow and then blue and then yellow. It does not flip-flop in between the different resonance structures. When you would see this particular molecule, it would be green. It's an amalgamation of those different resonance structures. I find that analogy helpful to try and understand what we're talking about when we're talking about resonance structures. So here's this very similar molecule. This is not an allocation, this is an alloanion. So now this carbon doesn't have a positive charge, it's a negative charge because it has this lone pair here. But the structure of this particular alloanion is almost identical to the structure of the allocation. And again, there's a question here. It says, what is the geometry about each carbon atom in this alloanion? It turns out that these 3 carbon atoms are still trigonal planar, even though Vesper theory might tell us otherwise for the carbon bearing the negative charge. And again, the reason why it is still trigonal planar, because it wants to put these p orbitals in perfect alignment, I'll say, to have side-to-side overlap. The big thing about orbitals is overlap in between them. And it will take whatever geometry it needs to, or that it can, in order to maximize the geometry between the different, maximize the overlap between the different orbitals. And the best way of overlapping these p orbitals in a pi fashion is when they are exactly side to side like this. So this carbon atom that bears the lone pair and the formal negative charge, it remains trigonal planar in order to keep its unhybridized p orbital completely overlapped, or with a maximum overlap with the other p orbitals. Okay. So we talked briefly about valence bond theory. Now we're going to talk about the other prevailing bonding theory, and this is what's called molecular orbital theory. And molecular orbital theory is just another way of describing bonding in organic molecules. Now, recall in valence bond theory, or VB theory, remember that we use what we called a localized approach. That is that the bondings were localized in between a couple different atoms. In molecular orbital theory, we extend this idea of bonding over the entire molecule. So that's sort of the subtle difference over this. So again, in order to create molecular orbitals, so remember in valence bond theory, we created these hybrid orbitals, right, by mixing atomic orbitals. Well, we still start with atomic orbitals and we still mix them, except now instead of creating hybrid orbitals, what we're creating are what we call molecular orbitals. And again, as orbitals always describe, they describe the likelihood of finding electrons in a space around, in this case, not an atom, but the space around a molecule, because we're talking about molecular orbitals. And we're going to mix these orbitals in a similar fashion as we would when we would hybridize them in valence bond theory. So molecular orbitals that show continuous electron density in between the atoms are known as bonding molecular orbitals, and molecular orbitals that show zero probability of finding an electron between atoms are known as antibonding molecular orbitals. This basically continues the concept that I was talking about earlier in the previous video about how these particular orbitals overlap. So in this particular case, you can take either hybrid orbitals, or you can even take atomic orbitals in order to create these molecular orbitals. And in this particular case, they've taken these two sp hybrid orbitals. Again, these look very, very similar to p orbitals. And what's important here are usually when we draw molecular orbitals, we have on the two opposing sides, so the left and right hand side, we have either the atomic orbitals or the hybrid orbitals that we are mixing. And then in between them is where we stack, and again, this is an energy scale. So basically it's the y-axis here. So the higher up you go, the higher in energy you are, the less, we'll say, stable those orbitals are. And then what you do is you have your atomic orbitals or hybrid orbitals on either side, and in between them is where you draw out your molecular orbitals, the bonding and the anti-bonding molecular orbitals. So when you take these two hybrids here, so what they're really showing you is that we're taking this sp and this sp orbital, and we're bringing them together in a head-on fashion. So this lobe is going to interact with this lobe, and that's what they've drawn here. Again, they haven't included the nuclei in these, but what they have included is the symbol of the element. So what we're doing is we're taking an sp hybrid from carbon and an sp hybrid from oxygen. But where they put the chemical symbol of the two different elements or the atoms is where the nuclei are. And again, the important thing here to understand is that notice that there is a continuous overlap between the carbon and oxygen here, shown here by this constructive interference between orbitals. And if you have continuous electron density, if you will, or where you have constructive interference between these orbitals, this is a bonding orbital. So this is bonding. And anytime you can have bonding, of course, you can have an anti-bonding orbital. And this is what they're showing you here, okay? This is a better description of what the anti-bonding orbital looks like, but essentially what you're doing here, again, is you're taking what are we doing here? Here we go. We're taking two either hybrid orbitals or two atomic orbitals, and now the two lobes that are coming together have opposite phases. And so when you add these together, those opposite phases are going to actually shrink. And so what you're getting is something that looks like that. This picture that I've drawn here is literally the exact same as this picture. It's just depicted a little bit differently, okay? And so what's important here is to notice in between the carbon and oxygen nuclei, notice there's an area of, non-continuous electron density, or there's an area where you don't have constructive interference between the orbitals, and this is known as an anti-bond. For every bond, there must always be an anti-bond. And we've seen this before in your first year chemistry. You can always take, two s orbitals, for example. They have the same phase. They will come together in a bonding fashion. You can also take them together with opposite phases, creating an anti-bond. We'll get back to orbitals a little bit later on when we start talking about the reactivity of these different organic molecules. So we're just going to finish now talking about different ways of representing organic structures. Lewis structures are great. However, they do have their drawbacks. One of the drawbacks is that Lewis structures can be time consuming, especially for anything, really, it doesn't take very many atoms for them to get to be time consuming. However, the biggest problem with Lewis structures is that the structures become quickly cluttered, and this obscures some of the key features of the molecule that we want to look at. And the reason why they become cluttered is essentially because of the high number of hydrogen atoms that are on organic molecules, because organic molecules, of course, almost all of them contain hydrogen attached to carbon. And if you have a whole bunch of hydrogen atoms, it really becomes hard to kind of see what the actual skeleton looks like and some of the other specific features of the molecule. So there is sort of an in-between sort of way of drawing these molecules. So we can have Lewis structures, and if we condense down some of the information, or way I like to look at it is how we could pack some information. We call this a condensed structure. And in condensed structures, what we do is we eliminate certain bonds, reducing the amount of clutter. And so interpreting these structures is done with an understanding of basically the valence of each atom, i.e. 4 bonds to carbon, 3 to nitrogen, 2 to oxygen, and 1 to halogen, and the hydrogen atoms. And so couple little things that we do when we do condensed structures. So carbon atoms followed by hydrogen atoms are assumed to be directly bonded. And so instead of explicitly showing all the bonds in between carbon and hydrogen, we just have the atoms drawn directly adjacent to those atoms. And so those bonds are understood to be there. And so then if you know that the number of hydrogen atoms are less than the valence of carbon, then it's assumed that the next atom is bonded to a carbon atom. And then if multiple similar groups attach to a carbon, then these can be listed in parentheses. So as an example, here is a Lewis structure of a particular molecule. And you can see this is not a very large organic molecule, but it becomes very difficult to see just, first of all, how many carbon atoms there are there. You know, it's our eyes quickly just look and we see, oh, there's a whole bunch of hydrogen atoms. For example, the aldehyde functional group might be lost in this. So we can condense this down by drawing it like this. So now you'll notice that what we've done is we've explicitly removed the explicit bonds between carbon and hydrogen. So instead of this group here having 3 hydrogen bonds directly attached to the carbon, we've just drawn this as a CH3, for example. Okay, and this group would be condensed down to a CH2, and this would also be a CH2, and this would be a CH2, and this is a CH2. We can condense that down even more because there are 4 CH2s in a row. We can just write 1 CH2 in brackets and have a subscript 4 after, meaning that there are 4 of these. Okay, and we understand because we're dealing with organic compounds that those carbon atoms in the CH2 are attached to other carbon atoms of CH2 groups. And so on and so forth. When you get down to here, so that's these 2 carbon atoms here, if you actually look at the valencies of those 2 carbon atoms, you'll see that they really only have 3 bonds to it. So then it's understood then that there's going to be there has to be a carbon-carbon bond in between those 2 carbon atoms. If not, then the valencies would not be met for those atoms. I will say that typically, even in condensed structures, we still show multiple bonds in between carbon atoms because it's just much easier to depict that. But again, it can be depicted in different ways. So if you had included those 4 CH2 groups in the condensed form, it would look like this. But again, it just becomes easier and quicker to draw it if you condense them down into some parentheses. There are some common abbreviations, condensed abbreviations for certain functional groups, and you're going to see these a little bit later on, and they're also included in the functional group table that you'll see from in chapter 2. So just as an example, you know, an aromatic ring, a benzene ring, which looks like this. Okay, here is its Lewis structure. This is drawn in a line structure, which we'll talk about in just a minute. Its typical condensed abbreviation is C6H5. It's just a little bit quicker to write C6H5 rather than drawing all of those atoms with alternating double and single bonds and so on and so forth. In order to really understand these condensed structures, it's important that we always remember the normal number of bonds or the valencies of these different atoms. So again, remember we talked about this where carbon likes to form 4 bonds, and you can see 4 bonds here. And underneath it, or above it, I guess, I'll write the number of lone pairs. So this will be lone pairs that. So if carbon has 4 bonds to it, it should have 0 lone pairs. Nitrogen and phosphorus typically like to form 3 bonds with 1 lone pair. Okay. And then when we get to oxygen and sulfur, typically 2 bonds with 2 lone pairs. And then when you get to the halogens, they typically like to form 1 bond. So that's this number here. And they like to form 3 lone pairs, and so on and so forth. And this is a convention that you're going to want to get familiar with by just looking at these different organic compounds, and this will become second nature. Now, by far the best way that we use to describe or to draw these different organic structures is through line structures. Line structures, again, we remove even more explicit information. However, it becomes much quicker to draw them. And it also dramatically reduces the amount of clutter. And so therefore it can emphasize the shape and the different functional groups of the organic molecule. And that's ultimately what we want to know when we're looking at these molecules. We just need to learn a few of the conventions with line structures. So we literally remove carbon atoms and hydrogen. We don't remove them, but we remove the letters that represent these atoms from the structure. And we literally just draw lines. And so it's understood that all bonds between atoms are drawn as solid lines in a zigzag pattern, okay? And that the carbon atoms are generally, because they're not generally explicitly drawn, it's understood then that the point of these zigzags, these vertices, or each vertex, the end of lines and bond transitions are understood to represent carbon atoms. So this is a great example here. Notice that we just have basically some zigzag lines here. However, we can look at this and notice there's no clutter in terms of the hydrogen atoms or these letters C's are drawn here. And so what we need to do is understand where those carbon atoms are. So the end of lines represent carbon atoms. So there's 2 carbon atoms there. Each point or vertex in your zigzag represents a carbon atom. So there's 3 more there. And then at each bond transition, so you can see at the very end here that we are transitioning from single to triple bonds. And so there's a carbon atom there and a carbon atom here. So in this particular structure, we have 7 different carbon atoms, which I've highlighted in little green circles there. It's also understood because we know the typical valence of carbon. So for example, if we look at this carbon on the end here, that carbon has only 1 bond right now to another carbon atom. Therefore, it must be attached to 3 hydrogen atoms, which we have not explicitly shown. And that's the nature of the way we draw line structures. So we typically remove that information. So just because you don't see those hydrogen atoms does not mean that they're not there, they're just not drawn. We will draw all heteroatoms. So although we've removed the actual physical C's and H's in our structure, any heteroatom, so anything other than carbon and hydrogen, we do explicitly draw. So if you see an oxygen or nitrogen, you'll see those letters actually drawn. Hydrogen atoms are omitted when they're attached to carbon typically. However, they are always included when they are attached to a heteroatom. And oftentimes you'll see this drawn in either like these slides or in journals or in textbooks. The lone pairs will often be omitted. However, I think it's really important that you guys understand that they're still there, and so you're going to want to put them down. So as an example, we have a line structure here of this particular molecule, but if you've included the lone pairs, it would look like this. And I think at this stage, it's important that you include those lone pairs because as we'll see later on, it's these lone pairs that will be involved oftentimes in the reactivity of these molecules. Understand that we don't usually typically draw everything strictly in a condensed form or strictly in a line form. There's a lot of variation in there and mixing and matching depending on how we want to highlight the molecule. As an example, you can see in this structure here that the hydrogen atoms are of course drawn explicitly to the heteroatoms nitrogen and oxygen, as it should be. But notice down here that they've actually included the physical letter C with the 2 hydrogen atoms attached to it. Why have they done that? Well, perhaps in this particular case, they want to highlight that carbon atom and hydrogen atoms. So you'll see a little bit of a mix and match sometimes in between this, depending on what they highlight. Maybe that's the area of reactivity, and so they really want to highlight that carbon and those 2 hydrogen atoms attached to it. Okay. The other thing to note here is if you do explicitly draw an atom, like whether it be C or O or something like that, then you must draw the hydrogen atoms attached to it. Okay, so here's another example. You can see here, this first drawing is drawn in just a strict line structure. So this is nice and clean. You can see it's a 6-membered ring. It's got this methyl group coming off of it. That's very easy to see. Don't forget though, at this particular carbon atom, there is a hydrogen atom which they've shown here. So again, if they wanted to highlight that hydrogen atom because it partook in some reactivity, you might actually draw the structure like this just to highlight that hydrogen atom so that you do not forget that it's there. And then finally, we can also include dashes and wedges. Again, this is to show three-dimensionality at these different tetrahedral centers. And so you can see here, for example, in this molecule on the left, that here they've actually shown you where the OH and the hydrogen atom are pointing. So the hydroxy group is understood to be pointed towards us, and the hydrogen atom is pointing away from us. However, if you didn't need to highlight that hydrogen atom, so again, strictly speaking, this hydrogen atom is not usually included in line structures. So if you didn't need to highlight that atom, then you could easily draw the structure like this. Okay, and this is exactly the same thing. Notice here, again, it's a nice clean structure. You've got all your heteroatoms drawn, you've got the carbon chain, I can see that. And this hydroxy group is still understood to be pointed towards us. And because we understand the valency of that carbon atom, that carbon right here has only 3 bonds right now, right? 2 of them in the plane of the screen, 1 of them is pointing towards us. So that must mean then that there's a hydrogen atom there that's not shown and it's pointing away from us because we can only have the 1 dash and then the 1 wedge. So as a very simple, straightforward exercise, it's important that you can go from one structure to another. So taking Lewis structure, for example, and converting them into line structures, or vice versa, taking a line structure and converting it into a Lewis structure. Again, if you look at this first example, this is a really small organic molecule, and already there's a lot of hydrogen atoms there, and it kind of clutters up the structure. It's a little bit hard to see. There's only 3 carbon atoms, and what's the functional group, and so on and so forth. So to convert this into a line structure, we look and we see that there are 3 carbon atoms, and so you just draw this in a zigzag form. So we can start by going like this, and I'm done. There's my 3 carbon atoms. Now I do need to include the heteroatom, which is a nitrogen, so I'm just going to go here. The hydrogen atoms to heteroatoms are included. I've drawn it as a condensed form. So notice that the bonds in between nitrogen and hydrogen are not explicitly shown in the way I've done it. This is a typical way of condensing it down. And this is my structure. I am done. Notice I haven't drawn any of the hydrogen atoms attached to carbon because I don't need to. It's understood that this is a CH3 group and that these 2 are CH2 groups. And you're going to get used to being able to read these structures by just continually looking at them and drawing these as line structures. If we do this last example, we'll see that, again, you know, there's a ring here. The ring's a little bit cluttered. So I'm going to start there, and I know it's a 6-membered ring. I can see those 6 carbon atoms. There's a multiple bond here. The hydrogen atoms to the carbon atoms I'm not going to include. There is a heteroatom here, chlorine atom, so let's include that. And then we do have carbon-oxygen bond, and then there's a methyl group here. So notice that I included the dash to this carbon-oxygen double bond. It was given to me, so I'm just going to include that in here. And you can see very quickly now that doing this line structure, I get a much better sense of what's going on with this molecule. I can now easily see the ketone functional group. I see that I've got this alkene with a halogen chlorine atom attached to it involved in this 6-membered ring. So line structures are something you're just going to need to get used to seeing because we're going to see them everywhere as I'm drawing them, and you'll see them in the text and in the slides as well. And then also get used to the fact that, you know, there will be some aspects of it that are highlighted sometimes or drawn in condensed forms like this NH2 group.
In this video, we're going to talk about functional groups of organic molecules. Why are we concerned about functional groups? And why do we want to, you know, understand functional groups? The reason behind this is because the functional groups essentially dictate the reactivity of molecules. And as you can see here in this slide, basically a lot of different properties are tied to the structure of the molecule. So you can see color, chemical reactivity, mass, interactions with light, solubility, boiling point, and so on and so forth. So if we have an understanding of the functional groups within the molecule, we'll get a better understanding of its properties, such as these here. So one of the nice features of drawing molecules in line structures, as we learned previously, is that it can really help to emphasize the important parts, I'll say, of the molecule. So you've got a couple molecules here drawn, and you can easily see, for example, in this molecule on the left, we can easily see that we have a hydrocarbon unit, and there is a functional group right beside it. So here's the hydrocarbon unit, and then we've got this OH functional group, which we call a hydroxyl group. If we look at the other molecule beside it, we can see that there's a bigger carbon skeleton chain, but there's still a hydrocarbon unit here, and you can see that there are quite a few rings there. We can also see this hydroxyl unit here. We've got another functional group over here, and then there's even more hydrocarbon units. So what we could say with this molecule is that because they both have the hydroxyl functional group, there is a chance, at least, that they might have or share some similar properties. Okay, let's talk a little bit about functional groups and what we exactly mean by functional groups. Hydrocarbon, and a hydrocarbon is nothing more than when you have an organic molecule that only contains carbon and hydrogen, which is why we call it a hydrocarbon. It's the most basic organic compound, and it would also be considered perhaps the most basic functional group. Okay. The thing about hydrocarbons, or alkanes as they're called, is that they only contain carbon-carbon single bonds and carbon-hydrogen single bonds. And these bonds are actually quite strong, and they are difficult to break. And therefore, they're generally unreactive. If you've noticed, when you start looking later on at reactivity of these different molecules, you'll see that the hydrocarbons, there's not a lot of reactions that we can do with them. Definitely not as reactive as other molecules that contain other functional groups. So it's kind of the, as it says here, the hydrocarbon units are therefore generally unreactive, and they're like the primary functional group, and they act as basically a scaffold that you basically add other functional groups on, which will change the properties and the reactivity of the molecules, and we'll look at that shortly. So functional groups are generally are molecules that contain certain reactive bonds and or non-bonded electrons or lone pairs. So I just want to define a couple things. When we talk about hydrocarbons, we can essentially have two different types of hydrocarbons, those that are what we call saturated and those that are unsaturated. As it says here, saturated structures are molecules that have a maximum number of hydrogen atoms allowed by the valence of the other atoms. So they're essentially saturated with hydrogen atoms. That's where the term comes from. When we talk about unsaturated molecule, we're talking about molecules that either have multiple bonds, double or triple bonds, and also or rings. So in this example that we have here, this first molecule is saturated because there are essentially no rings and there's essentially no multiple bonds. The second molecule here, we would call this molecule unsaturated because it has that carbon-carbon double bond. And this third molecule here would also be considered unsaturated because it contains a ring. The key concept here to understand is that an unsaturation can be either a multiple bond or could be a ring. Okay, so most organic molecules do contain functional groups. And these are groups of one or more atoms whose structure confers a particular pattern of reactivity. That's basically the definition of a functional group. Why do we care about this? Because functional groups tend to have predictable reactivities. And so if we can understand what functional groups these molecules contain, then we can have a better way of predicting, perhaps, its reactivity. So there's two main features of functional groups. Well, it's not exclusive, but they can contain multiple bonds, so pi bonds, or heteroatoms, or both. So let's look at pi bonds here. We have 4 examples of molecules, and all 4 of these have some form of multiple bond. And so the alkanes, as I said, these are the saturated hydrocarbons. And so those are, like I said, the sort of the lowest level, or the very simplest functional group. Some might even consider it not a functional group, but we'll just call it the simplest functional group that there is, the simplest organic molecules, nothing but carbon-carbon and carbon-hydrogen single bonds. If you introduce carbon-carbon double bonds, these are known as the alkenes. And so we have an example of an alkene right here, as it says. And so, again, if we understand how alkenes behave, then we can have better predictive powers of the reactivity of this particular molecule. We could also have alkynes, which are a functional group where we have carbon-carbon triple bonds, and we have an example of that up here. And then finally, we can also have aromatics or aromatic molecules. This is a special type of ring. You've probably heard of this as benzene, and these are molecules that are 6-membered rings. Well, not necessarily 6-membered rings, but they're ring structures that have an alternating single and double bonds in them. And so, for example, in this molecule here, which they've highlighted in red, there's an aromatic ring which is fused to a non-aromatic ring. So understand that molecules, organic molecules, don't have to have just one type of functional group. Oftentimes they contain multiple functional groups. So in this last example, you can see this molecule which contains a ring, and it also has an alkyne and an alkene, shown here and here. So those are just simple functional groups that contain pi bonds. We can also have functional groups that contain heteroatoms, or heteroatoms and pi bonds, and that's what we'll look at here. So recall that a heteroatom is nothing more than an atom that is anything other than carbon and hydrogen. So oxygen, nitrogen, and so on and so forth. So if you look at some of these examples here, we have a hydroxyl group. You guys will also know this as an alcohol. We have an amine here, so the heteroatom for an amine is nitrogen. We have a nitro group, which we'll see more of as well. This molecule contains a heteroatom and multiple bonds, even though they're not shown here. This nitro functional group is represented in its condensed form at the moment. And at the bottom here, we have a few other functional groups, such as an amide, a nitrile, and an anhydride. And you can see they all contain heteroatoms, whether it be oxygen or nitrogen or both. The other thing to consider is that these heteroatoms often also have unpaired electrons, or lone pairs. They're not drawn in these molecules. Let me just include a few here, but clearly this oxygen would have a couple lone pairs, and this nitrogen would have a lone pair, this nitrogen here, and so on and so forth. Again, I want you to get in the habit of putting in your lone pairs so that you do not forget that they are there. Okay, as it says here, and as I've already mentioned, that organic molecules often contain more than one functional group, and so they will exhibit behaviors that can be attributed to all of those groups. Which is why, like I said, we try and tend to understand how these functional groups behave so we can have better predictive properties, especially when it comes down to reactivity. And so understanding how the reactivity patterns are tied to a molecule structure, we can make predictions on what kind of reactions that these molecules will undergo. So again, just a couple examples here of the molecules, and you can see one is a steroid here on the right, some type of steroid. You can see it's got a lot of different functional groups, a ketone, an aromatic ring, a hydroxyl group. And this other one on the left here also has quite a few functional groups for a rather small molecule. I will just say at this point that you're just going to want to try and get used to some of these more common functional groups and start learning their names and also their structures. And we'll continue to do this as we go along. In this video, we're going to be talking about intermolecular forces and how they pertain to the properties of organic molecules. So effectively, organic molecules are clouds of electrons. And it's essentially this distribution of these electrons around the molecule which give rise to these intermolecular forces or forces in between organic molecules. So when organic molecules are close enough to each other, they'll exhibit attractive forces towards each other. And if these are collectively strong enough, this will give rise to the different properties such as melting point, boiling point, and solubility. And we'll look at some examples of this in a few minutes. There's effectively 4 different types of intermolecular forces that we're going to be looking at today. Electrostatics, dipole-dipole interactions, hydrogen bonding, and London forces. Hopefully these are all familiar to you from your previous chemistry courses. So intermolecular forces result from essentially charge interactions, right? We know that opposite charges are attractive forces and similar charges will repel each other. And so the distribution of electrons within molecules is not always perfectly even. We have areas of higher electron density and we have areas of lower electron density. And we can map this using what we call electrostatic potential maps. And you can see an example of this on the side here, and we also color code this. So effectively, if you look at this molecule of formaldehyde, that area in red is representing, of course, a higher electron density, and the areas in blue are representing areas of lower electron density. So effectively, you have positive regions of molecules which are attracted to negative regions of neighboring molecules and vice versa. The strength of these interactions, of course, will depend on the number and the size of the charges involved. And of course, the larger the charges and the more we have of these interactions, then the stronger that these forces will become. And if you have, fewer interactions, then of course you have weaker forces in between these molecules. Let's look at, let's go through these 4 different intermolecular forces in just a little bit greater detail. We'll start with electrostatic interactions. And these are interactions that take place between functional groups that have a full formal charge. So if you look at these 2 examples here, we have a carboxylate and an ammonium ion, and both of them have full formal charges here. And so these interactions are by far the strongest intermolecular force that we'll be looking at, and they result in ionic structures. Another great example of this would be if you were to think of just a common table salt, which is an interaction between sodium cations and chloride anions. Okay, let's look at dipole-dipole interactions. These dipole-dipole interactions are effectively interactions between different dipoles. Okay, so it's the positive end of one dipole which is being attracted to the negative end of another dipole. What are dipoles? Dipoles are effectively created when you have an electronegativity difference between atoms within a functional group. If you look at this molecule here, we have a ketone functional group, and you'll notice that we have a delta minus, so there's that Greek symbol delta, which we use to depict a partial negative charge. So delta is just meaning a small or partial charge. And then we also have a delta plus, which is representing a small or partial positive charge. And effectively, there's an electronegativity difference between this carbon and oxygen, and it creates this little dipole, partial negative charge on oxygen, partial positive charge on carbon. Don't get this confused with the electrostatic interactions, because we don't have full charges here. We have partial charges, which creates a small dipole. Or, you know, you could look at it as sort of a vector, which is why they have an arrow drawn there. So when these molecules come together, when we have these dipole-dipole interactions, they're going to try and line up so that all the negative ends of the dipole are interacting with a blue, or I should say a positive end of a different dipole. And so if we look at this particular map, we've got a whole bunch of formaldehyde molecules. And for example, you can see here, we've got this negative end of the dipole, which is of course depicted in this density map, which is red. And you can see that it's kind of approaching the blue end here, which is of course the positive end of a dipole. And if you look at, you know, this entire map here, you can see how they're kind of all arranging themselves, where, you know, negative is being attracted to positive and positive is being attracted to negative, and so on and so forth. Okay. So let's now talk about hydrogen bonding. And hydrogen bonding should be familiar to you. And hydrogen bonding is nothing more than a special kind of dipole-dipole interaction. And it is indeed important to understand the difference between hydrogen bonding and regular dipole-dipole interactions, because it does have a significant effect on the properties of molecules. So there's two parts to a hydrogen bond. You need a hydrogen bond donor, and you need a hydrogen bond acceptor. So the requirements here are for the hydrogen bond donor must have a hydrogen atom which is attached to a small, highly electronegative atom, such as oxygen, nitrogen, or fluorine, for example. So in this example here, you can see that we have this alcohol molecule, and it's got this hydrogen attached to an oxygen atom. So there's our hydrogen bond donor. Now, in order to have a hydrogen bond acceptor, all you need here is a small, highly electronegative atom, such as oxygen, nitrogen, or fluorine. And so you can see in this particular example that we have these two molecules. It's the same molecule. They're actually hydrogen bonding with each other. And so one molecule is acting as the hydrogen bond donor, and the other one is acting as the acceptor. The hydrogen bond itself is depicted as that sort of blue dashed line, and it's in between that hydrogen atom and of the donor to the electronegative atom of the acceptor. Hydrogen bonds are really important in organic chemistry. As I said, if you look at these two different functional groups here, we have a hydroxyl group or alcohols, and the amines here. They definitely have the requirements in order to partake in hydrogen bonds. And so we can explain and understand the properties of these molecules based on these hydrogen bonds that they can form. All right, and the last intermolecular force we're going to look at are what we call London dispersion forces. These are attractive interactions that exist between molecules in close proximity. You have to understand that every single molecule will have London dispersion forces. And the other thing you have to understand is that they are extremely weak forces. However, they do add up. And so in this particular case, size does matter. Where does this come from? Well, again, the electrons around molecules are not perfectly evenly distributed around a molecule. And so at any given moment, you might have, a few more electrons on one side of a molecule than another, and that creates a temporary dipole. So you have like sort of a little bit of a negative charge on one end of the molecule, and another little bit of a positive charge on the other end. And that's just sort of a temporary thing. And this is constantly fluctuating. However, when these molecules get close to each other, these very small but temporary dipoles can have attractive forces to each other. And this is what we call these London dispersion forces. So let's see how these intermolecular forces will play out in terms of physical properties. And specifically talking here about melting or boiling points here for molecules. So if the structure of the organic molecule determines what kind of intermolecular force we're dealing with, then of course, those intermolecular forces will also tell us how or at least give us a good indication of the physical properties of the particular molecule. So we want to be able to investigate these different molecular structures so that we can get a better idea of their physical properties. So essentially, the more intermolecular forces that are at play, they'll be that much more difficult to separate the molecules from each other, and therefore that would have an effect on its melting point and or boiling point. One way to think about this is that when you're melting something or when you're boiling something, what you're effectively doing is you're providing energy into the molecule in order to separate the molecules. So the question is, if they're being bound very tightly, it'll require more energy, and therefore they'll have an elevated boiling or melting point. If it's easier to do that, then their melting and boiling point will be lower. Okay, so let's look at we'll look at these different properties, and we'll also look at the different intermolecular forces and how they play out in this. So we've got a table here of 4 different molecules. I'm just going to number them so you can follow along which ones I'm talking about. If we just start with the first two, if we look at molecules 1 and 2, and if you look at their melting points, or you can look at the boiling points, it doesn't really matter. You can see that when we go from molecule 1 to 2, that in terms of the physical property, we have an increase in melting point or an increase in boiling point. Now, why is that? Well, with these hydrocarbons, the only real intermolecular force that we're dealing with are London dispersion forces. And as I said before, they're quite weak, but they do add up significantly. So basically, the more London dispersive forces that you can have, the higher the melting or boiling point will be. And so in the case of molecules 1 and 2, molecule 2 is just literally bigger, and therefore it has more London dispersion forces, and therefore it should have a higher melting point or boiling point, and that's exactly what we see. If you were to compare molecules 2 and 3 now, and if you actually count the number of carbon atoms and hydrogen atoms, you should see that they are identical. They both have the same number of carbon atoms and the same number of hydrogen atoms. However, notice that there is there's a difference in between their melting point and their boiling point. And in this case here, molecule 2 has a higher melting and boiling point than molecule 3. And why is that if they're the exact same size? Well, here it comes down to shape. And as the little word bubbles are saying here, basically molecule 3 is more branched, and therefore it has lower surface area. And what that means is the more surface area it has, the less likely it can actually create more of these London dispersion forces. Or said differently, molecule 2 can actually create more London dispersion forces because it has more surface area. And then if we just look at number 4, molecule 4, you'll see that it has the highest melting point and the highest boiling point of all 4 of these molecules. And what's the difference? Well, the only difference with this one here, of course, is that it's actually in a ring. And it turns out that most rings can actually stack very well. And what we mean by stack is that they can kind of approach each other in a kind of a very regular way. So imagine like plates, for example, kind of nestled into each other, and you can form a very large stack. And because they can stack so well, they have, again, an increased amount of, in this case, London dispersion forces, which will, of course, increase their melting point and their boiling point. So for simple things like hydrocarbons, you're really just looking at the size, the amount of branching, and the possibility of rings in order to predict the relative melting and boiling points. If we look now at molecules where we can start increasing the type of intermolecular forces in between them, let's take a look at these 3 molecules. So again, I will number them. So molecule 1, of course, has the only force at play here for molecule 1 would be London dispersion forces. When you go to molecule 2, what they've done is they've added an oxygen atom into this molecule. So as soon as we do that, we now have the potential, well, we don't have the potential, we have actually a permanent dipole set up here. And so now we're getting into dipole-dipole interactions. And dipole-dipole interactions are definitely stronger than London dispersion forces. And you can see that played out by the boiling point. You go from a boiling point of 36 degrees up to 101 degrees. When you go to molecule 3, we still have a dipole set up here, a permanent dipole between the oxygen and the carbon atom, but also notice now we have a hydrogen atom attached to that oxygen, and this basically allows us now to do hydrogen bonding. And because it can do the hydrogen bonding, you can see that we increase the boiling point of this molecule even higher. So in terms of dipole-dipole interactions, the hydrogen bonds can also have a very significant effect on the boiling points or melting points. And then finally, if we look at how this plays out in terms of electrostatics, here we've got 4 molecules. Let me again label these. So if we start at the top with molecule 1, this molecule has essentially the capabilities of doing only dipole-dipole interactions, and it has, a melting point of minus 125 or boiling point of 21. If you go to molecule 2 now, we still have a permanent dipole set up here, but again, because of that hydroxyl functional group or the alcohol functional group, we have the capabilities of doing hydrogen bonding. And so we should see an increase in the physical property in the melting point or boiling point. And that's what we see here. If you go to molecule 3, what we're doing now is we still have the capabilities of doing hydrogen bonding. So we still have this hydroxyl functional group here. We also have this very nice, strong permanent dipole as well. So here we're kind of stacking several different intermolecular forces. This molecule is quite polar. So we're increasing the polarity, which makes it a stronger dipole. And so because we're stacking these intermolecular forces, we should see an increase relative, for example, to molecules 1 and 2. Again, notice that these molecules are all relatively the same size. And this is why we're doing this comparison. So with molecule 3, now you can see that we go from a melting point of, say, minus 125 to minus 114. And now this one's actually at 16.2 degrees. So this is a fairly significant increase in its melting point. And then finally, when you get to molecule 4, of course, we now have electrostatic interactions. We have full formal charges on these atoms. This is a salt, and you can see now from the very dramatic increase in melting point that the electrostatics, as we said before, was definitely the strongest of all the intermolecular forces. Okay, so let's just finish off by talking about solubility here. We've been talking about melting point and boiling point, but we can also talk about solubility. And when we're talking about solubility, we need to also talk about the intermolecular forces between the solvent. This is the liquid that you're using in order to dissolve something, the solute. Okay, so we're really looking at the intermolecular force in between the solvent molecules and the molecules of the solute, the stuff that's actually being dissolved. We can classify, in a general sense, organic solvents into sort of 3 categories or families, and these are listed here. So we have polar protic solvents. These are polar solvents that are able to also act as hydrogen bond donors, so that's important. We can also have polar aprotic solvents. These are also polar solvents. However, they do not have the capability of being hydrogen bond donors. They can, however, act as hydrogen bond acceptors. And then finally, we have what we just call non-polar solvents. And this is solvents, and basically the only intermolecular force at play here would be London dispersion forces. You might have heard this adage before, but the general rule of thumb when it comes to solubility is that likes dissolve likes. So if you have something polar, you're going to want to use a polar solvent. If you have something that's non-polar, you'll want to use a non-polar solvent to dissolve it. That's a good general rule. However, It's nothing more than just a general rule. So this is just a very quick table to show you some of the different type of organic solvents we talked about. So at the bottom here of this table, these molecules down here, these molecules are effectively non-polar solvents. There's a lot of hydrocarbon units there. For all intents and purposes, they're not very polar. Then if we go to these second row here from the bottom, these are we'd probably term polar solvents. They're just they're more polar than the non-polar solvents, obviously, but they do not have the capabilities of acting as hydrogen bond donors. And then the last two categories here are the polar aprotic and polar protic solvents. And effectively, the only difference between these two types of solvents is whether or not you have a hydrogen atom attached to a small, highly electronegative atom, such as oxygen or nitrogen, that type of thing. So if you look at the polar protic solvents, water, methanol, ethanol, you can see that they all have at least one hydrogen atom that is attached to a small electronegative atom. The polar aprotic solvents, while they are polar, they don't have a hydrogen atom attached to an oxygen atom or a nitrogen atom or a fluorine, for example. And so this is how we categorize these different solvents. Now, water is a very highly polar solvent, and it's also able to do hydrogen bonding. This is the reason why water has such a high boiling point for such a small molecule. And it presents an interesting situation for organic compounds because essentially there are some organic compounds which are soluble in water, but a lot of them are not. And it's because we have to do this interplay between the amount of hydrophobic and the amount of hydrophilic parts to these organic molecules. And so nonpolar molecules or portions of molecules we term as hydrophobic, which means water-fearing. So again, water being polar, anything non-polar is going to be hydrophobic. Oil and water is essentially what we're talking about here. If you have a lot of polar groups, especially polar groups that can do hydrogen bonding, for example, on your organic molecule, then they're going to be what we term as hydrophilic, water-loving, and they're going to definitely be more water-soluble the more of these hydrophilic groups that they have. So finally, just to finish this off here, the degree to which an organic compound dissolves in water is governed basically by the proportion of hydrophobic and hydrophilic regions, right? So if you just look at this, this little, these three examples here, if you look at the smallest molecule here, the hydrophobic region, so that's this hydrocarbon unit right here, and the polar group here, they're kind of, equally, they represent about equal portion of the molecule. So this particular molecule is miscible in water, meaning that you can dissolve it. This is nothing more than ethanol. It is soluble in water because basically the ratio of hydrophobic and hydrophilic is good enough for it to be able to dissolve in water. If you go to the second molecule here, you can see that there's a much larger hydrocarbon unit attached to that polar alcohol functional group, that hydroxyl group. And even though that is polar and can form hydrogen bonds, there's a much larger hydrophobic area now. And so it just basically, that's helping it reduce its solubility in water. And then if you go to the third entry here, what we're seeing is we still have that larger hydrocarbon unit, but now what we've done is we've made this molecule more polar. It's a different functional group. This is carboxylic acid. And because it's a more polar functional group, that's helping to offset, if you will, the larger hydrophobic region. And so you can see that it increases its solubility in the water because of that extra polarity. Okay, and then finally, again, as we saw before with the London dispersion forces in hydrocarbons, whether or not you have branching or less branching in these molecules can also affect its solubility in water. So if we look at these two different examples here, we have these two alcohols, and effectively they have the same number of carbon atoms. However, you can see in the first example, the carbon chain is essentially linear, and in the second example, the carbon chain is actually branched. You can see that the branched molecule, molecule 2, is more soluble, it's miscible with water. And the reason for this is because it is branched, and it basically makes it smaller, more compact. And so that means that the surrounding water molecules are better able to do their hydrogen bonding with themselves and solubilize this particular molecule. Okay, so that's all we're going to really talk about in terms of the about these physical properties. Essentially, the take-home message here is that these physical properties, solubility or melting point or boiling point, are dictated by the type of intermolecular forces in between these molecules, and hopefully you get a better sense of what these intermolecular forces are, and how they, pertain to the different properties of these molecules. In this lecture, we're going to talk about the general aspects of organic nomenclature. The first few slides that we have here are a list of different functional groups, and these are the more common organic functional groups that you'll need to be familiar with in this course. So basically, it's sort of set up as a table. On the right-hand side here, sorry, on the left-hand side, you'll have the structure of the. So you can see here under structure, I've got the expanded version of what that functional group looks like. Over to the right, we have what this particular functional group would look like in a condensed form. So you can get used to seeing it drawn sometimes in condensed form. And then the next two columns are its name and the suffix that are used for nomenclature purposes, which we'll talk about in a few minutes. So I'm not going to go through every single one. It is there for your reference. Let's talk about organic nomenclature. We use a system that's been set up by the IUPAC for the nomenclature. And in general, there are four main parts or four fields to a name of an organic molecule. There's the first field, which will name and position any substituents. We have the second field, which refers to the compound root, typically the longest carbon chain or the biggest ring. We have a third field, which is the saturation index, or sometimes it's also called an unsaturation index. It's basically an indication of whether or not you only have single bonds or if you have any type of multiple bonds in your organic molecule. And the fourth field defines the principal functional group. And again, we'll talk about each one of these in turn. We're going to start with the compound root. So this is the second field, because the compound root will appear in every single organic name. So the compound root is basically based on the number of carbon atoms in the longest continuous chain or ring. And for this particular course, we only need to know the first 10. So you can see this table here, and effectively the root word is tied to the number of different carbon atoms. So for example, if your organic compound only contained one carbon, the root would be meth. If it contained 2 carbons, the root would be eth. And if it had 3, it would be prop, and so on and so forth. They have numbering for any number of different carbon atoms. We're going to stop at 10. Most of these should be intuitive. So for example, we know that a hexagon has 6 sides or 6 points to it. And so hex means 6 carbon atoms, and so on and so forth. If you put the word cyclo before the root, then we are talking about a ring. So for example, if I was talking about cyclobutane, the but is telling me that there's 4 carbons, but because the word cyclo is before it, then I am referring, of course, then to a 4-membered ring. So this, for example. Okay. Next, we're going to go on to the third field, which is the saturation index. The saturation index, like I said, indicates whether there are only carbon-carbon single bonds or whether if there are any carbon-carbon double or triple bonds. Again, all organic compounds will contain this third field in their name. So at the very least, your compound name, your organic name should always have the second field and the third field present. So whenever you only have carbon-carbon single bonds, the saturation index in this particular case will end in ane. So this is a simple example here. We have the organic nomenclature of hexane. So hex here is referring to the compound root. So it's telling me that it is 6 carbons long. And the fact that I have an A here is telling me that they are all carbon-carbon single bonds. So from this particular organic name, I can draw the structure of this. And it would be simply me drawing 6 carbon atoms. So I have 1, 2, 3, 4, 5, 6. They're all carbon-carbon single bonds. I'm drawing this in a line structure, so I haven't drawn any letter C or any of the hydrogen atoms attached to it. So this is very simple. It's a very simple name for a simple organic molecule. Let's make this molecule just slightly a little bit more complicated, and let's introduce a carbon-carbon double bond into it. And so you can see we now have this new name, which is called hexene. And you'll also notice there's a 1 there. I'll talk about this in just a minute. So whenever you're trying to interpret a name and draw its structure, I would highly suggest that you start by looking for the root so that you know how many carbon atoms there are. And so I see hex here, so I know that I'm dealing with 6 carbon atoms. So I can start with hex and draw my 6 carbon atoms. There's my 6 carbon atoms. Now I notice in this name that I have an E, not an A. It's not an ane, it's an ene. And that E is telling me, this is 1 letter difference, yes, but this ene is telling me that I have a carbon-carbon double bond. The question is, where does that carbon-carbon double bond appear? Well, that's what the number refers to. So it doesn't matter if you want to read this from left to right or from right to left, as long as you're just consistent with your numbering within your organic name. So let's, for example, we'll call the left-hand carbon carbon 1, and we'll read from there. And so that's telling me that when I see a 1, so for 1 hexene, it's telling me that the carbon-carbon double bond starts at carbon 1 and obviously goes to carbon 2. So I can now include my carbon-carbon double bond. And so this is what the structure of 1 hexene would look like. Now I just want to address, you'll notice that there's also another name in parentheses there where it says hex 1-ene. Both of these forms are correct for this particular structure. Why do we move it? Why is that 1 in a different position? Well, when we're dealing with simple organic names, sometimes, and again, this is dependent on the journal or the textbook that you're looking at, but sometimes the locator for the multiple bonds, so in this case, the double bond, will be put out in front of the root word. So in this case, hex. And the reason why they've moved the 1 to the front of the name is that it actually it's easier to pronounce. It's easier to say 1 hexene rather than hex 1-ene, okay? However, if you want to be, a stickler with the rules, it's always best to have the locator put directly in front of whatever field it's referring to. So this is the proper IUPAC method of doing it. However, just be aware that some textbooks or journals or whatever will also put that locator for the saturation index in front of the root, okay? So let's continue here. Let's do another example, and you can see here 1 hexine or hex 1-ine. So again, the root here is hex, so I'm going to start by drawing 6 carbon atoms. And then I notice now that I have a Y rather than an E, so I have an ine. And the ines refer to a carbon-carbon triple bond. And again, the locator is telling me where that carbon-carbon triple bond is found. It starts at carbon 1 and obviously goes to carbon 2. And so I would then now be able to put my triple bond here. Now, before we move on, I just want to talk about how when you're also drawing these molecules, we want to try and represent the structure as best we can. And so in this particular case, because I have a carbon-carbon triple bond, and if you recall from the previous in chapter 1, for example, we talked a little bit about geometry of these molecules, and you need to get familiar and used to the idea that when you have triple bonds, that around those central atoms, the molecule is linear. And I'm specifically referring to this carbon atom right here. At the moment, I have it bent, and so I've got these fairly extreme bond angles of about 120 degrees. This bond angle should actually be 180. So I'm just going to clean up the structure and draw it more like what it should be. So there will be carbons 1 and 2, and then I'll go to carbon 3, 4, 5, and 6. And then now I will put in my carbon-carbon triple bond. Okay, and so I will just highlight the carbon atoms. There's one here, one there, one there, one there. So I should still have 1, 2, 3, 4, 5, 6. I do, but now you can see that I'm clearly showing the linear geometry around carbon 2 there. Okay, so the saturation index, you're going to have 3 indicators. It's either an ane, meaning carbon-carbon single bonds, an ene, referring to carbon-carbon double bonds, or an ine, referring to carbon-carbon triple bonds. Okay, so there's a little note here, and it says that whenever a principal functional group is not present in your molecule, so these 3 examples we've looked at, there is no principal functional group, okay? And when that's the case, we need to number the chain to give the multiple bond the lowest number, okay? So for example, if we look at this second one we looked at, notice that we numbered the alkene in this particular case at position 1 and not 6, because we always want to give everything, whether it be a substituent or a principal functional group, or in this case, the saturation index, we always want to give it the lowest number possible, okay? Now, we do this for the multiple bonds when there's no principal functional group present. Now, if there are multiple bonds, or more than one type of multiple bond, we need to add a prefix, you know, as simple as di or tri or tetra, to indicate the number of double or triple bonds in the molecule. And we have to give a locator, a number to indicate all the positions. So let's go through a few more examples here. So here we have a molecule, the name is 1,3-hexadiene, or hexa-1,3-diene. Again, they've just moved those 2 number locators in front of the root. It's just a little bit easier to say it, but both are equally correct. So again, I would start with the root. I have hex, so I know I have 6 carbon atoms. So I'll draw 1, 2, 3, 4, 5, 6. And now, what other information do I have? Notice I have an ene, so I know I have an alkene, but I don't just have 1 because I have a diene. So that prefix di is telling me that I have 2 alkenes, and they are found in the positions 1 and 3. Again, we don't always, we never indicate both positions of the alkene. We just indicate the first carbon of the carbon-carbon double bond, and it's understood that the one adjacent to it or next to it after, in terms of numbering, is where the double bond is. So in this particular case, if I'm numbering from left to right here, so I have 1, 2, 3, 4, 5, and 6, then I know I have a carbon-carbon double bond starting at 1, so that's 1, 1 to 2, and then I also have another carbon-carbon double bond at position 3, and which is obviously going to 4. And so this would be the structure of 1,3-hexadiene or hexa-1,3-diene. Now, you'll also notice that there seems to be this new letter A that has been introduced here, okay? I don't want you to get that confused with the saturation index. This letter A has only been introduced And the only reason is because if you actually ignore the numbers, notice that the next letter after the A is a consonant. And if you didn't put that extra A in there, it would be a little bit more difficult again to say the word, right? It'd be hexadiene. Whereas if you add an A and say hexadiene, it's a little easier to roll off your tongue, so to speak. And so this is why we add this. And this is only whenever we have these prefixes like di or tri or tetra that you might see this new letter A that's been put in there. And again, it's strictly just been put in just so that it's easier to actually pronounce the name of the molecule. Okay, let's look at another example. So we have here 1,5-hexadiene. So again, I'll just draw this over here. I'm going to start with my root, which is hex. And then I can go ahead and put in, so this would be carbon 1. So then I have 2, 3, 4, 5. 5 is right here. And so my other carbon-carbon double bond would start here. You'll notice in this particular example, because it's so symmetrical, I could have numbered it the other way and still have gotten to the same answer. It wouldn't really matter the way I numbered it. However, just be careful that you're always consistent with your numbering when you're doing these molecules. In the next example, what we've done here is we've included a mixture of different type of multiple bonds. So if we look at the name, we have 1-hexene 3-ine. So again, this might be confusing that 1 is actually referring to the alkene, the ene, okay? And the 3 is obviously referring to the ine. Again, I prefer this. They're both correct. I prefer this because it's very clear when you do this that the number 1 is referring to the ene and the number 3 is referring to the ine. I would suggest you pick one method of doing this. I would suggest you choose this method, but I just want you to be aware that you might see it slightly different again in the textbooks and in the journals, which is why I'm bringing this up. So again, in this particular molecule, we have 6 carbon atoms. We have a carbon-carbon double bond in the 1 position, and then we have a carbon-carbon triple bond that starts in the 3 position here. So I'm going to go ahead and draw this. And I am going to make sure I include the correct geometry. So this is carbon 1. So between carbons 1 and 2, I have a carbon-carbon double bond. And I specifically drew the other carbon atoms in a linear fashion because I knew I was going to be drawing a triple bond here. However, so this would be carbon 2, there's carbon 3, there's carbon 4. Carbon 5, and there's carbon 6. Okay, so again, don't be thrown off by the lines, the straight lines or the linear lines when you're doing these carbon-carbon triple bonds. There are in fact carbon atoms at that transition when you go to the end of the triple bond to the next carbon over. Okay. And then finally, here's another example. We have 1-hexene 5-ine. So again, I'll put that over here. So we have a carbon-carbon double bond in between carbons 1 and 2. That's what the 1-ene is referring to. And then the 5-ine. So here I have my molecule. And again, the numbering is 1, 2, 3, 4, 5, and 6. Now, one last thing I just want to point out is you'll notice that a letter E has been dropped. And so I'm just going to scroll back up here. And if you look at this very first example, when we introduce the alkene, notice that it says ene, so it's E-N-E, okay? And you'll notice that down here, for example, down in this example, notice that it's just E-N and there's an E that has been dropped. And again, the reason for this is just for visual sake, whenever the next letter, so I'm skipping the number here, is a vowel, we're including Y's as vowels, So we don't want two vowels to follow each other, so that's why we drop that NE there. We still pronounce it as an ene, so this molecule would be hex 1-ene 5-ine, but we just drop that E whenever there's a vowel that follows it. Okay, so that's saturation index. And now let's look at the first field, which is substituents. So these are structural elements, and oftentimes they will be functional groups, that are not part of the longest carbon chain. They're actually attached to the longest carbon chain. Okay, so the substituents being the first field, they appear first in the name. And just like everything else, they are going to be numbered with respect to their position. Okay. And when it comes time to deciding how you're going to number your chain, there is a priority for this, and the priority starts with principal functional groups. We haven't talked about that yet, but we will soon. If there's no principal functional groups, then what you do is you look at the saturation index in order to give you an indication of what your numbering is going to be. And then if that still is not helpful, then what you'll go to then is looking at your substituents. Okay. So they take the last priority when numbering the main chain. And we'll talk a little bit more about this and look at some examples later. Substituents are always listed when you're writing the name in alphabetical order, and their location is indicated by a number. The numbers will not be in numerical order, of course. The numbers will just be tied to the particular substituents, but the substituents themselves are listed alphabetically. And if you have multiples of a particular substituent, they are all numbered and indicated again, just like we did for the saturation index with a prefix giving you the how many there are. So we're just slowly but surely here building more complicated molecules. So let's look at this example here. So here we have a name 5-chloro-1-hexene, or again, if we put the indicator of the saturation index in front of its actual the field, so in front of field 2, it would actually be 5-chloro-hex-1-ene. So again, first thing you should do is find the longest carbon chain. I can see the root there is hex, so again, I'm dealing with a six carbon chain. So I'll go ahead and, oops. So there's my 6 carbons. And then now I have to, I'm gonna, from this point on, I mean, it just depends on how you decide to number. If you're numbering it from left to right, just be consistent. So I will number this from left to right. So carbon 1 will be on the left-hand side, and then carbon 6 will be the one on the far right. And so what do I know? I know that I have an alkene in the 1 position, so I can include that here. And now notice that I have a chlorine atom, so it's named as a substituent, as a chloro substituent, and it's found in the 5th position. And so now I can include my chlorine, and I'll just include my lone pairs. And so this is the structure of this particular organic molecule known as 5-chloro-1-hexene. Let's look at one last example. This one's just a little bit more complicated, but again, as long as you follow these rules and just be systematic, you can get to the correct answer. So it seems like a big mouthful. And again, this is not a very large molecule. You can see that the molecule name looks very complicated the more stuff you add to it. But ultimately, it's still a fairly simple molecule. So we have here 4,5-dichloro, so 5-fluoro. So that whole unit here, all of this is your first field. This is all describing substituents. Then we have our root, which is hex, and then we have the ene, which is the referring to the saturation index, and that's our second field. So this molecule contains 3 fields, the first 3, 1, 2, and 3. Okay, so again, I'm going to start by drawing the root. The root here is hex, so I'll get another 6 carbon chain. Again, it doesn't matter. I'm just going to start with the saturation index. I can see that it's a 1-ene in this particular case, so then I know that I have a carbon-carbon double bond between carbons 1 and 2. And now I'll deal with the substituents. Again, because I've started my numbering here, 1, I have to always be consistent with everything, substituents, saturation index, and so on and so forth, okay? So what do I have? I have I have a chlorine substituent in the 4 position. I'm just going to erase this to give myself room. So I know I have a chlorine substituent here. However, I also have another chlorine substituent in the 5 position. This is why it's 4,5, and notice it says dichloro, telling me I have 2 chlorines. So I will also include my other chlorine atom in the 5th position here. Okay, and then finally, notice that I also have a fluorine atom in the 5th position. So in fact, actually, I'm just going to erase this and add them both. Got my chlorine and my fluorine. And so there's the structure of this particular molecule. Just following the numbering and the root, and you can get to the final answer. Okay, let's talk now about the 4th field, which we haven't talked about yet, and this is the principal functional field. So the principal functional group will always take the highest priority when you're numbering the main chain if the molecule contains a principal functional group. And not only that, the principal functional groups also have a hierarchy. And this is a modified table. It's not a complete table, but this is a table of principal functional groups that you will need to know for Chemistry 2500. And they are listed in order of highest priority, starting at the top, going down. Okay, so the carboxylic acid has the highest priority, and down here, the amine would have the lowest priority. Okay, you'll also note that there are some functional groups that are not ever considered as a principal functional group. Okay, they're always treated as a substituent, and these include the halogens, ethers, and especially nitro groups. Okay. So the thing to understand with principal functional groups is that they only ever, you can only ever have one principal functional group in a molecule. Okay. This is why we have a priority or a hierarchy of these different principal functional groups. And we'll look at some examples of this as we go along. So the functional group with the highest priority, according to that previous table, is named as the principal functional group. And that's where those suffixes that we saw when I had all those functional groups listed, that's where that'll come in to play. So if you, the principal functional group will dictate how the suffix of the name, and then every other functional group that is of lower priority than the principal functional group will always be named as a substituent, okay? So let's just take a look here at a couple examples. Let's look at this first one. So what do we have here? We have 5-chloro, 1-hexene, 3-ol. And again, the alternative method here of mentioning this or naming this molecule will be 5-chloro-hex, 1-ene, 3-ol. Again, the only thing that's moved here was the number for the saturation index. Okay, what do we, again, how can we start with this molecule? I'd start with the root. We have, again, a 6-carbon atom chain, so I'll start there. Okay, I have an alkene in the 1 position, so this goes from the 1 to 2. I'm just gonna be consistent number from left to right here. What else do we have? Notice we have a substituent. So the substituent, the first field, we have a chlorine atom in the 5 position. So I will put this here. There's my chlorine atom. And then notice the very end of the name ends in ol, okay? And this is referring to an alcohol functional group. And so if we go to our principal functional group priority list, okay, notice we have alcohols, and they're right here, and the suffix is also shown. So that means that this molecule gets named as literally an alcohol because the principal functional group of this molecule is an alcohol. Okay, notice that the halogen, so the chlorine atom, is not named as a principal functional group because it is one of these functional groups that is never named as a principal functional group. So let's include our alcohol now. And our alcohol is found in the 3 position. Notice there's that 3 directly in front of the suffix of that, of the alcohol. So I'm numbering from left to right, so it's 1, 2. So our alcohol here is placed in position 3. Okay. Now this is important because I cannot number, once I've started my numbering, notice that I cannot number this molecule from right to left, because my alcohol functional group then would be found in position 4. And again, whenever you're numbering these, you always want to have your, if you have a principal functional group, you always want to give it the lowest number possible. So by numbering from left to right, I give it position 3. If I number it from right to left, I would be in position 4. And so 3 is lower than 4, and this is why I'm numbering this way. Okay, let's look at this next molecule. 2-chloro-5-hexene-1-ol. So again, I have the root of 6. Draw this over here. Okay, I have an alkene in the 5 position. Okay, I'm just going to change things up. I'm going to call this carbon here as carbon 1. So I'm actually starting my numbering from right to left. It doesn't matter how I start this. I'm basically just flipping the molecule around. The key is being consistent. Okay, so the right-hand carbon is carbon 1, and now the left-hand carbon is carbon 6. So my alkene starts from carbon 5 and goes from carbon 5 and goes to carbon 6. I have a chlorine atom in the 2 position. Okay. And what else do I have? I have an alcohol in the 1 position. So this is carbon 1, so now I can draw my alcohol. And so this is the structure of this molecule, okay? Now, I want you to look closely at the last 2 examples that we did, and I want you to see that the only difference between these 2 molecules is literally the position of the alcohol. But I also want you to note how it changed the numbering, okay? So in the first example, this was carbon 1, 2, and 3, and this was 4, and that was 5, and this was 6. Okay. In the second example, we actually reverse the numbering. And this is solely due to the position of my principal functional group. Again, the principal functional group must be given the smallest number possible. So in the second example, the way it's drawn here, I want to give that carbon that the alcohol is attached to as position 1, not position 6. Okay. Now let's look at an example now where we can have multiple different functional groups, and we'll have to use a hierarchy of principal functional groups. So this molecule is 2-chloro-4-hydroxy-5-hexene-al, okay? And I want you to notice the very end of that molecule, the name, it's an Al, not Ol. So, you got to be careful of your letters. One different letter change can actually have a very big impact on the name of your molecule. And if we go to our list of functional groups here, you can see that al is the suffix that we use for aldehydes, okay? And notice here that aldehydes have a higher priority than alcohols. So if you have a molecule, and that's the example that we're looking at right now, that contains both an aldehyde and an alcohol, it's not going to be named as an alcohol, it's going to be named as an aldehyde because that functional group has a higher priority. So it will be named as the principal functional group. Okay, so let's go through this here. Again, I have a 6-carbon chain. So I'm going to start by drawing my 6 carbon atoms. I have an alkene in the 5 position. So I'll call that carbon 5, and now I'm going to be consistent. Okay, I have, what are my substituents? I have a 2-chloro, so I have a chlorine atom in the 2 position. So here's my carbon 2. And then I also have a hydroxy group. What is a hydroxy group? Well, it's an alcohol. But notice that it's named differently because when it's a principal functional group, it's named as an ol, but when it's named as a substituent, it's named as a hydroxy group. okay? And it's found in the 4 position, 2, 3, 4. So my hydroxy is found right here, okay? And then finally, notice that I have al, and notice that there's no number there, okay? That's because it's found at position 1, and I'll talk about that in a minute. So I literally have an aldehyde in position 1. So if we look at the numbering that I was using, that was the number that I was using, okay? Now, there's really no problem if you would have written 5-hexene 1-al. That 1, however, is redundant, okay? And it's redundant in this case because aldehydes, and this is what this note is on the side here, that there's no number is necessary for a principal functional group that must be terminal because they include the first carbon atom of the main chain. What we're saying is you cannot have an aldehyde part of the main chain found other than on the ends, okay? Either carbon 1 or carbon 6 in this case, for example. However, if it is the principal functional group and it must have the lowest number, it must be found at carbon 1. And this is why that 1 has not been included in front of the al, okay? Now, this is only for functional groups that must be terminal. Okay, they're not all like that. The alcohol, for example, can be found at different positions. And so that's why when in the previous example, we actually had to give a number in front of the all. Okay. Okay, let's talk a little bit about formatting. Okay, so if there's any stereochemistry, and we haven't talked about this yet, but this will eventually get included into our nomenclature. So if you do have any stereochemistry like cis or trans or R or S, these are typically placed at the very front of the name. And then if you're, writing this out with a processor or something like that, it'll be italicized. So you can see here, for example, in this particular name, the stereochemistry trans is put in right out in front. So it's actually in front of the first field, so to speak, okay? Other things, numbers and letters are always separated by hyphens. So again, if you look at this example here, this first example, notice that every single, when there's a the separation between a number and a letter, there's always a hyphen there, okay? And then if you have consecutive numbers, they are separated by commas, okay? So you can see there in 3, 4, there's a comma in between 3 and 4. Okay, so it's commas in between numbers and it's hyphens in between numbers and letters. Substituents are always listed alphabetically. If we go back to some example, I never really brought that up here. So for example, in this last one that we looked at just before here, we had 2 substituents. We had a chlorine and we had a hydroxy. And notice that we listed the chloro before the hydroxy because C comes before H alphabetically. So just need to be aware of that when you're listing your substituents. Now, speaking of alphabetical, there's a couple of caveats that you need to consider when you're listing things alphabetically. Prefixes such as di, tri, tetra, and all that stuff, they are not considered part of listing things alphabetically. Okay, so you just basically ignore the prefixes. You also ignore any words that are italicized or letters that are italicized, such as sec or s or tert or the italicized t for some of these other groups here as s-butyl and tert-butyl. Okay, so some examples here. So if you have 4,4-dichloro, the alphabetical letter here is C, okay, not D because the di is not included. If you have 2,2,6-tribromo, again, the prefix tri is not included, so this would be a B alphabetically. We're going to be looking at this in just a moment, but when you have some different other alkyl groups, there's some special ones that have special names. So in this case, a tert-butyl group, that tert is italicized and therefore it is not included alphabetically. This would be used starting with the letter B. And just to throw a fly in the ointment here, the isopropyl group, notice that iso is not italicized, and so this would be the letter I alphabetically. And just a reminder, when you're trying to find out how you're going to number your chain or your ring, you start with, if it has a principal functional group, you give that the lowest number. If that doesn't resolve the issue, then you go to the saturation index. If that doesn't resolve the issue, then you look at the substituents and you want to give it its lowest series of numbers. That will be explained when we go through some examples, okay? And finally, if you still can't, if there's still a tie, I will say, at this point, then you break the tie by listing the substituents alphabetically to find your lowest number to number your chain. So this is just an example, kind of going through all of that. I'm not going to go through this in point form. This you can look at how we can approach naming an organic molecule. This next table are the list of substituents that you are responsible for Chemistry 2500. Now this looks like a really scary table, but in fact, there's really not that much new here. Most of it is fairly intuitive. We're going to be talking about alkyl groups as substituents in just a moment, but they basically follow the same route that you learn for numbering a chain. Right? So if you have a substituent called a methyl substituent, that meth is telling you that it's a 1 carbon substituent, just like it was for your longest carbon chain. And if you have F, it's a 2 carbon substituent, and so on and so forth. Okay. Now, if you're talking about ethers, so this is basically when you have an oxygen attached to a specific alkyl group, all you do is add the word oxy to your root. So if you have a methyl substituent, you're talking about a CH3 group. If you have a methoxy substituent, you're talking about an OCH3 group. It's fairly intuitive. The halogens are fairly intuitive as well. So if a fluorine is named as a substituent, it's fluoro. If it's a chlorine, it's chloro, and so on and so forth. These substituents down here, these are some of the more special alkyl substituents. We will be talking about these in just a moment. And again, they also have their ether analogs. And again, you'll just notice that we just added the word oxy in there. So if you have isopropyl and you add an oxy, make it an ether, it'll be an isopropoxy group. So if you learn the alkyl groups here, then the ether versions are fairly intuitive. And then there's just maybe a few extra new ones here for some of these other functional groups. These are when these particular functional groups are not named as a principal functional group, but when they are named as a substituent, right? So for example, we looked at that one where we had an alcohol, but it was named as a substituent. So it was called a hydroxy group, not an alcohol. Okay, let's talk now about carbon-based substituents. And I just kind of already mentioned them in our list. And it's very simple. What you do is you would take what you would call the molecule. So if, for example, if you considered the methane molecule, this is 1 carbon because we have the meth and it's an alkane. So it's a carbon with 4 hydrogen atoms. If you stick that on a large carbon chain and you're going to make that methane as a substituent, all we're going to do is we're going to change the ane ending, so the suffix, to YL. And that's what the YL is referring to. It's referring to substituents for these carbon-based units that we're sticking on a carbon chain. So basically, all you're doing is taking away 1 hydrogen atom. Now you're sticking that CH3 group on a carbon chain, and you're calling it now a methyl group, okay? Same thing, if I take an ethane and I remove any one of those hydrogen atoms, it doesn't matter, I've just removed this one, and then you stick that now onto a carbon chain, you get what's called an ethyl group, okay? And what I've done here on the sides is I'm trying to show you what these substituents will look like when they're drawn as line structures, because it's very important you get familiar with what these look like when you're attached to a carbon chain, okay? So methyl and ethyl are fairly straightforward. When we have a 3 carbon unit, so we're looking at propane here, I want you to see that there are 2 different ways of attaching a propane unit to a carbon, a long carbon chain, okay? You can either attach it on either one of the 2 ends. So in this case here, I've removed this hydrogen atom, but it could have been any one of these 3 or any one of these 3. It doesn't matter, okay? And if I stick that onto a carbon chain, I get what's called an N-propyl group, or typically what we say is just a propyl group. It's like the normal, that's where the N is for. It's just a normal straight 3 carbon chain. So it's a propyl group, okay? And this is what it would look like when it's drawn. It's a line structure. So I've got a squiggly line here because basically what I'm saying is that this 3-carbon unit here, 1, 2, 3, is attached to a really long chain here that I just haven't drawn, okay? Now, if we go back to the propane molecule, and if you look at the 2 central hydrogen atoms, if I remove one of those and attach this propane unit to the longest carbon chain via that central carbon, I actually get what's a different looking substituent. And this is no longer called a propyl group because it looks differently. It's actually called an isopropyl group, okay? So, you know, technically it would be called a 2-propyl, but we never usually call it that. It's typically called an isopropyl group. And so what I really want you to do, I'm going to clean up the structure here, is I really want you to pay attention to how this looks different, okay, drawn in line structures. So that's for propyl, and this is what it looks like for isopropyl. Again, if I were to number the carbon atoms, just so you can see them clear, 1, 2, 3, okay? The difference is the point of attachment, okay? So for propane, carbons 1 and 3 are essentially equivalent via symmetry. So if I stick it on carbon 1 or stick on carbon 3, I'm going to get a propyl group. If I attach it to the main chain via carbon 2, I get what's called an isopropyl group. And then we just have a few more to know. If you look now at a butane molecule, okay, and this is you know, a straight chain 4-carbon unit. Again, we have 2 different ways of attaching this to a long carbon chain, either from either end, right? Whether it's the left-hand carbon atom or the far right-hand carbon atom. Either way, we're going to get this straight chain attached to the main chain, which is called an N-butyl group, or just simply a butyl group, okay? Or I could attach it to any one of the 2 internal carbon atoms. Again, they're both equivalent via symmetry. And then what I get here is what's called a 2-butyl group, or often referred to as a sec. And the sec is referring to, is short for secondary, meaning that it's attached to the second carbon of the carbon chain. So 1, 2, you can see that carbon 2 here is attached to the main chain. And so this is why it's called a sec-butyl group. Again, there's a subtle difference of how this is attached to the main chain, but that's why I'm listing these so that you can get a feel for how it looks when it's attached to a longer carbon chain. Okay, so there's just 2 more to go here. So we have the butyl group. We're going to stay with a 4-carbon unit, but this is normal butane, right? 4-carbon chain. But there is another isomer of this known as isobutane. This is also 4 carbon atoms, okay? However, this particular molecule, isobutane, can also be attached to a longest carbon chain 2 different ways. It could be attached via one of these terminal CH3 groups, and if you attach it to a long carbon chain, you get what's called the isobutyl group, okay? Again, I want you to pay very particular attention on how the isobutyl group looks different from a sec-butyl group and from just a regular butyl group. And then finally, if you attach this isobutane to the longest carbon chain via by removing this hydrogen that I've just circled, and in that central carbon atom, you get what's called a tert-butyl group, tertiary carbon. So tert is just short for tertiary. Oftentimes it's called tert-butyl or T-butyl, okay? Now there's just a few other common substituents and functional groups you should know. You should be familiar with the molecule benzene. And so you can see it's basically a 6-membered ring with alternating carbon-carbon double and carbon-carbon single bonds. There are some common names that have been adopted by the IUPAC that you must know for these different type of aromatic compounds, okay? And so some of them might be obvious, some of them not so obvious, but these are common names that are always used, okay? So for example, benzaldehyde is a fairly intuitive name. You can see the word aldehyde and benz, so it's basically a benzene with an aldehyde functional group attached to it. Benzoic acid, it's obviously a carboxylic acid attached to an aromatic ring. Some of them might not be as intuitive, like aniline or maybe even toluene, but these are the common names, and they have been adopted by the IUPAC, so they are technically official. Now, if we look at aryl-based substituents, so this is when you take a benzene ring and stick it onto a long carbon chain. We don't name it as benzene, we name it as a phenyl group, okay? So again, you'll notice the YL ending for these carbon-based substituents. This is often abbreviated or condensed into a PH, so capital P, lowercase h, that stands for phenyl, okay? And sometimes you might even see it even condensed down to a C6H5, okay, because there are 6 carbon atoms and 5 hydrogen atoms. I want you to be very careful. Notice that phenyl, YL, is not phenol, okay? Again, it's a 1-letter difference, but phenol is referring to this molecule, and phenyl is referring to a benzene, just a straight benzene ring attached to a carbon, a long carbon chain. And I'm going to mention one more because it comes up a lot, and this is what we call the benzyl group, okay? And I know because the word has benzyl, it's got the word benzene in it. It seems like, oh, it should be a benzene attached to an aromatic ring. That's not. A benzene attached to an aromatic, a benzene attached to a long carbon chain is called a phenyl group. What is a benzyl group? A benzyl group is basically a benzene ring, but you have an extra CH2 there, and then you attach this to a long carbon chain here, okay? And again, the abbreviation here would be BN for benzyl, and this would be condensed down to CH2C6H5. In this video, we're going to be looking at different conformations by rotations of organic molecules. Okay, so the first thing that we need to understand is that under normal conditions, so that's STP, standard temperature and pressure, molecules are always in constant motion. They are tumbling around in whatever vessel they're in, but not only that, they're also experiencing bond rotations around single bonds. And we have rotation around carbon-carbon single bonds, or any single bond for that matter, because the overlap when you have a single bond or a sigma bond is always remains intact, and so you can have this rotation. If we look at this diagram here on the bottom, so what you've shown, what they've shown here is a sigma bond in between 2 different carbon atoms, and you can see that you have overlap of those 2 orbitals, which are depicted in sort of a pinkish color. And if you were to rotate along that carbon-carbon sigma bond, you'll never disrupt the overlap in between the orbitals. And so you can have a rotation about that. And that's what they're trying to depict here with this little green arrow. Okay, so when you have these rotations about these carbon-carbon single bonds, these different spatial arrangements that are produced give rise to what we call conformations. So as an example, if you look here to the right, they've got 3 different molecules, 3 different depictions of the same molecule. And basically what they're doing is they're keeping the left-hand carbon static, it's not moving, and they're rotating the right-hand one. And so you can see that this hydrogen atom here, which is in the plane of the screen, and then they're doing a slight rotation according to that green arrow. And then now you can see how they've labeled the different hydrogen atoms, color-coded them so you can kind of follow along. And you can see that now it is starting to come towards you, which is why it's drawn as a dash. And then you can really, if you pay attention to the yellow hydrogen atom, you know, as it's rotating, it's pointed behind you. Now it's really pointed behind you, and then they just keep doing a rotation. So these are so one of the things that's important to understand is that when you're dealing with conformations, you're always dealing with the same molecule. So in this particular case, because we're dealing with a 2-carbon molecule and it's only saturated bonds, this is ethane. And so these are just different conformations of ethane. Okay, they're not different molecules. It's important to understand that. Okay, now conformations are difficult to view if you draw them in line structures. And so what we actually have to do here is learn a different way of depicting these molecules to really highlight these different conformations about a particular bond. And so again, what we do here is we take a molecule, any molecule, so we're still dealing with ethane in this particular case. And instead of looking at it like we are here, okay, so this is drawn in a typical line structure format. And of course, they've highlighted the hydrogen atoms. But what we're going to do, as the little eyeball and the arrow is trying to show you, is that you're actually going to rotate the molecule so that you're looking directly down that carbon-carbon bond. And this is what we're going to see if you do that. Okay, and so what they're trying to do here is they're trying to break down how these this depiction works. So if we go over here, and if you look at the top here, they've highlighted the right-hand atoms in blue. And so when you're looking down that bond, that carbon atom right here is going to be the first carbon atom that you see. Okay, and what you imagine then, that carbon atom is right here. So what they're doing is they're just showing you how they get to the front portion of that molecule. And if you're looking down that carbon-carbon bond, you notice that you have a hydrogen atom pointed straight up, and then you should have two hydrogen atoms pointed on opposite sides, and they should have, 120-degree bond angles, and that's really what you're seeing here, okay? So we're still looking down this carbon-carbon bond, but let's look at the bottom picture here now. And now we're focusing on the group that's behind the front group. So now they've highlighted that in red. Okay, and so now this carbon atom, which is directly, because you're looking down that bond, is directly behind that front carbon atom. They show that, as you can see here, as a circle. And the reason why you show it as a circle is because you'll see when we combine these two pictures together to show you the Newman projection, we want to still be able to see that carbon atom that's behind. So when you're looking down this bond, this hydrogen atom here in red that I've circled is now pointing straight down, and that's what you see right here. And then you have the other two hydrogen atoms splayed left and right at 120-degree bond angles. So now if you just meld these two pictures together, you get the actual Newman projection. Okay, and so you just need to learn the protocols, if you will, to building these. But basically, the carbon that you're directly looking at, because you're always looking down a carbon-carbon bond when you're looking at these Newman projections, will be drawn as a point. So that's that little point right there. And then, of course, the carbon atom behind it is not drawn as a point because then you wouldn't see it. So they draw it as a circle. Okay, and just pay attention to the hydrogen atoms that are coming off of a particular carbon atom. So you can see that the red circle has those three red hydrogen atoms coming off of it, and the blue dot, or the point, if you will, where they merge, the three hydrogen atoms in blue are coming from that point. Okay, so you just need to get familiar with how we depict these different Newman projections. And then we can actually look at the different conformations. It's easier to see them. So why do we really care about these different conformations? Well, because the different conformations actually have different energies, okay? And by understanding this, this allows us to get better insight into the reactivity of these molecules. I've said before, it's essentially always about energy. So we can describe these rotations about a particular bond by what we call the torsion or the dihedral angle, okay? So when the bonds of the front carbon atom align with those of the back carbon atom, I'm not just talking about the carbon atoms themselves, I'm talking about the bonds, right? Because those carbon atoms are attached to different things. When those bonds align, one on top of the other, so to speak, we call this the eclipsed conformation. Just kind of like, when you have, lunar eclipse and, you've got the sun and the moon moving on top of each other. So when you have an eclipsed conformation, there is actually repulsion between these adjacent bonds, and this creates a type of strain. And we call this torsion strain, okay? And this will raise the energy of the conformation. And again, understand the convention here. When you're going up in energy, you're going to a less stable environment or conformation. Okay, so in the eclipsed conformation, you're creating more torsion strain and therefore raising the energy, making the molecule slightly less stable. Okay, If you keep rotating, eventually you get to a point where the different bonds are going to be further apart, and this will reduce the torsion strain, therefore lowering its energy and making it therefore a little bit more stable. Okay. When we get into this type of conformation, we call this a staggered. Okay. So let's look at this in a little bit more in depth with some pictures, see if this makes a little bit more sense. So when we're talking about the torsion angle, basically what we're talking about is an angle between two planes that are defined by four atoms that are connected to each other. So look at this molecule here. This is nothing more than simple butane, right? We got 4 carbon atoms. You're looking down the bond between carbons atoms 2 and 3. And you can see they've labeled those 4 carbon atoms, okay? And then in this picture down here, they're really trying to show you how we define that torsion angle, okay? So it's basically be the angle between the bonds 1 and 2 with respect to the bond angles between atoms 3 and 4. So we have to define some planes, and they kind of defined them in that the blue shading, and that angle in between those two planes is what we call the torsion angle, okay? And basically, the greater the torsion angle, the less the torsion strain, okay? So let's go back to our ethane molecule, and let's look down the carbon-carbon bond, and let's look at these two different conformations, the eclipse conformation and the staggered conformation. So we'll start with the eclipse, and this is on top here. Okay, and so again, that's the line structure that we highlighted, but right to the right of it, of course, you can see now the Newman projection. And again, just pay special attention in how they drew this. So again, you have that front carbon atom, which has a little point where those 3 merge, so that's the carbon atom there, and then the red circle behind it is, of course, the carbon atom behind it. And notice what they've done is they haven't actually physically drawn the 2 hydrogen atoms sitting on top of each other. They've just moved them just slightly to the side so that you can at least see the 2 hydrogen atoms. But it's understood that they literally are one on top of the other when you're looking down that bond perfectly, okay? And the torsion angle between them would be literally 0 degrees, okay? This is the eclipse. So basically all 3 bonds so all 3 carbon-hydrogen bonds from the carbon that's in front are eclipsing the 3 carbon-hydrogen bonds of the carbon that is behind that first carbon, okay? So this particular arrangement or conformation, the eclipse conformation, is higher in energy than the staggered conformation. So if you were to take the back carbon atom, it doesn't matter which one, but let's just take the back carbon atom, and now we're going to start to rotate it a little bit, and we're actually going to rotate it by 60 degrees. So now we're looking at this picture down here, okay? And again, let's pay attention to the Newman projection here. And so again, we still have a normal Newman projection, but notice now that the hydrogen atoms, again, I want you to focus on the 2 highlighted ones, so those are the 2 in red. Okay, they're not sitting one on top of the other. And in fact, if you look at the bonds, again, just look at the carbon-hydrogen bonds on the front carbon atom with respect to the carbon-hydrogen bonds with the carbon behind it. And those bonds and atoms are no longer sitting on top of each other. They are staggered, right? That's where the name comes from. And because we've reduced the strain, the torsion, so we've increased the torsion angle, and therefore we've decreased the torsion strain, okay? So the angle has gone from 0 degrees to 60 degrees, and therefore we get to a more stable conformation, so we're lower in energy, okay? Now, again, I want you to be very clear when I'm talking about, lower in energy and higher in energy, I'm always talking in relative terms, okay? Just because we say that the stagger, or if we say that this eclipse conformation is less stable, I'm not saying that it's not stable. I'm saying that it is less stable, okay? So we need to be very clear on that. Okay, we can actually graph this fluctuation between staggered and eclipse conformations, and that's what we're looking at here. And this is for a simple ethane molecule, okay? And so we'll start here right at the origin at the bottom here, and that is referring to, and I'll just number it 1, this particular Newman projection. So we just happen to start in this particular case in the staggered conformation, okay? And what we're going to do is we are going to, I'm just looking at how they've done this. They seem to be rotating the front carbon atom. It doesn't really matter. And so what we're going to do is we're going to start, and again, you can follow along by looking at the highlighted hydrogen atom. So the hydrogen atom in blue that's pointing up, that's attached to the front carbon atom, and that's the one we're going to be moving. And so this plot is nothing more than the torsion angle, which is on the x-axis, versus essentially the energy, the strain energy, okay? So when we start at the staggered, at this particular conformation, the energies, what we're going to find out is at its lowest energy possible. And now what I want you to imagine is that we're going to start to rotate that front carbon atom. That blue hydrogen atom is going to start moving you know, in a clockwise fashion. And at some point, as we're doing this, that blue hydrogen is approaching that hydrogen atom that is directly to, like, we'll say at 3 o'clock, if you will, as it's rotating. And as it's going to rotate, and eventually when we get to about 60 degrees, those two hydrogen atoms and all the other ones as well in bonds are all going to eclipse each other. And so you can see here, I'm just going to draw over the graph. As we do this, the energy starts to go up because we're going higher in energy to a less stable conformation until we get to the very peak at the top of this peak. And that's when we get to the eclipse conformation, okay? Now, if we keep rotating clockwise, now that blue hydrogen atom, which was eclipsed, and again, I'm referring to this one here, right? It's going to start keep moving down. And as we do that, it's now starting to approach another staggered conformation. And so as it's moving away from those hydrogens becoming less eclipsed, the energy comes down. And eventually we'll get to the fully staggered conformation right here. And, you know, we can see that these two are different in the sense that if you're just looking at the highlighted hydrogen atom, but we can't label different atoms. So, I mean, for all intents and purposes, these two staggered conformations, which I'm just going to number this as 2. So these two staggered conformations, 1 and 3, they're identical. Okay, they literally have the exact same energies. And you'll notice that as we just keep rotating, and when we start to go through an entire circle, so 360 degrees, okay, you'll see that we're just going to constantly be going through various different conformations. We're going to be going through staggered, an eclipse, back to staggered, back to eclipse, and so on and so forth. And this is what this graph looks like. It looks just like a sine wave, okay? Okay, so hopefully you can follow along there. So essentially when we're talking about torsion strain, we're really just talking about the difference between eclipse and staggered conformations, okay? Now, what we're going to define is something, a new type of strain, which is called steric strain. And this often gets confused with torsion strain, but there is a subtlety here that I'm going to try and highlight. So steric strain is defined as a repulsive force between the electron clouds of atoms that are close to each other but not directly bound. So again, in the previous example, let me just scroll down here. In the previous example, we were looking at essentially the relative distance between say these two highlighted hydrogen atoms, right? So there was this highlighted hydrogen atom blue up here, and there was one down here, okay? And so when we're dealing with just hydrogen atoms attached to these different carbon atoms, then we're only going to be dealing with torsion strain. As soon as you get to a group that's larger than a hydrogen atom, then you introduce this concept of steric strain. Okay, so take a look at this new molecule that they're showing you. It's essentially dichloroethane. So we've replaced basically 2 hydrogen atoms with 2 chlorine atoms. Again, they're highlighted in red. So here they've drawn the line structure, and here you've got the Newman projection. Okay, so hopefully you can follow along there, and you can see that those 2 chlorine atoms that are attached to different carbon atoms, but those carbon atoms are attached to each other. The torsion angle between them right now, if you were to define that torsion angle, is 180 degrees. They are literally as far apart as possible as they can be. And so in this particular arrangement, when the torsion angle between those 2 bigger, excuse me, those bigger groups is 180 degrees, you, again, as we said before, the greater the torsion angle, the less the torsion strain, okay? And then also the less the steric strain in this particular case. Okay, so what I want you to do now is, in the previous example, when we looked at just ethane, when we went from staggered to eclipse conformations, all the staggered conformations and all the eclipse conformations were the same. They were equivalent energy. So again, you can see every single eclipsed conformation up here. I didn't finish numbering these, but we could, right? So conformations 2, 4, and 6 all have the same energy, and the staggered conformations 1, 3, and 5 also all have the same energy. When we changed some of those hydrogen atoms for a different group, we actually introduced a few more different conformations in them. And that's really what this slide is really going to talk about. And we have some special names for these things. So let's go through this. So in this first depiction here, in the staggered conformation, which I'll number as 1, we have the 2 chlorine atoms as far apart as possible. Okay. Now, if you rotate, it doesn't matter. Again, if you rotate the front carbon or the back carbon, it doesn't matter. If you do a rotation, and what they've done in this case, so I'm looking now at this particular conformation, which I've numbered as number 2, what they're doing is they are moving the front carbon atom counterclockwise in this particular case. And so notice now the relative positions of the 2 chlorine atoms. Notice now they're about, the torsion angle is 60 degrees, okay? This particular conformation is known as a gauche conformation, and that's what they have right here, okay? Basically when they are, I'll say adjacent to each other. I don't mean adjacent literally bound to each other, but I mean spatially adjacent to each other. Okay. And then if you keep rotating, eventually you can get to the point where not only will everything be eclipsed, but where those 2 chlorine atoms will also be eclipsed. And that's where we have the greatest, not only torsion strain because it's an eclipse conformation, but also the greatest steric strain, because now those 2 chlorine atoms, which are large clouds of electrons, are as close as possible, and there's repulsive forces between those electron clouds. And so again, you got these really nice stick and ball models here of these different conformations. And you can see that the distance between these 2 chlorine atoms is much closer in, say, that eclipse conformation versus the staggered conformation. Okay, and so as we decrease the torsion angle, as we go from 180 to 60 to 0, we're going to be increasing not only the torsion strain, but also the steric strain in this particular case. We can graph this. This graph will look slightly different because we've now introduced a few new type of conformations here. So in this particular graph, let's start up here. I'll call this 1. They're starting in what we call the eclipse conformation, okay? And not only is it just eclipse, but it's eclipse where the 2 chlorine atoms are as close as possible. So the torsion strain between those planes that are defined as 0, okay? And notice it's also the highest in energy on this graph. Again, the energy is the y-axis. What are they doing here? They're moving the back carbon atom clockwise. So if you do a rotation by about 60 degrees, so you can see we've gone to 60 degrees here, and now we get to conformation 2. So this is a staggered conformation, so we've reduced the torsion strain, but not only that, we've also reduced the steric strain because now we're moving the chlorine atoms further apart relative to conformation 1. If we keep rotating another 60 degrees, now we get to conformation 3. And this is going to go to an eclipsed conformation. And why is this eclipse conformation not as high in energy or not as stable, not as least stable as conformation 1? Well, notice here that even though it's an eclipse conformation, notice that the what's being eclipsed here in terms of the chlorine atoms is a chlorine atom and a hydrogen atom, not the 2 chlorine atoms. So even though we have an eclipse conformation, the steric strain between the 2 chlorine atoms is a little bit lower than it would be in conformation 1. And so this is why it's at a different energy. It's a little bit better than conformation 1. If we keep rotating again by another 60 degrees, now we have the 2 chlorine atoms at 180 degrees apart. They're as far apart as possible, and not only that, it's also in a staggered conformation, okay? So remember, staggered is always going to be a lower conformation than eclipsed, and this is by far the best staggered conformation within this particular molecule. You'll notice that the energy here of this particular conformation is slightly lower than the conformation, the staggered conformation 2, okay? And again, it's because those chlorine atoms are just that much further apart. So we keep rotating, and then we're going to get to, so this was 4, then we'll get to an eclipse conformation 5. I want you to see that the eclipse conformation 5 is literally identical to eclipse conformation 3. Okay, we're just having we just have the chlorine atoms on just different sides, but they're basically at the same distance in both conformations and therefore have the same energy. We rotate again, and then we get this other staggered conformation, number 6. Again, notice that 6 and conformation 2 are identical in terms of energy. These are 2 different gauche conformations. And then finally, if we go to, or if we rotate by another 60 degrees, we end up by reproducing conformation 1, and that brings us back to top of our graph, okay? So by introducing different groups, we might introduce different number of conformations here. Okay. Now what we're going to do is we're going to talk a little bit about cyclic molecules, and we're going to look at just a few to start with, and that's where we're going to end. So in cyclic molecules, we typically depict these as simple polygons. Okay. The problem with that, though, is that it does neglect their true three-dimensional structure. And of course, when we introduce cyclic molecules, we also introduce a new type of strain, which we call angle strain. Okay, an angle strain arises from bond angles that do not permit for maximum overlap between atoms of molecules. Another way of looking at this in terms of angle strain is that you get basically a deviation from the ideal bond angles for that particular atom, okay? So for example, if we look at cyclobutane here, we would just draw it as a simple square, okay? Or oxetane, you can see that it's a 4-membered ring with an oxygen atom. If you have cyclohexane, for example, we just draw that as a simple hexagon and so on and so forth. The problem is that cyclohexane, the way it's drawn on this screen or on a piece of paper, would actually appear to be flat, and that molecule is by no means flat. And so we need to consider this when we're considering these cyclic structures. So we'll start at the simplest ring, which would be a 3-membered ring. And this possesses, out of all the rings, the most strain, because it experiences all 3 types of strains that we've talked about. That is torsion strain, steric strain, and angle strain. Okay. So to kind of get you to think about this, let's start with propane. So we have this simple molecule here, propane. And you would have to input 36 kilocalories of energy in order to force that molecule into a ring. And that's what they're trying to show you here in this reaction, okay? And the problem is, if you look at, especially all 3 carbon atoms in propane, they would all be in a tetrahedral geometry, and they'd all have angles of about 109 degrees. But then as soon as you force it into this 3-membered ring, you're going to introduce a lot of angle strain, because if you actually just look at the angles in that triangle that we drew, they would be at 60 degrees. And that's a serious deviation from 109, and that's where we're introducing this angle strain in here, okay? Another way to look at that is looking at, as it says previously here with a defined angle strain, is that not allowing maximum overlap in between orbitals. So if you were to look at the bonds, the carbon-carbon bonds in propane, so again, they're showing you here the overlap between the orbitals. Everything's happy, they can overlap, no problem. But then as soon as you force it into a ring, these overlap here is kind of being bent. You're getting these what we call bent bonds. Sometimes they're referred to as banana bonds. And that reduces the overlap. It might not look like it's being reduced here, but it is. I mean, again, for these sigma bonds, you want to have a direct head-to-head interaction. And here you're actually bending, you're introducing an angle in there. And so you're reducing the overlap of these orbitals. And by doing so, introducing this angle strain. Now, if we look here, here is a line structure with highlighted hydrogen atoms. And a 3-membered ring would have no choice but to be planar. And in fact, it is planar the way it's drawn here, okay? If you look down any carbon-carbon bond, Okay, so let's just imagine here, I'll draw a little eyeball, and we're looking down this carbon-carbon bond. What they've done here is showing you the Newman projection for this. And you're just gonna have to take a few minutes to really try and understand that Newman projection. Okay. In fact, if just to make it simpler, let me just erase this eyeball here. I think what they're doing with this, yeah, I think they have the eyeball looking down this carbon-carbon bond. Okay. And when you look down any carbon-carbon bond, this is the Newman projection, as I said, and you can see that if you look, let's just look at these bonds here, they are indeed completely eclipsed. Okay, and so by being eclipsed, you're introducing that torsion strain, you have the angle strain, and of course, everything is as close as possible, so you're introducing the steric strain as well. Okay, so again, even though we predict this molecule to have bond angles of 60 degrees, it doesn't in fact have bond angles of 60 degrees because molecules will do basically whatever they want to do in order to be as comfortable as possible. And what I mean by comfortable, I mean, of course, by being in the lowest energy possible. So these bond angles are a bit better than 60 degrees. I can't remember, I think they want to be, they're around 70 degrees, I think. But what we actually see is that the bonds themselves are seriously bent, and it's doing that in order to try and reduce some of that angle strain. Okay, let's look at just two more rings here. We'll look at four-membered rings. Four-membered rings, again, we would draw them as a square, but they are indeed not planar. And the reason why they adopt a non-planar geometry, it's to reduce the amount of strain within the molecule. And of course, with less strain, molecule will be more stable. Okay, so right off the bat, if you were to draw a square for these four-membered rings, the bond angles would be just better than three-membered rings, right? So if I were just to draw cyclobutane like that, we'd expect these bond angles to be about 90 degrees. So 90 is not 109 for these carbon atoms, but it's still better than 60 that was predicted for three-membered rings. So four-membered rings are just inherently more stable than three-membered rings, just by virtue of having better angle strain. But if this molecule was planar, as it's drawn here, okay, the problem is then, again, if you look down any single carbon-carbon bond, you would see that all those hydrogen atoms would be eclipsed, and that would introduce a lot of torsion strain. So in fact, this molecule is not planar. It actually adopts this, what we call a butterfly conformation. Okay, so basically go from opposite corners and you're going to create a crease and then fold up the molecule a little bit like that. This is the Newman projection for, the butterfly conformation. Again, you're going to want to take just a few minutes to really try and understand this conformation. And what they're doing in this particular case is they're looking down this carbon-carbon bond to generate that Newman projection. And you can see now, and they've highlighted that with those two red hydrogen atoms here, notice that they're not exactly eclipsed. They're not completely staggered, but they're more staggered than they are eclipsed. And by adopting this butterfly conformation, it reduces the amount of torsion strain. And so therefore the molecule is a little bit happier. The other thing you have to understand too is that this molecule, this butterfly conformation of a four-membered ring, is rapidly doing what's called a ring inversion. So basically, you can see here that this carbon atom here and this carbon atom are kind of pointing up, if you will, and then you can just imagine folding along this crease, defined right here, and then now they're both pointing down, so to speak. And this is happening very quickly at room temperature. Okay, and then finally, we're just going to end it here with five-membered rings. The most stable conformation for a five-membered ring is what we call the envelope conformation. Again, when you're typically drawing these, we would just draw a simple pentagram, right? Or pentagon, I should say, not a pentagram. And the bond angles, again, are getting better. You can see here, they've shown that at about 108. So it's actually got very little angle strain because you're very, very close to the ideal angle of 109 or 109.5 for the typical carbon atoms. However, if the molecule was planar, as it's shown here, again, if you look down any bond, so look down this red bond here that they've defined, you would see that all the hydrogen atoms are eclipsed. Well, in order to get away from that, again, one corner, and in this case, it's this corner right here. So this corner here is moving up, okay? And it's no longer in a plane. So basically, you kind of have these 4 carbon atoms here that I'm highlighting in a plane, and then the other one is kind of puckered up a little bit. It kind of looks like an envelope, and this is where the name comes from. And by doing that, if you were to look down that red carbon-carbon single bond, you would get this Newman projection that they show you down here. And you can see now that basically the hydrogen atoms are almost perfectly staggered at this point. And again, this is why this molecule adopts this unusual envelope conformation. It's just literally to try and reduce the amount of strain it experiences so that it can be lower in energy or more stable. Okay, we're going to end it there, and then we'll continue with the next video, and we're going to be talking about 6-membered rings because they're extremely important in organic chemistry. In today's video, we're going to be talking about the conformation of 6-membered rings. 6-membered rings are found in many organic compounds, and the reason why it's found in so many different organic molecules found naturally is because cyclohexane is the only ring under 14 carbon atoms that is essentially free from any strain. And the reason why it can be essentially free from any strain is because it can adopt a really important conformation known as the chair conformation. And this is what we're going to spend time talking a little bit about today. Now, when you look at a cyclohexane ring, and if you were just to draw it as a hexagon, it appears like the molecule is flat. And as we saw with the other rings, barring the 3-membered ring, these rings do not adopt flat conformations. And this is especially true for the 6-membered ring. The chair conformation of the cyclohexane ring, and it's named because it kind of, if you were to look at it a certain way, it kind of resembles a chair. And this is what they have drawn here for you. And they've got a plane defined, a blue plane, and what they're trying to show you is that the ring, parts of the ring are going to be below that plane and parts of the ring are going to be above that plane. So I'd like to just talk a little bit about the features of a cyclohexane ring, especially in its chair conformation, because there's a lot of symmetry at play here, and it's really important that you're able to understand what's actually happening here. So a cyclohexane ring has 6 carbon atoms and 12 hydrogen atoms. And what you're going to see is that the hydrogen atoms can be in one of 2 positions, and these are known as either axial hydrogen atoms or equatorial hydrogen atoms. And they are highlighting those separately in these 2 pictures. So they have the axial hydrogen atoms highlighted in yellow. And what you'll notice is that these are going either directly pointing up or directly pointing down. The equatorial hydrogen atoms, this is on the picture to the right of this, and the hydrogen atoms are highlighted in red. You can see that they're not perfectly vertical. They're kind of going off at an angle, again, either pointing down or pointing up. And it's really important that we understand that you have these 2 different, we'll say, spatial positions for these hydrogen atoms. Again, what you'll notice if you focus in on the 6 axial hydrogen atoms, you'll notice that 3 of them are indeed pointing up and 3 of them are indeed pointing down. And this is the same thing for the equatorial hydrogen atoms. Again, it's a little bit, maybe a little bit harder to see whether they're pointing up or down, but you can just look at the way the bond is either angled up or down. Again, you'll have 3 of them pointing down and you'll have 3 of them pointing up. The other thing I think to notice, and this is very helpful later on when you're starting to learn how to draw these cyclohexane rings, is that whether the hydrogen atom is pointing up or down is, well, it alternates between carbon atoms. So let's look now at the the chair conformation of a cyclohexane ring. And this is where they're showing you the entire ring with all the hydrogen atoms attached to it. And what I want you to notice is, let's just start at any particular carbon. So let's just say we start here. And what you'll notice is that any particular carbon atom, it'll always have one axial hydrogen and one equatorial. And it's like this for for all 6 of these carbon atoms. So what I'm saying is you can't have a carbon atom that has 2 axial hydrogen atoms or 2 equatorial. It's always one axial, one equatorial. Now, if you focus in on that carbon that I've highlighted, and if you look at the axial hydrogen atom attached to it, which is pointing down, then you'll notice that if you go to any adjacent carbon atom, whether it be this one here, or whether it be this one here, notice the spatial direction of the 2 axial hydrogen atoms attached to it. They're pointing up. And what I'm getting at is that they always alternate. So if we started at that first carbon atom where the axial hydrogen is pointing down, then that means the next carbon atom attached to it, again, it doesn't matter if you go like clockwise or counterclockwise if we define a direction, they will be pointing up. And then if you go to the next one attached to that, the axial hydrogen will be pointing down. It's always alternating from pointing up to pointing down. And it's the same thing for the equatorial hydrogen atoms. Okay, so again, if you look at the first carbon atom that I highlighted, the equatorial hydrogen, this one here, is pointing up. And then if you go to any one of the carbon atoms adjacent to it, so let's look at the one here going clockwise, this hydrogen atom here is in fact an equatorial hydrogen and it is also pointing down in this case. So it's always going to alternate. Okay, now we can also draw Newman projections of cyclohexane rings. There's essentially no difference in the way the Newman projection is drawn. The only thing to consider is, and if you can see here in this picture here, when you're looking down one of the carbon-carbon bonds, it turns out that there's a bond that is exactly parallel to that bond. So when you're looking down one carbon-carbon bond, in fact, you can actually look down 2 carbon-carbon bonds at the same time. And so this is why they have the Newman projection shown here. And it might look a little bit weird, but you need to spend a little bit of time trying to understand what that picture is trying to show you. And they've got some hydrogen atoms highlighted in red, and they have some hydrogen atoms highlighted in blue. And you can see that here. And then they're also using those same highlights there in the actual Newman projection. So in this particular case, we're looking down these 2 carbon bonds here, and a carbon-carbon bond there. And that's in fact the Newman projection of those 2. Those are the front carbon atoms, and of course the circles represent the carbon atoms behind it. Now, we talked about how the chair cyclohexane is the most common by far conformation of a 6-membered ring. And this is because when it adopts this chair conformation, it is relatively free from strain. So if you recall earlier, we had defined things as torsion strain, whether things were eclipsed or staggered. We talked about steric strain, when you start replacing hydrogen atoms with larger atoms with bigger electron clouds. And of course, we talked about angle strain, which was essentially a deviation from the ideal 109.5 degree angle of tetrahedral carbon atoms. In chair cyclohexane, so the reason why they're showing you here the Newman projection, if you look at the Newman projection, I want you to look at basically any 2 hydrogen atoms that are highlighted in blue and red. So I'll say this one here and this one here. And you'll see that they are basically nice and staggered. And so in a chair cyclohexane, there's essentially no torsion strain here, because everything turns out to be staggered rather than eclipsed. Because we're all dealing with hydrogen atoms, there's essentially really no steric strain either. And then it turns out that the bond angles in a chair cyclohexane are right around 109 degrees. So very close to the ideal bond angle. And so this is why this chair conformation is so relatively free from strain. Okay. Now, one of the important things is you're going to have to learn how to draw these particular chair cyclohexanes. And in your textbook, specifically section 3.5.1 of your text, It breaks down a method. Again, you don't have to follow this method if it doesn't work for you, but there is a way that they show you on how to start learning how to draw these cyclohexane rings. And it is important that you can indeed draw these, not necessarily perfectly, but to get the general structure of a chair conformer. There's a couple common errors that's highlighted in this particular slide in order to learn and to draw these chair conformers, but also to avoid as you're drawing them. And so when you're drawing the ring itself, not the hydrogen atoms attached to it, but the ring itself, you should have no horizontal or vertical lines. And this is one of the most common mistakes I see when students are first learning this. And this is what runs them into problems. So for example, if you look at the structure here, these two lines that they started with when they drew are actually nice and horizontal. And that's going to run you into major problems when you're trying to put in your hydrogen atoms. So you should not have any vertical or horizontal lines when you draw your ring. Your ring should look more like this. And you can see that they're kind of slightly angled. It just takes a little bit of practice to realize what angle you're going to be at. Point two here is that if you look at any at the ring structure itself, and you can kind of break it down into these little V's, if you will. And this is in fact how they kind of teach you to draw this if you refer to that section 3.5.1. And if you look at any V, and if you look at the central carbon of the V, and if you look at the direction it's pointing, that's the direction that the axial hydrogen attached to it should be pointing. So for example, here, let me just look at one portion of this ring here. There's the V, and that V, that central carbon atom, the point of the V is in fact pointing down. And so that's telling me then the axial hydrogen should be pointing down. The way they have it drawn here is that it's actually pointing up, and therefore this is why it's incorrect. Okay. So if you look at the correct structure here, you can see that you have your V, and they actually now have the axial hydrogen pointing down. Just little things like that to get you started while you're drawing these things. Again, remember, if you have the first axial hydrogen and you point it down, then you know that you have to alternate now moving from that particular carbon atom. And it's an easy way of drawing in your structures. A little bit of practice and you should be able to draw these chair conformers fairly quickly. By far the hardest thing to do is to get correct placement of the equatorial bonds. Again, it just takes a little bit of practice. And one of the things that they point out here is that the equatorial bonds, there's a lot of symmetry in this chair cyclohexane. And a lot of these equatorial bonds are actually parallel to some of the bonds in the actual ring. And it's in fact, they're parallel to bonds that are 2 bonds away. So for example, if you have this equatorial bond here, and if I count 2 bonds going counterclockwise, or sorry, clockwise, 1, 2, now I have this bond here. And you can see that they are parallel. And if I continue going clockwise from that bond I just highlighted, 1, 2, oh, now I have another equatorial hydrogen, and so on and so forth. Okay, so you can see here in the incorrect version, those hydrogen atoms in an equatorial position, they're not parallel to any of the ring bonds, and so that's telling you that it's in an incorrect position. And again, they show you the same thing here for some of the other hydrogen atoms. And then finally, what they're showing you is when you draw the chair, the ring itself, the 3 bottom carbon atoms are understood to be pointing towards you, and the 3 top carbon atoms are understood to be kind of pointing away from you. Even though we're not really drawing dashes and wedges, this is the way it is. And if you look at this incorrect structure, and if you try and understand that spatial arrangement that they're trying to talk to you about, this looks kind of horribly strained, and this is why you want to actually draw it like this. So I would highly recommend that you look at section 3.5.1 so that you can get an idea of how to draw these structures. Okay, let's continue here. And one of the important things to understand is that a chair cyclohexane can adopt 2 different chair conformations. And these can actually interconvert through a process called a ring flip or a chair flip. Now, this kind of is a misnomer sometimes, because students tend to think that it just kind of flips over on itself like it's doing a somersault. That's not what happens at all. The best way of seeing this is actually with a model, which I will show you during our meeting on this particular section. So what actually happens here is that the bonds are moving in space. So it's not just like the whole molecule is doing a flip of itself, they're kind of rearranging. So rearranging is maybe not the best way of describing this, but they're kind of changing direction, so to speak. So here, what they're showing you is just the ring, and they don't have the hydrogen atoms attached to it yet. And just to try and get an idea of what's going on here. And I want you to focus in on, say, this carbon right here. And notice how it's sort of pointing down. It's below that plane that they've shown you earlier. When this undergoes a ring flip, basically this carbon is going to go up, and then from there, everything is going to kind of reverse. So the next carbon is going to flip down, and this carbon would flip up, and this one would flip down, and so on and so forth. And then you would end up with a ring that looks like this. It's still a chair ring, except all the carbon atoms that were pointing down are now pointing up, and all the carbon atoms that were pointing down up are pointing down. Okay, it's kind of hard to visualize this, like just in the static pictures here. Again, a model will help out a lot with that. Now, one of the important things about important consequences of this ring flip or this chair flip is what happens with the hydrogen atoms. And so they're showing you again the exact same ring flip here. And now what they've done is they've only added the axial hydrogen atoms. Okay, so again, you can see there are 6 axial hydrogen atoms, and they've in fact highlighted one of them, which is colored red. And you can see there's the little word balloon attached to those hydrogen atoms. And it says the axial hydrogen atoms will rotate to equatorial positions. So when the chair, when the ring itself undergoes this ring flip, one really important consequence to understand about this is that any axial hydrogen, so all 6 of those axial hydrogens, after they undergo a ring flip, they will now be all equatorial. Okay, and so what they've done is they've shown you here, you've got the 6 highlighted axial hydrogen atoms, and then they do the ring flip, and now all those are the same hydrogen atoms, and notice how they're all equatorial. Okay, now conversely, there's another picture. Here what they've got is the exact same ring, an exact same position as it was above, except here they've only highlighted the equatorial hydrogen atoms. And again, there's 6 equatorial hydrogen atoms. And so just like the above, the consequence above, when the axial hydrogen atoms turned into equatorial, those same exact equatorial hydrogens now, when you undergo a ring flip, they will all end up as axial hydrogen atoms, and you can see that here. Okay, so the take-home message here is that when a chair cyclohexane undergoes this ring flip, all axial hydrogen atoms become equatorial, and all equatorial hydrogen atoms become axial, and they kind of interconvert that way. Okay. Now, in actual cyclohexane, one of the important things to understand is that the energy of the 2 chair conformers via the ring flip are identical. Okay, and so you have to imagine, not only is this chair cyclohexane tumbling around in whatever vessel it is, it's also rapidly undergoing this ring inversion, this ring flip continuously, because both of the ring flips, both of the conformers have the exact same energy. Again, we would say that they were degenerate in energy. Now, let's leave cyclohexane now. What we're going to do is we're going to replace one of those hydrogen atoms with some other group. In this particular example, we're going to replace the hydrogen atom with a methyl group. As soon as we do that, we no longer have those 2 conformers being of equal energy. Okay, and this has to do with some new strain that's introduced into the molecule. So let's look down here for a minute, and you can see that they've replaced one of the hydrogen atoms with a methyl group, which is highlighted in blue, and they've also removed a bunch of the hydrogen atoms, and they're just doing that for clarity. Okay, and they're only highlighting the important hydrogens that they want you to see at this particular moment. So you can see that in this chair conformer, the methyl group is in the equatorial position. And of course, we know that if you do a ring flip, then equatorial positions end up being axial. So if we do a ring flip here, and that's what they've done here, you can see now that this is the same exact molecule, and now that methyl group is axial. It turns out, though, that when that methyl group is in the equatorial position, it's much more favorable. It's more energetically favorable, i.e. it's lower in energy when that methyl group is in the equatorial position rather than when it is in the axial position. Why is that? Well, it comes down to what we call 1,3 diaxial interactions. So that's a big mouthful, but it's actually very easy to explain. If you recall, when we looked at cyclohexane, remember we had 6 axial hydrogens. 3 of them were pointing up, 3 of them were always pointing down. If we go back to this picture here, especially when the methyl group is in the axial position, they've got the 3 axial bonds that are pointing up, for example, highlighted. This is why they've included those particular hydrogen atoms, okay? And so what actually happens is this methyl group is larger than the hydrogen atom that used to be there, right? We've replaced the hydrogen atom with this methyl group. Anything, is bigger than a hydrogen because a hydrogen is the smallest atom we could put there. So this group is bigger. And what's actually happening now is that this methyl group, it takes up more space, and it actually happens to be closer to these 2 axial hydrogen atoms on the same face of this molecule, okay? And if we were to number this, if we call this position 1, okay, and I count to one of these axial hydrogen atoms, that would be in position 3. I could do the same thing for if I were to count to the other axial hydrogen, so that methyl carbon I'll still call 1, then 2, 3, this would also be 3, okay? This is where the 1,3 comes in the term 1,3 diaxial interactions, right? And the rest of it is fairly self-explanatory. It's 2 diaxial interactions interacting with the methyl group, and these axial positions are 3 away, 3 positions, 3 carbon atoms away, if you will, from the methyl group in this case. And so this is where the term 1,3 diaxial interactions happen. Again, just look spatially at, let me clean this up a little bit. Look at the proximity of that methyl group to those 2 axial hydrogen atoms there. And then if you look at it over to the first conformer here, these are the same hydrogen atoms. Okay, but now everything's in the equatorial position. And notice that, like, spatially, that methyl group is much, much further away from any of those hydrogen atoms, right? And so because, clouds of electrons are further away, it reduces the strain, or in this particular case, this diaxial interactions. And therefore, this is why this particular molecule would rather have that methyl group in the equatorial position rather than the axial position. So as soon as you replace any hydrogen atom on cyclohexane with anything bigger than it, so i.e. any group, what we're going to find is that we now break the degeneracy of those 2 ring conformers from the chair flip or the ring flip. And what we're going to find is that we want the larger group. Typically, it'll rather spend more time in the equatorial position than in the axial position. And this is why you can see the equilibrium arrow here. It's not showing equally. It's pointing more towards the left, where the methyl group is in the equatorial position. And we find that this is always the case. Basically, the larger the group, the more time it wants to spend in the equatorial position. Okay, and again, the reason behind this is because of what we call these 1,3 diaxial interactions. So if you get a very large group, like a tert-butyl group, and this group is in fact very, very large, it spends almost 100% of its time, not in this position, but in the equatorial position here, okay? This is what this table is essentially trying to show you here. So this is not an exhaustive table. This is just a very small, but it'll give you an idea of what we're talking about here. So as it says here, in general, the more stable chair conformer of the 2 ring flips, right, is the one where the larger substituents are placed in the equatorial position. Okay, so if it has a choice being, because when it does a ring flip, it goes from equatorial to axial. and vice versa, it would rather spend more time in the equatorial position. So this table here just shows you a couple different groups that have replaced the hydrogen atom, so chlorine group or methoxy group, methyl, C6H5, that's a phenyl group, and that last one there is the tert-butyl group. And so you can see this is basically the percent it wants to spend in the equatorial position versus the percent it wants to spend in the axial position. And so basically, as this group gets essentially larger and larger, you can see it wants to spend more time in the equatorial position. We can quantify this, what is called an A value, and this is basically telling us the exact same thing. The larger the A value is, the more that particular group would rather be in the equatorial position. Okay, and that's all that A value is referring to. Okay, so we've looked at cyclohexane and the two different chair conformers due to the ring flip. We looked at replacing one of those hydrogen atoms with a group. Now we're going to look at a di-substituted six-membered rings, and you can see things get a little bit more complicated when we do this. Now, when there's more than one substituent to a six-membered ring, the position of the substituents need to be analyzed in order to determine the most stable conformer. Okay. So let's look at this particular molecule. This is a dimethyl, specifically a 1,4-dimethyl cyclohexane. And it turns out here, so you'll notice that those two methyl groups, notice that they're drawn with two wedges. That means that they're on the same side. Okay, the proper name for this would be cis. We haven't talked about this. We'll be talking about that in chapter 4. But you can still follow along here, noticing that there's two wedges there. So both of those methyl groups are on the same face or the same side of that ring, okay? And so what they've done here is, this is essentially the molecule drawn in a line structure with condensed methyl groups drawn on it. Again, we don't have to draw the CH3. We could have just had the end of a line here, but they wanted to highlight it, so they've used it in a condensed form. And then this particular structure represented in a chair cyclohexane looks like here, okay? That's what this is the exact same molecule. You can see they've still got the positions 1 and 4 highlighted, and you can see the two methyl groups, okay? And you'll notice that they're on the same face of the way this molecule is drawn. In this case, what they've defined as the top face, okay? That axial bond, position 4, is pointing up. And if you look at the equatorial position or bond from the methyl group in position 1, it's also pointing up. So this is what we have. And so what they've done is then they've just literally removed the two hydrogen atoms, and they've just drawn a very clean structure here, okay? Okay, so now what we want to do is we want to look at the two different chair conformers of this, okay? So here's the same picture, and what they've done now is, notice how one of those methyl groups is axial. They've highlighted that in blue, and of course, by being in the axial position, it's going to introduce these 1,3 diaxial interactions to those two hydrogen atoms that they're pointing to with those red arrows, okay? So there's nothing we can do about that. It's just that there are some of these diaxial interactions whenever you have these groups in the axial position. It just is. The question is how bad and how much of those interactions are there. So there's our chair conformer. Now let's do a ring flip, or what they're calling a ring inversion. And again, let's understand the consequences here, what happens when you do a ring flip, right? Axial bonds become equatorial, and equatorial bonds become axial. So if you look at this particular methyl group here, notice it's equatorial. Well, after the ring flip here, it's axial. And you can see that blue methyl group that was axial is now equatorial, okay? They've just now redrawn in those other two axial hydrogen atoms. And you can see now when we do a ring flip, now the other methyl group is experiencing two 1,3 diaxial interactions. So it turns out in this particular molecule with those two methyl groups on the same face, when you do a ring flip, those two conformers have equal energy, because in one conformer, you have some 1,3 diaxial interactions, and you have the other methyl group equatorial. And then when you do the ring flip, now the other methyl group is axial, experiencing 1,3 diaxial interactions, and the other methyl group now becomes equatorial. So they're equivalent, okay? And that's for this particular molecule. And it's very important that you analyze these individually like this every time, okay? And that's it. I mean, so one methyl group is going to have to be axial, the other one's going to be equatorial, and it turns out, even with the ring flip, that they both have the same energy. Okay. Now what I want to do is I want to look at a different 1,4-dimethyl molecule. And there's a very subtle difference here, and I want you to pay attention. Notice the bonds to the methyl groups. They're not both wedges in this particular case. One of them is now a wedge, and one of them now is a dash, okay? And this has major consequences on the structure, especially the energy of the molecule. Okay, so what is the dash and wedge telling us? Well, that's telling the wedge is telling us that this methyl group is pointed towards us, and this other methyl group attached to position 4 now is pointing away from us. Okay, now when we draw the chair conformer of this, we get this molecule here. And again, I want you to pay attention to what's actually happening here. So the dash and wedge mean that they're going to be pointing in opposite directions. So that means then, if we look at it in the chair conformer, that they should be on opposite faces. Again, if we were to talk about the top and the bottom face of our molecule. And so in position 1, what they're doing is they're saying, okay, this is on the top face of the ring. So it's pointing up, so to speak. And that means then this methyl group here must be pointing in the opposite face, the bottom face. Now, I'm going to stop here, and I really, really want to highlight this point that's up here, because students do this all the time, and it's incorrect. And I'm going to read this, and I'm going to repeat this over and over and over again. One of the things that you have to be able to do is to take a structure, a cyclohexane ring with its substituents on it, drawn in a line bond fashion, and be able to write it into the chair conformer, okay, correctly. And students always assume that there is a connection between dashes and wedges and whether they're attached to equatorial or axial bonds. And as it says here, the dashes and wedges are completely independent of whether the group is axial or equatorial. There is no correlation between dashes and wedges and axial and equatorial bonds. There is none. Okay, you need to be able to interpret the molecule correctly and put it in the right position, and then from there analyze the chair conformer. Okay. Again, just to highlight this, if there was a correlation, take a look at this particular methyl group attached to the 1 position. It has a wedge. Okay, and notice that in the structure here, so here's that same methyl group attached to position 1. It has an equatorial bond. Okay, now if you look at the next methyl group, which is attached to the dash in position 4, and it's drawn right here in our chair form, it's also equatorial. So right off the bat, you can see the dash going to equatorial, wedge going to equatorial. No correlation. Okay, so it's really important that you have to interpret what the molecule is to draw the proper chair conformer and then analyze the structure. Okay, so if you erase the hydrogen atoms, and you get the structure that looks like this, and you can see you have those 2 methyl groups on opposite faces of a ring. Okay, so they are in fact both in the equatorial position. So if we go down here, obviously, we know that when we do a ring flip, okay, those 2 methyl groups will now, those 2 methyl groups which are equatorial, so right here, there are 2 equatorial groups. We know that if that were to undergo a ring flip, then those 2 methyl groups will be axial. And that's what they're trying to show you here. So they're just in a different position here, but I want you to pay attention. If you have, so they have this methyl group, I'm looking at the top structure. The methyl group at position F, so to speak, it's axial, and the methyl group, which is in position C in this particular case, is also axial. Now it undergoes a ring flip, so they're doing a ring flip, and now we're getting this chair conformer. And notice that the two methyl groups are equatorial. And again, all you need to keep in mind is that the more groups that are larger than hydrogen in the equatorial position, that's always going to be a favorable, or generally a more favorable conformation. So in this particular case, you can have one chair conformer where the two groups are axial, and then when you do the ring flip, they now both become equatorial. So in this particular molecule, the two conformers of the ring flip are not equivalent, not like the previous example we looked at, where there was always one axial, one methyl group that was axial, one group that was equatorial. Here, they're either both axial or they're both equatorial. And of course, the one where they're both equatorial, this one down here, it is much more favorable. And you can see that from the equilibrium arrow, it's much larger, it's pointing to the conformer where they're both equatorial. Again, why is it better than having them both axial? Because when those two methyl groups are both axial, each one of those methyl groups is experiencing 1,3 diaxial interactions, which is raising its energy and making it just a little bit less stable. And that's what they're just trying to show you here. Okay, so here in this one conformer, they're both equatorial. You do the ring flip, and now they're both axial. And here they're showing you, they've highlighted the 4 hydrogen atoms that are also axial. And you can see that both of those methyl groups are now experiencing these 2 to 1,3 diaxial interactions. And so it doesn't have any of these interactions with the axial hydrogen atoms when they're both equatorial. And so this is why the equatorial is much more favorable. You can see that through this particular equilibrium distribution. Okay, we're not going to keep going on like with 3 groups and 4 groups. Essentially, it's always the same. The more groups that can be equatorial when you do a ring flip, the more favorable it will be. And so as a practice, and we're going to look at this when we do our meeting about this, but in the meantime, what I want you to try and do is take these molecules that are drawn here, they're drawn in line structures with some condensed forms of these methyl groups and hydroxy groups and stuff like that. I want you to draw them in their chair form, and then do the ring flip and look at the other chair form. And this all starts off by trying to be able to interpret the molecule correctly in a chair conformer, and then do the chair form. So we will work on that together when we do this meeting. In today's video, we're going to be introducing the concept of stereochemistry. We talked earlier about how early organic chemists had noticed that the actual arrangement, the different arrangements that these atoms could have, could give rise to different properties. One thing I want you to think about with these molecules is I want you to imagine these atoms as sort of Legos. So these Legos can come together in different ways. They have different connectivities. And this is sort of the same thing with these different molecules. So a given set of atoms, or given a set of atoms, you can connect them typically in more than one way. And this gives rise to what we call isomers. The first type of isomer I want to introduce to you are what we call constitutional isomers. And the definition of constitutional isomers are very simple. It's essentially the molecules that have the same molecular formula, but they have a different connectivity. So here's an example. We have these 7 different molecules, and they all have the formula, the molecular formula of C4H10O. And if you look at, hopefully you can see that all these 7 different molecules that are drawn, they all have that formula, and yet they're all connected differently. What do we mean by they're connected differently? Well, just look at the alkyl bits that are attached to the different features. So for example, these first 3 molecules on top here, these are all ethers. And if you look at the first one, you'll notice that the oxygen atom is actually attached to 2 ethyl groups. Whereas in the second one, the oxygen is attached to a methyl group on the left-hand side and a propyl group on the right-hand side. So it's connected differently. So they would be constitutional isomers. In the third ether, we have an oxygen attached to a methyl group, and in this case, on the left-hand side and on the right-hand side, it's attached to an isopropyl group. again, it's connected differently. These three ethers, they would definitely be constitutional isomers, but we would expect them to have similar reactivity because all three of them are in fact ethers. However, they should have different reactivity compared to the four molecules below, as these are all four alcohols. And again, they're all connected differently, but they are indeed different molecules. So the thing with constitutional isomers that's important is that these molecules, they're all different and they have distinct physical and chemical properties. So they're going to have similar chemical properties, like all the alcohols will behave similarly and all the ethers would behave similarly. But they would definitely have distinct physical properties, i.e. melting points or boiling points, solubilities, and so on and so forth. One of the important concepts of this is just being able to draw different constitutional isomers. So I'm going to leave this problem with you. We're going to look at this during our meeting when we cover this topic. And so this is just a very simple question. I've given you a formula here, C3H4Cl2, and I've asked you to draw all possible constitutional isomers. And I want you to draw them in line structures for this particular formula. Notice I haven't also given you a number. I'm not telling you that there's only 5 or that there's only 10. I will tell you there's more than one and there's less than, I don't know, say 100. But that's part of the question, is to go through this systematically and try and find these different constitutional isomers for this particular formula. I'd rather you focus not on discovering all of the different ones. I would rather you learn how to go through this systematically and just try and get as many as possible. And we will look, like I said, at this at one of our meetings. Okay, so that's constitutional isomers, but there's another type of isomer that we want to address, and these are known as stereoisomers. And there's definitely a subtlety here compared to the constitutional isomer. So here's the definition of what a stereoisomer is. The molecule has the same molecular formula, and this is exactly the same for constitutional isomers. However, in this case, stereoisomers also have the same connectivity. What is different about these different stereoisomers is their arrangement in three-dimensional space, or the three-dimensional arrangement in space. So these stereoisomers can have different three-dimensional arrangements, and these different three-dimensional arrangements in space, these are called configurations. And we're going to talk a little bit more about configurations and how we determine absolute configurations a little bit later. Just understand that the configuration of a molecule is permanent. So you've already seen this, but we represent these different configurations, or sometimes we will represent these different configurations on a piece of paper using these dashes and wedges that we've already introduced to you for when drawing line structures. This becomes extremely important when you are representing stereoisomers. And so this is why it's important that you know how to use dashes and wedges properly. So I want you to see here that there are two molecules. So there's molecule 1 here, and there is molecule 2 here. They're just drawn slightly different. So if you look at molecule 1 in the left-hand way they drew it, they've actually shown you the hydrogen atom that is attached to that carbon, which has the hydroxyl group attached to it. Again, strictly speaking, if you were drawing this in line structures, you would not show that hydrogen atom, and so it would be represented more like this. They're both identical, they're both correct. It just depends on what you're trying to highlight. But what I want you to what I want you to notice here in structure 1 is that the OH group here is pointed towards you, which is why it has a wedge. If you look at molecule 2, almost everything is identical. The only difference here is basically the spatial arrangement of that hydroxyl group. It's not pointing towards you, it's pointed away from you, and this is represented, of course, by that dash bond. So these two molecules, they have the same molecular formula. They actually have the exact same connectivity. What's different about them is their three-dimensional arrangement in space, and therefore they would be a type of stereoisomers. There are a few different types of stereoisomers, and which we're going to talk about. And the first one we're going to talk about is the idea of what we call enantiomers. And again, there's a lot of definitions here, and it's very important that you understand these definitions precisely in order to fully grasp the nuances, if you will, of these different type of isomers. So one type of stereoisomer is what's called an enantiomer. And enantiomers are stereoisomers that are non-superposable or superimposable mirror images of one another. Why is that written funny where it says superposable and there's the IM in parentheses there? I've always said it's, the way I've always pronounced this or said the word is always superimposable. However, the text uses the word superposable. So I just kind of inserted the IM in parentheses because this is just how I'm going to refer to it. And I just wanted you to be aware that we're meaning the same thing. What do we mean by superimposable or superposable? What we mean by that is that you take something, an object, and if you could imagine that they were like see-through, so to speak, in a sense that they didn't have actual physicality, and you can just literally take one object and put it on top of the other object where everything was perfectly aligned. Okay, that's what we mean by superposable or superimposable. So when we say non-superposable or superimposable, we mean that you can't line everything up properly. Okay, so enantiomers are objects that are mirror images of each other and that they are non-superimposable. Let's kind of go through an example of this. So what we have here, again, I'm just going to number these. We have two molecules, 1 and 2, and we want to determine if these are enantiomers. So we want to see if they are non-superimposable mirror images of each other. Now, the way molecules 1 and 2 are drawn for you on this slide, I hope you can see that they are clearly mirror images of each other. This is why they've been drawn like this. They've even given you that dashed line, which represents the mirror, and you can see that they are perfectly reflected. So at this point, they are definitely mirror images of each other. So what we need to determine is if they are non-superimposable mirror images of each other. So what they're going to do here is they're going to take molecule 1 and they're going to literally do nothing with it. So all they've done is they've transposed it down here and they kept the drawing of this particular molecule identical. What we're going to do now is we're going to take the second molecule and we're going to flip it and rotate it and just do some different things to try and we're going to try and get it to see if it completely lines up, and we could put it on top of molecule 1 to see that if it was perfectly superposable, right, or have everything line up. Okay, so the first thing they're going to do with molecule 2 is they're going to rotate it within the plane of the paper or the screen, okay? And that's what they're trying to show you here with this rotation, okay? And so basically, this group is going to go that way, and this group's going to go that way. And also notice that as you're rotating it, you know, basically clockwise in the plane of the screen, that the OH group is also going to kind of flip up. And when you do this rotation of 180 degrees, your molecule 2 now is going to look like this, okay? That's all we've done. We just literally rotated within the plane. Now notice that it's not perfectly lined up with molecule 1 down here. And the one thing I really want you to pay attention to is look at that 4-carbon chain. And I want you to look at it in molecule 1. And if you start here at this first carbon atom, and I'm going to be going through this carbon chain here, I want you to notice when I go to carbon 2, I'm going up in my zigzag, then I'm going down, and then I'm going up. Okay? Now, I want you to notice that same 4-carbon chain in molecule 2, and I want you to look at how we're going, we're doing the zigzag. So here, this is the same carbon 1 as it was in molecule 1, and notice now we're going down, up, down, rather than up, down, up, okay? So what we're gonna do now is we're gonna take molecule 2 and we're gonna rotate it now through the screen, the plane of the screen or the paper, so that this carbon will end up by being like below, so to speak, and the other carbon will go up, and your OH group will come down, and so on and so forth. Now, one of the things you have to pay particular attention to, especially when you define dashes and wedges, what happens when you do these type of rotations. And I want you to see that if you take that molecule and you rotate it 180 degrees, as they're showing you here, but now we're not going in the plane, we're going through the plane, that OH group, although it'll be pointing down, it will now be pointing away from you. And this is why the dash is, or sorry, the wedge is turned into a dash, okay? Now, this might be difficult for you to visualize. And when we're dealing with this entire topic here of stereochemistry, it's all about three-dimensional, you have to think of these molecules in three dimensionals. This is definitely easier for some people than it is others, but it's something that can become easier with practice. I would highly suggest that if you have trouble visualizing these molecules in three dimensions, that you actually invest in a good model kit. And I'll be using some of these during our meetings to try and highlight some of these features. However, if you can't see this, you just have to take my word for it that when we do this rotation, I'm just going to clean up my structure a little bit. When you do this rotation here through the plane, that this is molecule 2, and this is still molecule 2, okay? However, that dashed line, it needs to be there. It's no longer a wedge because that OH group, when you do this flip, this rotation, will make it go pointing away from you. Okay, now why do we do that? Because now I want you to notice here the 4-carbon chain. Notice there's that carbon 1. Notice I'm going up, down, up. It's perfectly lined up with the carbon chain from molecule 1 now. Okay, so again, they've redrawn. So here's molecule 2, there's molecule 1, and you can see they have them side one on top of the other, right? And I want you to notice that if you were to take, I mean, it doesn't matter if you take molecule 2 and put it on top of 1, or if you take 1 and put it on top of 2, that everything perfectly lines up except for 2 things. And I want you to point your attention to the carbon atom right here, which is this carbon atom here in molecule 1. And attached to that carbon atom is a hydroxyl group, and of course a hydrogen atom, which they've not shown, but it's still there. Okay, so everything, when you take those 2 molecules and stack one on top of the other one, everything lines up, or everything is superposable, except for the hydroxyl group, because in molecule 2, for example, it's pointed away from you, and in molecule 1, it's pointed towards you, and vice versa. Sort of the same thing now with the hydrogen atoms. In molecule 2, that hydrogen atom that's not shown to you would be pointed towards you, it would be a wedge, and in molecule 1, it's pointed away from you. So because not everything is 100% superposable or superimposable, these 2 molecules we would say would be non-superimposable. And they are in fact mirror images, as we could see from the very beginning of the slide. So these molecules are in fact enantiomers because they are non-superimposable mirror images of each other. Okay, so if you're still having trouble visualizing that, that's okay. You will continue to look at this a little bit later on, and hopefully it'll become a little bit easier for you. But right now, I just want you to just understand the strict definition of what enantiomers are, of these non-superimposable mirror images. Okay. Now, enantiomers have a special property, which is called chirality. And so because they have this special property of chirality, we say that the enantiomers are also chiral molecules. And chirality is nothing more than the property of an object such that they are non-superimposable on their mirror image. Okay, so you can give it a basically as an adjective for that property. So chirality. Achiral objects, so that A basically means not, so not chiral. So achiral objects are superposable or superimposable on their mirror images. That means you can have a mirror image of this molecule and everything perfectly lines up. One way of determining if a molecule is achiral or chiral is by looking for, to see if the molecule has, or the molecule of the object, it doesn't have to be a molecule, but to see if the object has a plane of symmetry. If a molecule does have a plane of symmetry, then the molecule will have to be achiral. Okay, so enantiomers, which are chiral molecules, they do not have a plane of symmetry. However, achiral molecules do. So for example, there's just a couple of examples here, these 2 molecules that are drawn here. So again, we've got 1 We've got 2. Again, this might be a little bit difficult to visualize at this point. You'll have to trust me though. So these 2 molecules, as I've written them 1 and 2, they're definitely drawn in a mirror image, right? So you can imagine a mirror plane here. So they're reflected perfectly. However, these molecules do in fact actually have a plane of symmetry through them, and therefore they would be achiral. So these 2 molecules, as I've written them as molecules 1 and 2, they're not in fact 2 different molecules. They are in fact the same molecule. So if you have a molecule that is superimposable on its mirror image, i.e. it's achiral, it's in fact actually the same molecule, okay? If the molecule is non-superimposable on its mirror images, following the exact definition of an enantiomer, then they are in fact 2 different molecules. Okay, well, we're going to talk a little bit more about this in a minute. So what they've done here is they've just basically rotated molecule, what I've numbered as 1 here by 180 degrees. You get this particular configuration, and then if you were to stack one of these 2 molecules on top of each other, then you would see that everything would perfectly line up. So they are indeed the exact same molecule. The mirror image might be a little bit difficult to see on that. So here's another example. We've got this molecule here, and the way it's drawn on the left-hand side, it's not immediately obvious that there's a mirror plane or a plane of symmetry in this molecule. However, if you take this carbon, the central carbon-carbon bond here, and you would do a rotation around that, and so effectively what you're doing is that OH group, which is pointed down and away from you, if you're going to rotate it up, and in doing so, it's now going to be pointed towards you, and you get this molecule. Well, it's the same molecule, you've just done a rotation, so it's just in a different conformation. We talked about conformations in the previous chapter. I hope you can see here that the plane of symmetry is much more obvious now. And the fact that this molecule has a plane of symmetry means that it is achiral. Okay, now if you had to determine whether a molecule was chiral or achiral by trying to find mirror planes in it all the time, this could get rather difficult for extremely large molecules, because you can have them in all kinds of different conformations and the mirror plane might not be obvious, and so on and so forth. Fortunately, there's another way, a much easier way of determining whether these molecules are chiral or achiral. And this is the concept of what we call chirality centers. So an atom, well, we're going to talk about atoms because we're talking about molecules, but if an atom, and typically understand that we're usually going to be talking about carbon, but it doesn't necessarily only limit it to carbon, but so atoms that are connected to 4 different groups can give rise to chiral molecules. And these atoms that have 4 different groups, they have a special name for them. And there's a lot of different things names that refer to the same sort of concept. So they could be called stereocenters. They could also be called asymmetric carbon atoms. They could also be called chiral centers. They could also be called stereogenic centers. So just understand that when you see those terms, that they all kind of refer to the same concept. So earlier, when we went through this exercise of determining whether those 2 molecules were enantiomers, non-superimposable mirror images, this was the molecule that we looked at right here. And we had determined that it was an enantiomer with the other mirror image of itself. But I just want to show you that you can look at this molecule very quickly and determine that it has what we call a chirality center, or chiral center, or stereogenic center. And I want you to focus in again on this carbon right here and ask yourself, what are the 4 things that it's attached to? It's carbon, it has a valency of 4, so of course it should have 4 different things attached to it. And if you look at this molecule, you can see that on the left-hand side, it has an ethyl group attached to it. And on the right-hand side, it has a methyl group. And then pointed down and towards you is a hydroxyl group. And of course, there's also a hydrogen atom attached to it that's not shown here, but so we have 4 different groups. We have a hydrogen, a hydroxyl group, a methyl group, and an ethyl group. So that particular carbon atom we would term as a chiral center. Now, just to show you some examples of how it doesn't always have to be carbon, here's an example containing sulfur. Okay, and so you can see that there's like an R group written there. R is just a generic way for chemists to say that there's just some group attached to there, and we usually give it either a number or it might be like a hash mark or prime, for example. So if you have R1 on one side and R1 on the other side, what they're saying is that whatever R1 is, it's the same group on either side. So in this particular case, they have R1 and they have R2, meaning that they're two different groups, whatever those groups are. They're just undefined. So that sulfur has an R1 group, it has an R2 group, it actually has a lone pair and an oxygen atom, 4 different groups, i.e. it would be chiral. You could also have, as another example, a nitrogen atom here, right? This is an ammonium ion, and an ammonium ion, it's a nitrogen atom that has no lone pairs and 4 bonds. And if those 4 bonds were attached to 4 different groups, then that ammonium ion would indeed be a chiral center. Okay. Now, just want to throw this out at you so that you're aware of this, but this concept of chirality is not only specific to, atoms that have 4 different groups. We see this also when we have restrictions around bond rotations. So this particular molecule that's drawn here is known as an alene. That's the functional group. And essentially what you have is 3 carbons in a line. So that's carbon 1, 2, and 3 here. And they're connected by 2 consecutive double bonds. Okay, that's what an alene is. And again, you have to take my word for this, but because of those double bonds, right, there's restriction of rotation around those double bonds, and this makes this particular molecule chiral. Okay. If again, it might not be completely obvious, and that's fine at this point, but if this molecule, if you had its mirror image of it, you would find that it would be non-superimposable on its mirror image, and therefore it would be an enantiomer to its mirror image. We can also see this property of chirality, not just with double bonds, but also with single bonds. And this is a little bit surprising because we know that we do have typically we have free rotation around single bonds. However, in certain molecules, that rotation isn't as free as you might expect because of for steric reasons, essentially. And here's a great example of this. This molecule is known as binol, and binol can indeed be is indeed chiral. And even though it has this single bond here, which I'm highlighting here and here, okay, there's a restriction of rotation around that carbon-carbon single bond, and it has to do with well, the bulk of this molecule, basically the size of it. And effectively, if you were to look at some of the hydrogen atoms on those rings, those hydrogen atoms would literally have to smash into each other in order to rotate around that bond. It doesn't want to do that, and so it doesn't rotate around that bond, and it gives rise to these different chiral molecules. So I'm not going to dwell on this. I just wanted to show you that we can have this property of chirality with molecules that don't just have 4 groups around it. There's other ways that this particular property can manifest itself. Okay. Now, I mentioned earlier how if you have stereoisomers, that they're going to have their own specific configuration. And so what we need here is a way of defining what that configuration is. And basically, this is now just an add-on to your nomenclature. And what we're going to do is we're going to use what's called the Kohn-Ingle prelog system to describe the absolute configuration of a chiral center. So it's a lot of words there, but it's just basically a way of describing one configuration versus another. That's strictly all this is. Okay, and so this particular system works for when we're dealing with atoms that have 4 different groups attached to it. Okay, so for the most part, the things that we'll be looking at. So in order, you want to follow these basically 3 simple steps in order to determine what we call the absolute configuration of a chiral center. Again, an atom or a stereocenter that has 4 different groups attached to it. So the first thing you're going to do is you're going to assign priorities to the 4 different groups attached to that stereocenter. And you can assign them however you want. I usually just use numbers 1 through 4. You can use A, B, C, D. It doesn't really matter as long as you're consistent and get to the correct answer. So the first thing you do is you label the 4 groups according to the priorities. Then, and this is extremely important, is you have to orient the molecule such that the group of lowest priority that you've assigned is pointing away from you, okay? Then what you want to do is you're going to trace a line from your first priority group to your second priority group to your third priority group, okay? You're just going to trace a line going from 1 to 3. And if you're going in a clockwise order, then you're going to assign the absolute configuration to that chiral center as R. It's just a letter, okay? However, if you trace this line 1, 2, and 3, and your line is pointing counterclockwise, we would assign the absolute configuration of that chiral center as S. So here's an example, okay? So we've got this molecule here, and they've given you the priorities. So we have priority 1 on the bromine, we have priority 3 on this methyl group, we have priority 2 on this oxygen atom, and then we have priority 4 on this hydrogen atom, okay? So that's step 1 has already been done for you. Now step 2, this is highly important. You have to have the molecule in such a way that the group of lowest priority is pointing away from you. Again, this is where dashes and wedges come in very handy. Notice that our group of lowest priority 4 is actually pointing away from us. That's why it has a dash. So I don't have to rotate or move this molecule around. The group of lowest priority is pointing away from me. Okay, so that's step 2 done. Now all I need to do is just trace a line from 1 to 2 to 3. It doesn't matter if you go through other numbers. It makes no difference at all. All you do is you start at 1, and I'm just going to start drawing, and I'm going to go towards 2. Okay? Now, you want to go in order. You want to go from 1 to 2, not 1 through 3 to 2, for example. So to go from 1 to 2, I need to go this way. And notice that I'm going clockwise. And because I'm going clockwise, I would say that the absolute configuration of this stereocenter, and this is the stereocenter here because it's got 4 different groups attached to it, the absolute configuration for the stereocenter would be R, okay? Now, if we had this other molecule here, and again, the priorities are the same that are given to you, notice that your group of lowest priority is still pointing away from you. And if you trace your line now from 1, 2 to 3, so again, I'm starting here and I'm going 1, 2, and I go to 3. And again, just ignore 4 at this point. You're just going from 1 to 2 to 3. Notice I'm going counterclockwise, and therefore the absolute configuration of this particular chiral center would be S, okay? And it's simple as that. There's 3 steps to it, and that's all you need to do. Of course, how do you assign priorities, right? In those examples, the priorities were given to you. You're going to need to be able to determine what the priorities are. And so what we're going to do is we're going to use the Collin-Ingle-Prelog system of assigning priority. And basically the priority is determined based on the atomic number of the atoms that are directly attached to the stereocenter itself. And basically atoms with higher atomic numbers get higher priority. It's simple as that. And then the atom with the second highest atomic number is assigned a second priority, and so on and so forth. So basically, you're just looking for the highest atomic number, and then you go on from there. Now, there's a couple other rules to this, which we're going to look at in a little bit more detail. So if you have atoms with the same atomic number, but they are different isotopes of each other, then the the heavier isotope gets the higher priority. So for example, if you were comparing a carbon-13 versus a carbon-12, carbon-13 would have a higher priority than carbon-12 because it is the heavier isotope. Simple as that. Oftentimes you're going to run into a situation where the priorities are tied. In that particular case, then you need to move out to the next set of immediately adjacent atoms, and then away from the chiral center, and then you need to list those atoms that are directly attached to it in decreasing atomic order, and you're looking for the first point of difference. I know there's lots of words there, and that sounds all confusing. We're going to look at an example of that as well. The last couple of things here is we need to have a system, a way of looking and how we're going to interpret multiple bonds. We're going to look at that in a different video. And then finally, if ever you have to assign a priority to an electron pair, so a lone pair, it would get, it has an atomic number of 0. We're just defining that as 0. Let's look, so this is where we're going to finish. We're just going to look at a way of showing you how we assign priorities here, okay? So let's start off at this first one here, this first molecule here. This has been the same molecule we've been looking at for the most part in this particular, in these examples. And so again, I'm just gonna highlight the chiral center here. And here they've explicitly drawn in the hydrogen atom, just so that we can see the 4 different groups, right? We have the ethyl group, we have a methyl group, we have a hydroxyl group, and of course we have a hydrogen atom. So what we need to do is assign priorities. Now, what you do is, and again, I've highlighted the chiral center. That's what I've circled in green, okay? You want to look at the atoms directly attached to your chiral center. Not the group, but the atom directly attached to it, okay? So what do I have directly attached to this? I have a hydrogen atom, I have an oxygen atom, I have a carbon atom, and I have a carbon atom, okay? Those are the 4 groups. And what I'm going to do here is I'm just going to redraw my chiral center, okay? And I'm going to put in the priorities as we go along here. So I'm looking for the group with the highest atomic number. And again, you can just get this directly off the periodic table. So I have oxygen, carbon, carbon, and hydrogen. Oxygen has the higher atomic number out of those 4 atoms. So oxygen gets priority number 1, okay? Now, carbon has the second highest priority of those 4 groups. However, there are 2 carbon atoms. So I can't yet determine the tiebreaker between those two atoms because they're both identical at this point. However, I do know that that hydrogen atom has the lowest priority. So I know that it's going to get priority 4. Okay. What I need to now determine is I need to find some way of finding a tiebreaker between those 2 carbon atoms so I can assign priorities 2 and 3. And that's leading us to this point right here. So let's go through that in a little bit more detail. So let me clean up my structure here. Okay. So you have to, so at this point here, we're at this carbon atom here and this carbon atom. And we're only focusing in on those 2 carbon atoms. And so what we need to do now, as it says in the instructions, is if the atoms are tied in priority, which we're at right now, then you move out to the atoms immediately adjacent to the ones directly attached to the chiral center. And then you're going to list them in decreasing atomic order. Okay, what does that mean? So I'm looking at this carbon and the other carbon atom. What is attached to that carbon on the left? I have a hydrogen atom, I have a hydrogen atom, and I have another hydrogen atom. It's a methyl group, okay? The hydrogen atoms just are not shown, but they are still there, okay? What is attached to the other carbon atom? Well, here there's a hydrogen atom, and then the other atom here is carbon, okay? Now, there's atoms attached to that carbon atom that I just drawn, but that's what's attached to this carbon atom, okay? And what you want to do is basically those atoms I just wrote in, you want to list them in decreasing atomic order, atomic number order, right? So that's what they've done here, okay? So all they've done is they've listed here 3 hydrogen atoms and they just went in decreasing order. So they're all the same. So it's just hydrogen, 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 okay? And then the other carbon, what was attached to it? Well, it was hydrogen, hydrogen, and carbon. Just list them in decreasing atomic order. So the carbon goes first, and then hydrogen, and then the hydrogen. Now what you do is you compare the 2 atoms at the top of your little list that you've got there, okay? So here's our list here, and then you got the 3 hydrogens on the other side. And you're looking for your first point of difference. And the first point of difference is right there at the beginning. It's hydrogen versus carbon. Carbon has a higher atomic number than hydrogen, and that tells me now then that this group here has to have a higher priority than the other group. So this is priority 2, and that is priority 3. And that's what they've drawn right here. Okay. Now, once you've assigned your priorities, then of course you need to orient the molecule so that the group of lowest priority is pointing away from you. Fortunately for us, the group of lowest priority is already pointing away from us. And that's group 4, which is the hydrogen atom. Now all I need to do is trace my line. So if I was doing it up here, so 1 to 2 to 3, notice I'm going clockwise. So the absolute configuration of this particular molecule would be R. Okay. Let's look at one last example before we close out here. So we're looking at this molecule down here. Again, I'm just going to redraw the chiral center. What do we have attached to this chiral center? I'll tell you right now that chiral centers are always usually indicated by a little asterisk. Okay, so that's what I'm trying to draw there. So that's the chiral center. You ask yourself, what is directly attached to that chiral center? There's an oxygen atom, there's a carbon atom, there's a hydrogen atom, and there's a deuterium. Okay, so which one has the higher atomic number? Well, of course, oxygen does, so that gets priority number 1. Carbon has priority number 2. And then now we are looking at the difference between two isotopes, hydrogen and deuterium. Deuterium is an isotope of hydrogen. And deuterium is a heavier isotope than hydrogen. So this should get priority 3, and this should get priority 4. Okay. Now, here's the tricky thing. Okay. We've got our priorities listed here now, but I cannot trace my line because you'll notice, and hopefully it's obvious here, but my wedge, okay, is priority 4. Notice that my group of lowest priority, number 4, is not pointed away from me, okay? And so what I need to be able to do now, and this is the tricky part, is to be able to reorient the molecule. I can't break any bonds, but I could flip it or rotate it or something like that, such that group of lowest priority is pointed away from me. And I think the easiest way of doing that here would be to, and I'm just going to redraw the chiral center, okay? And I want you to imagine, so I'm just going to put down here, here's priority 1 up top. And you can see how this is kind of a tripod. And imagine a hand coming down and grabbing that atom 1, okay? And so so the rest of the other 3 bonds that are kind of pointed downwards, they're kind of free to rotate, okay? And what I want you to do is imagine doing a rotation here, okay? So basically, this group is going to rotate here, this group is going to rotate here, and this group is going to rotate there, okay? Hope you can see that. Again, I'll show some examples of the model kit during our meeting. So I'm going to just keep the bonds there because the group, the dash, of course, still has to be pointing away from you. But what I want you to imagine is by rotating here is that 4 is going to go where the position 3 is, 3 is going to go to where position 2 is, and 2 is going to go where position 4 is. Okay, so I'm going to have 3, I'm going to have 2, and I'm going to have 4. And notice by rotating it this way strategically, notice now that my group of lowest priority is pointed away from me, okay? Now I can go ahead and trace my line. I'm going to trace from 1 to 2 to 3, and notice I'm going clockwise, and so again, this would be given a priority of R. Okay, so that's the start of how we assign priorities. We're going to do some examples of this later on in a meeting, but I'll leave it at this point, and then we'll get back to this this concept and continue in the next video.
In today's video, we're going to continue talking about the different aspects of stereochemistry. We left off last time talking about the Kohn-Ingle prelog substituent priority system, if you will. And we looked at how we can use that to assign priorities to the 4 different groups at a chiral center in order to assign its absolute configuration. There's one other aspect of this that we need to look at, and that is how we can interpret multiple bonds. So I'm specifically looking at this point here. So as it says here, when you're trying to assign the priorities and you come to an atom that is involved in a multiple bond, we need to first, I'll call it, unpack the multiple bond in order to then look at it so we can assign its priority. And what I mean by unpack is we're literally just going to take multiple bonds and interpret them as that same number of single bonds. So we're going to basically convert pi bonds into sigma bonds just for the process of assigning priority. Let's look at an example of this. Here we have a molecule and the chiral center is right here. As I said, typically we will put an asterisk beside chiral centers to identify them. And if we look at what's directly attached, the 4 atoms that are directly attached to this chirality center here, we have an oxygen atom. We have, so again, if we look at this structure here, we have this oxygen atom here, we have this hydrogen atom, this carbon here, and this carbon here. So we can assign priorities 1 and 4 immediately because oxygen has the highest atomic number out of those 4 atoms, and so it gets priority 1. And then hydrogen has the lowest priority out of those 4, and therefore it gets priority 4. The other 2 atoms, which are both carbon, are tied at this point. Okay, and so we're going to need to look beyond those 2 carbon atoms in order to break the tie. However, you'll notice that the carbon atom on the right-hand side is involved in a double bond with oxygen. So before we can break the tie in terms of priorities, we need to reinterpret that carbon-oxygen double bond into single bonds, okay? And this is what they're showing you over here. So as it says here, I want you to look at both. I want you to look at both atoms involved in the multiple bonds separately, and all we do is we ask ourselves. So let's look at the carbon of the carbon-oxygen double bond. It's involved in a double bond to oxygen. So all we're going to do is we're just going to take that carbon, and instead of having a double bond to oxygen, we're just going to give that carbon 2 single bonds to oxygen, and that's all we're going to do. And that's what they've done over here. So here's the carbon atom in question. And notice now that it has 2 single bonds to oxygen. That's just the reinterpretation of that carbon-oxygen double bond. Now, you have to look at both sides. So the carbon has a double bond to oxygen, but that oxygen atom is also double bonded to the carbon atom. So that means that the oxygen should have 2 single bonds to carbon. And so that's this oxygen atom here, and this is why there was an extra carbon atom here. So now it has 2 single bonds, so highlight here and here, attached to carbon. And so by taking the multiple bond and expanding it out into the requisite number of single bonds, we can now go ahead and try and determine the priorities. So down here, we have the molecule redrawn, so to speak, with the double bond unpacked. And if you remember, we're at these 2 carbon atoms at this particular moment, and we need to try and find out a way of breaking the tie in order to assign the absolute configuration. So as we learned in the previous video, what you need to do is ask yourselves what atoms are directly attached to those carbon atoms, list them in decreasing atomic order, and then look for your first point of difference. So this carbon atom on the left is attached to an oxygen, and of course there's a hydrogen atom which was not drawn, which I've just put in. And so this is why they've listed this here. So we have oxygen, oxygen, and then hydrogen. Again, listing them in decreasing atomic order. If you look at the other carbon atom here, or on the right-hand side, it also is attached to oxygen, oxygen, hydrogen. And that's what they've listed here. So you start at the top of your list and you make your way down. And of course, if we do that, we'll see that we are still completely tied. And so we haven't resolved, we haven't been able to resolve this just yet. So when you run into a tie, you always move 1 step away to the next atom and then reevaluate. So we were at this carbon here and this carbon here. And now we need to go back 1 more step away from the chirality center and reassess. Now notice in both of these situations, the left-hand group and the right-hand group, that I have a choice of which way I'm going to move back. I can go to, for example, I could look at this oxygen, or I could go and look at the other oxygen. Essentially, what you want to do is choose a path, see if you can resolve your issue. If you cannot, then you can go and look at, and go through the other path. So for example, what they've done here is they've decided to step back to these two oxygen atoms that I've underlined. And then again, we go through the same process. What is attached to the oxygen atom on the left? Well, it is a carbon atom right here. So that's what they listed there. And that's all that's attached to it. What is attached to this oxygen atom on the right? Well, it's also a carbon atom, and that's what they've listed here. And again, it is still tied. So in this case, what we're going to do then is we're going to go back to that carbon atom just before it, and then we're going to go to a different atom around. This usually happens when you're dealing with rings. So again, remember, we were here, and instead of going to that oxygen we just looked at, we're going to look at this oxygen atom here, and over here we'll look at this oxygen atom here. And again, we ask ourselves, what's attached to this oxygen atom here on the left? Well, it's a carbon atom. There it is. So they've listed the carbon atom. What is attached to this oxygen atom? Well, there is nothing attached to that oxygen atom. So that has a priority of 0 or nothing. Now we have a point of difference. Carbon has a higher priority than nothing. And so this whole group here will get the second priority. So going back to our original molecule over here, we'd already determined priorities 1 and 4. They're still there. And now we've determined the second and the third priority. And they're listed there. So that's the first point that we need to do when we're trying to assign the absolute configuration, is to assign the priorities. Once you have once you've assigned the priorities, then recall you need to put the group of lowest priority pointing away from you. And this is why they've taken the molecule and they've done a rotation through the plane of the paper or the screen, so that your group of lowest priority, the hydrogen in this case, is pointed away from you. Once your group of lowest priority is pointed away from you, then you can trace your line from 1 to 2 to 3. And you'll notice that I am going clockwise, and therefore they've assigned this a priority of R. Okay. I want to take a few moments now and look at drawing enantiomers. This is an incredibly important skill that you need to master. And there's several different ways of approaching this, and that's what this we're trying to show you here in the next few slides. If you recall, enantiomers are non-superimposable mirror images of themselves. So for example, if you had this molecule here given to you and I'd asked you to, I want you to draw its enantiomer, if you recognize that there's a chiral center there and they've shown you that it's actually in fact S, so chiral center is there, then one way of approaching this is to imagine just literally drawing its mirror image. And so they put this dotted line here to represent the mirror, and then they've drawn its mirror image. Okay. And by drawing its mirror image, then you've now drawn its enantiomer. And of course, if the one enantiomer, the first one we started with, was S, then of course its enantiomer must be R. Notice they drew the mirror as a vertical line. You could have easily have drawn the mirror as an horizontal line. So again, if we would have started with this molecule, you could have drawn this as an enantiomer. So it doesn't matter as long as it's its mirror image, and therefore you'll get its enantiomer. That's one way of approaching it. This method works well, especially if molecules are fairly small, but you can imagine if the molecule is fairly large and a little bit more complicated, say a bunch of rings, fused ring systems, it actually gets a little bit more difficult to redraw its mirror image. It's not always so obvious. With small molecules, not so bad, but with large molecules, it could be more difficult. Another approach to doing this is to invert the configuration at the chiral center, okay? And so what we can do is, and usually the easiest way of doing this is by basically changing a dash and a wedge. So for example, we're still looking at this molecule here. This was the same one in the previous slide when we were drawing mirror images. But in this case, we're not going to draw a mirror image. All we did, I want you to notice the difference here, is that we changed this wedge that was originally drawn to the dash, okay? So notice that everything else remains the same. So this is why they've written down this, that the backbone, the zigzag of the backbone remains identical. All we've done is literally just change the type of bond. And we're not just changing the bond, of course, we're changing the three-dimensionality of this molecule, okay? Now, the way it's drawn, these two molecules do not look like mirror images. So it might not be necessarily obvious at first that these molecules are enantiomers. But if you just remove, or if you just change that dash to a wedge or a wedge to a dash, you have to understand the consequences of this. And this is literally inverting the configuration. So if it started off as S, as in this case, and then you take away the wedge and add a dash, you've now created the R enantiomer. I want to talk a little bit more about this idea of switching groups and changing bonds. This is a very powerful method of really understanding the stereochemistry in a lot of different contexts, and I'll try and point this out as I go along. But the first thing you need to do is convince yourself that convince yourself of switching these groups and the implications that it actually has. So it says here, pay attention to the implications of switching two groups at a chiral center. So the first thing I want to do here is I want to switch two groups, and any two groups, and this will interconvert the configuration. So again, let's just remind ourselves of what we just talked about before. If we take this particular molecule, which they tell us is S, and if I just change the wedge into a dash, I've done an invert. So I inverted the configuration, okay? I've gone from S, in this case, to R. Okay, another way of doing this is by switching two groups, okay? So again, we're gonna start off with the same exact molecule as we have before. And now we're not changing the type of bonds here. All we are literally doing is moving two groups. So we're literally kind of breaking bonds in this case, but this is just a little mechanical exercise. We can't actually break the bonds, but by taking, for example, I'm going to take that bromine atom and I'm going to take it off of that bond, that the wedge that it's attached to, and I'm going to attach it where the methyl group is. So what I'm literally doing is I'm switching, in this case, a bromine atom for the CH3 group. I want you to see over here, after I've done the switch, that the carbon skeleton and the wedges and all that is identical. All I've done is I've moved the position of the methyl group and the bromine atom, okay? We call that one switch or one exchange. And I want you to be clear on the implications of when you do one switch at a chiral center, what happens. And the implication is that you invert the configuration. So notice how we started off here as S, and then when we switch the bromine atom and the methyl group, we now have a configuration of R. So this is another method of writing out an enantiomer of something. So if you're given a molecule and you're asked to draw its enantiomer, what you can do is switch two groups, and this will give you its enantiomer. Okay, so that's the first thing that we need to understand, is that anytime you do one switch, take two groups and swap them at a chiral center, you will invert the configuration. If you're not convinced of this, I would suggest that you look at this first molecule here and literally assign the priorities and assign the configuration. You should also get an answer of S. And then do the switch like they've done here. And when you've done that, then assign the configuration, assign the priorities so that you can assign the absolute configuration, and you should see that it gets R. So convince yourself that this is the case when you do one switch. Now what I want to do is I want to take this one step further. I want to take an original molecule, and I'm not going to do one switch. I'm going to do 2 switches, okay? Or as it says here, 2 sequential exchanges. So I'm going to exchange 2 groups, and then I'm going to exchange 2 more groups again from the original molecule. And I want us to understand the implications of that. So again, we're going to start off with the same exact molecule that we have been, okay? It's still this, 2-bromobutane, and it's the S configuration. And we're going to switch any 2 groups. So again, what they've done is they switched the bromine atom and the methyl group to give this one here. And we already saw that in the slide before. So we know when we do one switch, we go from S to R or R to S. We do an inversion of the configuration. Okay. However, now what I want to do is I want to take the second molecule after we've done one switch, and I want to do another switch. I'm just going to clean up my structure. And again, you can switch any 2 groups. You could switch the bromine and the methyl group back again. You would obviously get back to this structure, which would be S. Okay, but you can switch any 2 groups. And the groups that they switched in this example was now they've switched the bromine and the ethyl group. Okay, so they switched this and this group here. So that's what they get over here in the end. So we started off with this molecule here, and we did one switch and ended up with the R configuration. And then when we do a second switch, we get back to the original configuration of the molecule. And if you can understand this concept and just accept it, and this is what actually happens, then this is a very powerful method of assigning configuration and just understanding what's happening with these different molecules. And again, like I said, I'll try and point this out why this is important as we go along. So one switch will change the absolute configuration. 2 consecutive switches will get back the original configuration of the molecule. Let's take an example and let's look at how this can be powerful. Okay, so here's a molecule and you're asked to assign the absolute configuration of this molecule. And if you look at this molecule here, so the chiral center is right here. Okay, and what is attached to this chiral center? We have an oxygen atom, we have a carbon atom, we have another carbon, and we have a third carbon atom. So we know that oxygen has a higher atomic number than carbon. So we know that that oxygen gets priority 1, but now we have these 3 carbon atoms that are tied. Okay, so we need to be able to determine the difference between them. And so you'll also notice, because we're dealing with cyanide here, our nitrile functional group, which is a carbon-nitrogen triple bond, notice here that they're expanding this out or unpacking the multiple bond. So again, just to reiterate, this carbon atom here has a triple bond to nitrogen. We're just going to reinterpret that as that carbon should have 3 single bonds to 3 nitrogen atoms. And that's what is here. So this carbon here now has 1, 2, 3 single bonds to nitrogen. That's us unpacking that multiple bond. But again, the multiple bond is attached to 2 atoms, not just 1. So that nitrogen atom should have 3 single bonds to carbon. And so here is the original nitrogen atom here. I'll just circle it. And you can see it has 1, 2, 3 single bonds to carbon. And so this is the unpacking, if you will, of that particular functional group that had a multiple bond. So they've redrawn that down here. And now what you do is, of course, we're comparing these 3 carbon atoms. So this carbon, and of course, this carbon here. And what we're going to do is, for each carbon atom, we're going to look at the atoms that are directly attached to it and list them in decreasing atomic order. So as they pointed out here, on this carbon on the left, it is attached to a carbon atom and 2 hydrogen atoms. So they've listed them in decreasing atomic order. The carbon atom on the right is essentially a methyl group, so it has 3 hydrogen atoms attached to it. And this carbon atom up top, which we just unpacked, so to speak, is attached to 3 nitrogen atoms. And they're listed here. And then, of course, we're lucky in this sense because at the very top of our little tables here, of course, we can differentiate now between all 3 of those groups. Nitrogen has a higher atomic number than carbon, which has a higher atomic number than hydrogen. And so that's why this group here gets priority 2, this one gets priority 4, and this one gets priority 3. Okay? So just moving down here. So now this is the molecule that we started with, and now they have the 4 priorities listed. Okay? And again, now in order to determine the absolute configuration, before we trace our line from priority groups 1, 2, and 3, remember that the group of lowest priority must be pointed away from us. Now, how do we do that? Well, if you're very good at looking at that molecule and rotating it in your mind and still being able to see where the priority groups are, then by all means, you can do that. However, this opens yourself up, I think, to making mistakes really easy. And so this is where understanding, if you do 1 and 2 switches, understanding the implications of that can be very, very powerful. I don't know what the absolute configuration of this molecule is right now, but whatever it is, okay, I don't want to change the absolute configuration. I want to try and determine what its absolute configuration is. I'm just going to redraw this molecule so that I can have the group of lowest priority pointing away from me. And I'm going to do this by doing 2 consecutive switches. Okay, so literally what I'm going to do is my first switch is going to be to switch groups, well, what's called priority 4 and priority 1, because if I do that, that methyl group, which is priority 4, is going to be at the dash. So again, notice I'm not changing the bonds. I'm just changing the groups attached to those bonds. So when I do this switch, now I end up with this, okay? And now notice that my group of lowest priority is pointing away from me. However, again, I want to look at the absolute configuration of this particular molecule. So I have to do 2 consecutive switches to be dealing with the same molecule. So I've done 1 switch, switching 1 and 4. Now I can switch any other 2 groups. I'm not going to move 4 because 4 is where I want it. So I can switch any other 2 groups. So in this particular case, they switched groups priority 1 and 2, right? So they have that listed here, and now they generate this structure here. Okay, and notice that our group of lowest priority is pointing away from us. Now I can trace my line. I'm going from 1 to 2 to 3 in a clockwise fashion, and therefore I know that this particular configuration is R. This idea of doing 1 and 2 switches is very powerful because it doesn't allow me, I don't have to mentally do these acrobatics in my mind to rotate the molecule and be able to draw it perfectly. Because again, these are 3-dimensional structures, and it can be a little bit difficult to redraw them so that the group of lowest priority is pointing away from you. Typically what I do is whenever I have my priorities, I will always redraw my chiral center and only my chiral center. And I will just put in my priorities that I determined. And if my group of lowest priority is not pointed away from me, I am going to redraw the chiral center. And I always redraw the chiral center exactly as it is. So I literally cut it out of the molecule. And now I just do 2 switches, 4 and 1, and I could even do 3 and 2. It does not matter. Okay, I did 2 switches. Now I can trace my line, and this gives me an absolute configuration of R, which it should have been because that's what we just determined it to be. Okay, here are a couple molecules. So for each of these molecules, you have to first identify the different stereocenters, and then I want you to assign their absolute configuration. We'll be looking at that during one of our live meetings. So I'll leave those problems for you guys to just look at, and we can look at that later. Now, today what I want to finish on is talking about another type of stereoisomer known as distereomers. So we've already looked at enantiomers, and now we're going to look at this new concept called distereomers. So far, all the molecules that we've looked at have only contained 1 chiral center, okay? However, molecules can contain multiple chiral centers. There's nothing saying that a molecule can't have 3 or 5 or even 20 different chiral centers. And whenever you have multiple chiral centers, then now you have the opportunity of creating a new type of stereoisomer, which is called a distereomer, okay? And the definition of a diastereomer is right here. And you need to pay special attention to this definition, but also how it's subtly different from the definition of an enantiomer. So diastereomers are stereoisomers that are non-superimposable or non-superposable, non-mirror images of each other. Recall, enantiomers were stereoisomers that were non-superimposable on their mirror image. Diastereomers are non-superimposable, non-mirror images of each other. So there's a subtlety here, okay? And we'll look a little bit more at this in a minute. Now, so you can have a molecule with multiple chiral centers that is a diastereomer to another molecule with multiple stereocenters. But diastereomers also can have their own enantiomers to them. And another concept you need to understand is that when you have a molecule with multiple chiral centers, so let's look at this molecule here. I'm going to number this as 1, and this is 2. Okay, if you look at molecule 1 has 2 chiral centers, and they've given you the absolute configurations of both of those. So there's the carbon that is directly attached to the hydroxyl group is a chiral center, and the carbon that is directly attached to the amine is also a chiral center. And in this particular molecule, the 2 absolute configurations of these chiral centers are R and R. Okay, and notice here that they've drawn this molecule beside it, molecule 2, as I've labeled it, and it's mirror image. Okay. So these 2 molecules, and you have to take my word for it if you can't see this, but they are non-superimposable mirror images of each other. And if they're non-superimposable mirror images, that is the direct definition of an enantiomer. And so these 2 molecules are enantiomers to each other. Okay. Now, one of the things I want to talk about when you have molecules with multiple chiral centers, and you're looking at its enantiomer, one thing you have to understand is that every single chiral center in a molecule must completely change its absolute configuration in order to be its enantiomer. So what do I mean by that? So there's a chiral center here, and that same chiral center is here on molecule 2. And I want you to see that the absolute configuration changed. In molecule 1, that chiral center was R. In molecule 2, that chiral center was S. Now, if you look at the second chiral center, I'll just identify that with an X, for example. And then you look at the chiral center in molecule 2, that same chiral center in molecule 2. Again, notice that the absolute configuration completely changed. Okay. If it was R in the one enantiomer, then in the other enantiomer, it has to be S. Okay. So another way of looking at this, let me just imagine there's some imaginary molecule that has 4 chiral centers, R, R, S, and R. Okay. Again, it doesn't matter what the molecule looks like. Let's just assume that those 4 chiral centers are R, R, S, and R. If I was looking at its mirror image, then those same chiral centers would be S, S, R, and S. Okay. So for an enantiomer, you must always invert the absolute configuration at every single chiral center in order to have the enantiomer. Okay, and I could do this with 100 chiral centers, I can do this with 2 chiral centers, I can do this with 13, it doesn't matter. As long as they all change their absolute configuration, you will get its enantiomer. Now, where do diastereomers come in? Well, if you only invert some of the stereocenters in a molecule, then this will produce diastereomers, okay? So let's go back and look at these 2 molecules here that I've labeled 1 and 2, and we're gonna go down here. So this was molecule 1, and this was molecule 2, okay? That's those same 2 molecules as they're drawn up here. Now, notice, and let me call this 3, and this molecule 4. Notice molecule 3, okay? And again, they've given you the absolute configurations here. Okay. So again, you have to be able to compare the same chiral centers though. So you gotta be very, very careful, right? So this chiral center here with this OH is right here, and in this bottom molecule, it's right there, okay? And notice how in molecule 1, the two chiral centers were R. Let's look at molecule 3. In molecule 3, again, they've given you the absolute configurations. Notice that the absolute configurations are SR, okay? Now, molecule 3 then is a diastereomer to molecule 1 because not all of the chiral centers have completely inverted their configuration, okay? So you can see that this R switched to an S, that changed, but this R remained the same. So again, in order for it to be an enantiomer, all of the chiral centers have to invert their configuration, okay? If it was the exact same molecule, then none of the chiral centers would be inverted. And if only some of them change, then it is therefore a diastereomer. I'm just gonna clean up the structure a little bit. And this might not be obvious, but if you were to look at molecules 1 and 3, they are in fact non-superimposable, non-mirror images of each other. Therefore, that's the exact definition of a diastereomer. But one way of identifying diastereomers is by looking at the absolute configuration of these particular, of the different chiral centers, okay? Now, that'll only work if you know the absolute configurations of the chiral centers. But again, I want to go back to this concept that I was talking about earlier in terms of 2 switches and 1 switches and understanding those implications. That can also be very powerful here. And had these molecules 1, 2, 3, and 4, had they not had their absolute configurations written down, I would still be able to, within seconds, determine whether they were enantiomers or diastereomers, okay? And I want to show you how we can do this, again, by understanding whether you're doing 1 or 2 switches at a particular chiral center. So I want you to look at molecules 1 and 2, and I want you to look at the different chiral centers. Let's start with the one that is directly attached to an amine. So let's compare this chiral center and this chiral center. And I want you to look at it, that chiral center in molecule 1, and then I want you to look at that same chiral center in molecule 3, and I want you to ask yourself, has there been any switches at any of those groups at that particular chiral center? And so what I mean by that, notice that there's a methyl group here on the end, and it's on the same group in molecule 3 as well. Notice there's an amine on the wedge, in molecule 1 as well. Notice that you've got this alcohol moiety sticking off the end in molecule 1. It's also sticking off the end in molecule 3, I should say. And finally, there is a hydrogen atom which is not drawn in this structure, but they would both of them in molecule 1 and 3, those hydrogen atoms would be attached to a dash. Remember, tetrahedral carbon atoms have 2 lines, a wedge, and a dash. I see 2 lines and a wedge, so therefore that bond that's not shown to the hydrogen must be a dash. What I'm getting at is that in this particular chiral center, there's been literally no switches. It's identical. And so if I know that the top in molecule 1, that chiral center is R, then I know nothing has changed. There's been no switches, and therefore the chiral center in 3 must also be R, okay? Let's look at the other chiral center. So now I'm looking at the one attached to the hydroxyl group in both molecules 1 and 3. If you do a quick scan, I noticed that the dash, which was attached to the hydroxyl group in molecule 1, is now, sorry, the wedge in molecule 1 attached to the hydroxyl group is now a dash in molecule 3. And recall when we were looking at drawing enantiomers, There were several different ways of doing that. One of them was literally by switching the bond. This really represents one switch. So let me just redraw this here, and I'm going to include the hydrogen atom. Okay. And so we had an NH2 here and an R group. Okay, so I've just redrawn molecule 1. And I want you to look at that. And so you've got your OH, your hydroxyl group, your hydrogen, your methyl group, and then of course that amine moiety. Now in molecule 3, I'm going to redraw the molecule and I'm going to include the hydrogen atom. And there it is there. Now I hope you can see that going from molecule 1 to molecule 3, there's been one switch. The hydroxyl group and the hydrogen atom they've switched places. They've done one switch, okay? And so and again, understanding the implication of that, when you do one switch at a chiral center, you invert the absolute configuration. So if it was R on top, and it was, then therefore I know that at the bottom here, this must be S. So again, this is another way of understanding how one or two switches can be a very powerful way of really understanding what's going on with these molecules. Okay, so we've compared 1 and 3. I hope you can see if you look at molecules 2 and 4, you'll see that not all the chiral centers have switched, and therefore they're distereomers. You can even do other cross relationships. So for example, 1 and 4 are also diastereomers. 2 and 3 are diastereomers. Now, 3 and 4, because they're mirror images of each other, are enantiomers, and 1 and 2 are enantiomers. But all the other cross relationships will be diastereomers. Now, we're just going to finish on this last section here. And a question might come up about, well, how many stereoisomers should I expect to see? How many enantiomers and diastereomers are there? Well, fortunately, we have a way of determining not the exact number, but we can know what the maximum possible number of stereoisomers can be. And that is by using this very simple formula, 2 to the power of n, where n is equal to the number of stereocenters. So in this example that we were doing above here, let's just take one molecule. Let's look at molecule 1. Molecule 1 has 2 stereocenters. So by plugging that into our little formula here, so 2 to the power of 2, and that's what they're showing you here. So 2 to the power of 2 gives us 4. And that's telling us potentially the maximum number of stereoisomers there are for this particular molecule. And this particular molecule does indeed have 4 different stereoisomers, as we'd numbered them previously, 1, 2, 3, and 4. Okay. And then being able to see the relationship between those 4 different molecules is also very important, which we just spent a little bit of time doing. I just wanted to reiterate that this formula only predicts the maximum number, because for some compounds with multiple chiral centers, they'll produce configurations that are actually identical molecules. So you might not necessarily have 4 stereoisomers, you might actually have less than that. And that's something that we're going to talk about in the next video. In today's video, we're going to finish talking about stereochemistry. We last left off, we were talking about diastereomers, and we also finished by talking about the maximum number of stereoisomers that can be predicted for a given compound, depending on the simple formula of 2 to the power n, where n was equal to the number of stereocenters. And we finished by emphasizing how that this can only predict the maximum possible number of stereoisomers, because sometimes certain configurations, as it says here, will produce identical molecules and therefore actually will reduce the actual number of stereoisomers. And so let's look at that now. When you have a molecule that only contains one stereocenter, it will always be chiral. and it'll have a non-superimposable mirror image, or said differently, it'll have an enantiomer. So whenever something has one chiral center, it is absolutely chiral, and it can have two possibilities. It could have an enantiomer. However, molecules that contain more than one stereocenter, they're not always chiral, and that's really what we want to explore right now. If you look at this molecule, or these molecules, I should say, to the right here, so let me go ahead and label these. So we have these 4 molecules. And if we just focus on molecule 1, you can see that there are 2 stereocenters, and then we can label these with asterisks here and here. They've already given you the absolute configurations of those 2. And you look at that, and so this molecule contains 2 stereocenters. So if we plugged it into our little formula up here, you would see that 2 to the power 2, it would predict a maximum number of 4 different stereoisomers. And we would expect this molecule, if we looked at the 4 different stereoisomers, to look like these molecules numbered 1 through 4. However, if you really pay attention to molecules 3 and 4, the way they're drawn, it looks like they are indeed mirror images of each other, and they are mirror images of each other. But they are not enantiomers, because again, the definition of enantiomers are non-superimposable or non-superposable mirror images. These molecules are definitely mirror images, but they are also superposable, meaning that they are identical molecules. And so here's a case where you have a predicted maximum number of 4 different stereoisomers, but the actual number is 3. So let's look at these compounds in a little bit more detail to see if we can understand why those 2 molecules were identical. So those 2 molecules, which are in fact 1 because they're identical, these are called meso compounds. And these are molecules that contain more than one stereocenter, but they have a superposable or superimposable mirror image, and therefore they become identical. Okay. An easy way of seeing molecules or seeing what we call these meso compounds or identifying them is looking for a plane of symmetry or a mirror plane in the molecule. This may or may not be obvious depending on how the molecule has been drawn. This concept is very similar to polarity. So for example, you can have a molecule like carbon dioxide, which has a central carbon atom, and it is bound to it has 2 double bonds to 2 oxygen atoms. Those carbon-oxygen double bonds are definitely polar. So here's a molecule, carbon dioxide, that has polar bonds, but yet overall the molecule is non-polar. This is sort of the same concept here. Just because a molecule has more than one chiral center doesn't necessarily mean that it will be a chiral molecule. And this is because we have this concept of meso compounds. Let's go back and look at compounds 3 and 4 here. So let me relabel these. Here was 3 and here was 4. They've redrawn them here. And what they're doing is they're just doing a little bit of a rotation. So they're rotating in the plane of the screen. So they're taking molecule 3 and they're rotating it 90 degrees counterclockwise to generate this particular conformer, as you can see. And then they've also taken molecule 4 and they've rotated it clockwise within the plane of the screen to generate this one here. And if you literally were to pick one of them up, so let's just say we take 3 and pick it up and literally sit it on top of 4, everything would be completely lined up. So we would say that it would be superposable or superimposable, as I like to say. Meaning that they are identical molecules. Again, to be an enantiomer, it has to be non-superimposable mirror images. These are superposable mirror images, which also mean that they're identical molecules. Now, this may or may not be obvious. Again, it just depends on how well you can sort of visualize these molecules in 3-dimensional space. However, like I said, meso compounds can also be identified because they'll contain a plane of symmetry. And the way this molecule, molecule 3 and 4, which are obviously the same molecule, but the way they're drawn, I hope you can see as they try to show you here on the right-hand side, that there is a mirror plane that completely bisects this molecule. So anytime you have a molecule that has more than one chiral center and it contains a plane of symmetry within the molecule, then that molecule will be a meso compound. Okay, we're going to talk about another form of stereoisomer. It's actually not really necessarily another form, but it just looks differently. And these are known as double bond stereoisomers. You're probably already familiar with this. So we'll just talk about the finer details about these type of stereoisomers. So the arrangement of groups around a double bond can also produce these stereoisomers. And there's two geometries are possible. And you've probably seen this nomenclature before. We've referred to some double bonds as cis and some other double bonds as trans. And this is just referring to this type of stereoisomer, okay? Now, we're also going to introduce a new type of nomenclature for these stereoisomers, and that'll be E and Z. So E and Z are basically synonymous with R and S, except that E and Z refer to double bonds, whereas R and S refer to chiral centers. Now, there might be a little bit of confusion here. Oftentimes, cis and trans are used interchangeably with E and Z, and strictly speaking, they do have their particular uses. So the cis and trans, it's a little bit messy. The cis and trans form of describing this is when a carbon-carbon double bond, so each, let me step back. For when each atom of a multiple bond, a double bond, has only one substituent attached to it. So in this particular molecule, here's one substituent attached to the carbon of, or one of the carbons of the carbon-carbon double bond, and here's the other substituent on the other carbon. Said differently, what you'll see then, if there's only one substituent at each carbon of the multiple bond, then that means there has to be a hydrogen atom attached to both ends of the atoms that form the multiple bond. Okay, so one way of looking at cis and trans multiple bonds is by looking at the relationship of the hydrogen atoms. If they are on the same side as they are here, then we call this a cis double bond. And if the two hydrogen atoms are on opposite sides, then we call that the trans double bond. Why do we have a different way of naming this as E and Z? Well, because we don't necessarily always have two hydrogen atoms to look at on opposite sides or on the same side or on opposite sides of the multiple bond, which is why we have this other type of nomenclature. Okay. So in order to determine the stereochemistry about a multiple bond, we're going to assign priorities to the groups attached to the multiple bond in exactly as we did with stereocenters. So we're still using the Kohn-Engel pre-log system in order to do this. And for each substituent attached to either end of the multiple bond, we assign priority 1 and 2. Then what we do is we look at the relationship of the two groups of higher priority on either side of the multiple bond. If they are on the same side, we would designate this Z, and if they are on this opposite side, then we designate this E. So let's go through an example of this to make this a little bit clearer. So here's a molecule. And I want you to see here, again, I want you to look at both atoms that make up the multiple bond. So I'm obviously referring to this carbon atom here and this carbon atom here. What we want to do is assign priorities to the two substituents attached to the one atom of the multiple bond, and then we want to assign the priorities of the two substituents attached to the other atom of the multiple bond. Note here in this particular molecule that the cis and trans designation doesn't really apply here because Again, I can't look at the relationship of the two hydrogen atoms because this molecule doesn't have two hydrogen atoms attached to the atoms of the multiple bond. There's only one. And this is why we have this EZ nomenclature. So if we start off with, let me just number these carbon atoms. So this will be carbon 1 and that's carbon 2. You look at carbon 1, that's the carbon. So that's kind of like the stereocenter. I want you to think of it that way. So in the Kohn-Engel pre-log system, you look at the atoms directly attached to, either the stereocenter or in this particular case, the atom that is part of the multiple bond. So we're asking ourselves, what is directly attached to carbon 1 as what I've labeled as carbon 1? Okay, there's a carbon atom right here attached to it, and there's an oxygen atom. Which one has the higher atomic number? Of course, the oxygen has the higher atomic number. Therefore, that group gets higher priority. And this is why they've circled it here. Okay, so that's the left-hand side done. Now we go over to the right-hand atom of the multiple bond. Again, it's a carbon atom, which I've labeled as 2. What is directly attached to that carbon atom? Well, there's a carbon right here, and there's a hydrogen atom. Carbon has a higher atomic number than hydrogen, so it gets higher priority. So this is why they've circled this group, okay? And if you put those two higher priority groups together on the same molecule, so we'll look here, so there they are there. Notice that the two groups of higher priority are on the same side, so we would label this as Z, as it's shown here. Had they been on opposite sides of the double bond, then we would have labeled it E. Now, you may have a hard time remembering if Z is on the same side or E is on the same side. Let me share with you a little mnemonic device that I was taught when I was an undergrad, and I've never forgotten this. And I remember my organic prof wrote this on the board. Oops. He wrote Zame Zide, meaning that Z, of course, is when the two groups of higher priority are on the same side. I've never forgotten it, so if you want to use that, then by all means do so. And that's it. I mean, you just follow the Kohn-Engel pre-log rules as we did with stereocenters. You're just finding out the two higher priority groups on either side of the multiple bond, and then you just ask yourself what's the relationship between them, and then you can assign your E and Z. In terms of nomenclature, the stereochemistry, and this again has been mentioned in the nomenclature notes. There's a slide that kind of summarizes this, but I'll just reiterate this here. Whenever you do have a stereochemistry designation, whether it be R and S or whether it be E and Z, these are placed at the very beginning of the name. So this will be in place actually in front of the substituents, the first field, typically in parentheses. Now, if this is typed out, they are usually italicized. However, if you're just writing it out, then obviously we don't expect you to italicize it. If there's more than one stereochemistry designator, then there'll be a number in front of the R or the E, and that is referring to the atom at that particular number. So for example, we have this molecule here. This is 2-bromobutane. Notice that there is a wedge here. So there's an actual stereocenter right here. And so this particular molecule would have, there's one chiral center. It has to be chiral. So the absolute configuration of this would have to be either R or S. It turns out that this particular molecule is R. And so you can see in its name, this is its full name. Notice that the R comes right in front of where the substituents are. Okay, there's no number referring to this particular stereocenter because there is only one stereocenter. So if you have, any sort of knowledge in stereochemistry, you'll be able to determine which stereocenter is R. If, however, you have two or more different stereocenters, as in this molecule here, this is 2,3-dichloropentane. There are two stereocenters in this particular molecule, and so you would actually need to designate which stereocenter is R and which one is S, and so on and so forth. So the full name here, so if you were to number this molecule according to nomenclature, we would start from left to right, 2, 3, 4, 5. There's the numbering. So it's telling me then that the stereocenter at position 2, that carbon atom, has an absolute configuration of R, and the stereocenter at position 3 has an absolute configuration of S. Okay. Let's just briefly talk about physical properties of enantiomers and distereomers, or physical properties of stereoisomers. You have to understand that distereomers of a compound, they all have distinct molecular structures and they have distinct physical and chemical properties. Okay, so just as an example, you know, this molecule we just looked at in the previous slide, the 2,3-dichloropentane molecule, this particular molecule has a diastereomer to it. I know because it has more than one chiral center. So this particular molecule would have a particular melting point or boiling point, for example, and then its diastereomer would actually have a different melting point and or boiling point. Okay, that's what we're saying. They have different physical properties. They would also have different chemical properties. They might not be drastic changes in physical or chemical properties, but they are different nonetheless. Enantiomers, however, are a little bit trickier. So pure enantiomers have identical physical properties, okay, except for in one case. And this is the way that enantiomers will rotate plane polarized light. Okay, and so this diagram is just trying to show you what actually happens when you have enantiomers and their interaction with plane polarized light. What exactly is plane polarized light? All they've done is when you have a light source, and so here's your light source right here or here, and all they've done is the light is propagating in all manner of directions, okay? And then what they do is, so they call this unpolarized light, they pass this through a filter or a polarizing filter, and it basically allows one plane of light to come through. And so now all the light passing through this particular filter, it's pointed up and down, so to speak. It's in the same plane as this red arrow here, okay? That's all plane polarized light is. So it's polarized light. It's only going one direction now, it's in one plane. And now what they do is they take that light and they pass it through a sample of, let's just say it's a pure enantiomer. Let's just use, as an example, how about this 2-bromobutane? So let's imagine that it's R2-bromobutane. So this light is going through this R2-bromobutane here, and it's gonna rotate that light, that plane polarized light, by a certain degree. And we have a machine, a polarimeter, which can measure the angle, the distance of rotation of the plane polarized light. So you can see here, it's rotated, and that measurement, that angle is measured in as alpha here. And yeah, you can't predict by how much it's going to rotate. It'll just rotate it in a particular direction by a certain amount. Now, let's imagine now that we do the exact same experiment. So we get the exact same plane polarized light, and now we pass this plane polarized light not through R2-butane. That's what it was, right? Yeah, R2-bromobutane. But now we're going to pass it through S2-bromobutane. And what we'll see, if the two enantiomers are perfectly pure, you'll see that the molecule, the different enantiomer, will rotate the plane polarized light by the exact same amount, except in the opposite direction. So it's a kind of a unique feature to enantiomers. Every other physical property is identical. So pure enantiomers have the same melting point, the same boiling point, everything, except for the way they rotate plane polarized light. I want you to think about this a little bit further. This is one of the reasons why, well, I'll just say that this is one of the reasons why enantiomers can be difficult to work with, because you're going to want to, in synthesis, in chemical synthesis, we always want to be able to separate these two different enantiomers. So you'd want to be able to separate a solution of R2-bromobutane from S2-bromobutane. And if you think of most of the techniques that we use in order to, separate molecules, we typically do this based on their differences in physical properties. This becomes exceedingly difficult to do if the two compounds have the exact same physical properties. Now, the reason why it's important to be able to separate these is because their chemical, because of their chemical reactivity. It turns out that, and this is especially true or especially important in biological systems, but different enantiomers can have drastically different biological reactivity, and that can have serious consequences to, a human, for example. Here's just another example of, the properties of enantiomers. So again, as it says here, because enantiomers don't interact with each other in the same way that they would if they were identical molecules. And again, I want you to think about this. You have to understand that if I'm talking about R2 bromobutane and S2 bromobutane, those are two different molecules. Enantiomers are different molecules. Diastereomers are different molecules. And it's a subtle thing because they have the exact same molecular formula, they have the exact same connectivity. It's their three-dimensional arrangement in space that makes them different. However, they are different compounds. But if you look here in this table, you can see we have S-alanine and we have R-alanine. And notice that they have the exact same melting point because enantiomers have the exact same physical properties other than how they rotate plane polarized light. However, if you take a mixture of these two compounds, okay, this is called incidentally a racemic mixture when you have equal proportions of two enantiomers. And you have to understand that if you take an equal mixture of these two things, that the R enantiomer is going to act sort of as an impurity to the S enantiomer, and the S will act as an impurity to the R. And something that you should know from Chem 1000 is that when you introduce an impurity into a pure compound, you typically would depress its boiling point and or melting point. And in this particular case, you can see the last entry in this table that if you have a 50-50 mixture, as they said here, so this is a racemic mixture of R and S alanine, notice the melting point. The melting point drops dramatically here. And this is because they're acting as impurities to each other. Okay. We're just going to finish talking about yet another way of representing organic compounds. These are known as Fischer projections. And this was used especially in carbohydrate chemistry. However, it's still relevant today. And so this is why we're still talking about it. These projections are an efficient way to draw molecules, especially ones that contain a lot of different stereocenters. So again, typically it used to be just used for carbohydrates, but it can be used basically for any molecule that contains many stereocenters. The thing with Fischer projections is you have to really understand the conventions of the way a Fischer projection is drawn in order to really grasp what the molecule looks like. So here we have two molecules. We've got glyceraldehyde, we have arabinose, two different molecules, and they're drawn in line structures here, right? So we have these two molecules here drawn in line structures. Over to the right are these exact same molecules, but they are drawn as Fischer projections. So typically what we do is you have this sort of long zigzag chain. What we do then is we look at it from top to bottom, so to speak, right? So you can see here, you've got your aldehyde functional group here. That's it up here. Got another aldehyde functional group there, and it's on top. Typically, they would usually put the group that is the most oxidized on top, and then line up the rest of the molecule going down from there. So you can see, for example, in glyceraldehyde, you have one chiral center, and then their chiral center is right there. And in arabinose, you have three chiral centers, and so they're listed down here, and here they are here in the molecule. And so basically what you do is you line all the chiral centers from top to bottom, so to speak, and it is actually a little bit easier to visualize what's going on here. With these carbohydrates, typically what you have on either side, on the left and right-hand side in a Fischer projection, is a hydroxide group and a hydrogen atom. So I want you to notice, look at all the chiral centers that have been indicated with the asterisk. The, if you look at the 1,4-glyceraldehyde, you have an OH group and a hydrogen, and then exact same thing. They're just in either left or right-hand side, depending on their stereochemistry. Now, one of the things you need to understand with Fisher projections is that mentioned over here? Yeah. And change slides a little too quickly. This point here is of vital importance that you understand. So in a Fisher projection, okay, all the vertical lines are depicting bonds that are angling into the page. They're not going to be drawn with a dash, but it's understood that they are going into the page. And all horizontal lines are depicting bonds that are coming out of the page or coming towards you, i.e. a wedge. Again, they do not use dashes and wedges in Fisher projections, but it's understood that those horizontal lines are coming towards you and those vertical lines are pointed away from you. And this is of the utmost importance. So, and that's what they're kind of trying to highlight here. So here's a molecule in a Fisher projection. And if you actually put in the dashes and wedges, this is what you would see. Notice the horizontal lines are 2 wedges and the 2 vertical lines are dashes. Same thing here, right? We've got a Fisher projection here. And if you put in the dashes and wedges, you would have it looking like that, okay? The thing you have to understand is that if you were to view a Fisher projection from its side, the carbon skeleton essentially forms this arch, okay? And what's important to understand is that the actual Fisher projection themselves, they actually don't represent a real conformation of the molecule. In order for the molecule to actually contort itself into a Fisher projection, it would be such a high energy conformation. It's just not practical to consider it that it would actually adopt that position. We only do it for drawing purposes. Okay, so it's only for drawing purposes so that we can visualize the chiral centers a little easier. So again, let's look at this molecule here. And it's drawn in the Fisher projection. They've actually put in the dashes and wedges for you. But what they're trying to get you to understand here is that you're looking at it from the side, okay? And so if you would actually be able to see now what this eyeball is looking at, you would be looking at it like this. And this is the arch that they're talking about here. There's the carbon skeleton and it's kind of arched up, okay? Now with 3 carbon atoms, there's really no problem with this depiction. This could be a real conformation for this particular molecule. But as soon as you get to a few extra carbon atoms, then it gets a little bit unrealistic, okay? So let's look at this molecule down here. So here's the Fisher projection. Again, just so for clarity, they've actually added the dashes and wedges. Again, typically we never do for Fisher projections. But again, you're looking at this from the side. So if you would actually see what that looks like, this is the molecule that you would actually see here. And now you can really see that pronounced arch in the carbon chain. And I'll tell you right now that that particular conformation for this molecule is crazy. It would never actually happen because there's so many different and better conformations that this molecule could adopt. But that's what this represents, okay? And it's important to be able to try and take a molecule in its line structure and then draw it in its correct Fisher projection, or take a Fisher projection and draw it in its proper line structure. And it's a little bit more tricky than you might actually think. Okay, we're almost done here. This is basically just a flow chart, so to speak, with our tongue-in-cheek sort of name here, stereochemistry. And it's basically a flow chart that you're going to start at the top and make your way down. It's a series of questions you can ask yourself in order to determine what the relationship of 2 molecules are. So this is really just there for reference for you.